At SpaceX, our primary goal is to enable people to live on other planets, most notably Mars.
They got a message from the action man. I'm happy, hope you're happy too. I've looked on a leaving love, so written touch for the crew. Speaking of nothing's good, it's pictures of jackets and synthesis. Ain't got no money, ain't got no hair. Take it for granted, it's glowing, glowing, glowing. She's the answers, find to forget. Now, major times, the junket, strung out in heaven's eye. Giving an old-time love.
The earth is full of the goodness of the Lord. By the word of the Lord were the heavens made, and all the host of them by the breath of his mouth. Let all the inhabitants of the world stand in awe of him. For he spake, and it was done. He commanded, and it stood fast.
Hey, NASA astronaut Reed Wiseman.
Hey.
Do you think you have a few minutes to answer everything about living in space?
I got all the time in the world.
Awesome. Well, where are we?
We are in the Space Vehicle Mock-Up Facility. It's a gigantic building at the Johnson Space Center in Houston, Texas. And this is where astronauts spend the bulk of their time training for spaceflight.
Is this the window where you took all of those really cool pictures of Earth?
This is the cupola. It's a series of 7 windows that look down on the Earth.
Nice. How big is the International Space Station?
They say it's about the size of a 5-bedroom house. It's kind of hard for me to conceptualize. In reality, it's just really narrow and really long.
How long did you have to train before going to the ISS?
About 5 years.
And how many total days have you spent in space?
165.
What's the record?
Jeff Williams, he has the US record, 534 days in space, but Russian cosmonaut Gennady Padalka, almost 1,000.
Wow, what's a groundbreaking experiment that you completed aboard the ISS?
I survived.
I heard you age faster in space.
Maybe a little bit.
Is there a maximum height or age that you have to be to become an astronaut?
We used to have restrictions on that, but now it's pretty much come one, come all.
Is there Wi-Fi?
There is, but it's not as good as it is on Earth.
How do you get in contact with people on the ground?
We have space-to-ground communication systems. It's basically a radio or a walkie-talkie, and we just call on this and say hi to Houston.
Is there a delay?
Almost none.
How did you get to the station?
A rocket.
How long did it take for you to get from Earth to the space station?
It takes about 6 hours.
And how long did it take for you to get back?
Oh, that's a crazy ride. It's about 3 hours long.
Any jet lag?
Horrible jet lag.
How often do you get to talk to your family?
Get to talk to them once a week.
Ever prank call anyone?
Of course you prank call people.
Ever get homesick?
Yeah, you get homesick a little bit.
So are the beds comfy?
There are no beds.
I heard you have to be strapped to a wall.
You do?
Are you claustrophobic?
A little bit.
What else can you do in your room besides sleep?
You can read, watch TV, do some work, whatever you want.
Do you have a bedtime?
Everybody has a bedtime.
Do you have alarm clocks?
I use my watch.
How many crew members do you have?
It was me and 5 others.
Were there any language barriers?
Doc and Yeshna, of course there were language barriers.
Ever get sick of your roommates?
No, you never get sick of your roommates.
What did you do in your free time?
Oh, you look out the window.
What's a typical breakfast aboard the space station?
It was very much like a breakfast on Earth, so I liked eggs, occasional oatmeal, maybe even a waffle.
Was the food any good?
I actually thought the food was pretty good.
What's your favorite meal on the station?
I love chocolate pudding cake.
How do you cook your food?
You can either inject it with hot water or put it in a food warmer.
What's the first thing that you ate when you got back to Earth?
I really wanted a pizza, but I saw a salad and went for it.
So did you have to work out?
You work out twice a day for about 2.5 hours, 2.5 hours.
And what kinds of exercises?
Primarily, you're either lifting weights or running on the treadmill. Our treadmill is attached to the wall, and so when you're on it, you're running straight down towards Earth. Very weird feeling.
So how do you stay on the treadmill without floating away?
Bungee cords.
So do you burn the same amount of calories as you do on Earth?
I think you burn a little bit more because your brain is always active.
I heard that in microgravity, sweat sticks to you.
It does. If you have hair, it kind of builds up in your hair and you get this big sweat bubble on your head.
How do you shower?
We have soap impregnated towels.
How do you pee in space?
Ooh. We have a funnel.
Where does your pee go after you flush?
A little bit of processing and then right back into the drinking water.
How do you pee in a spacesuit?
We have a diaper.
How much water do you have to drink each day?
You drink just about the same that you would on Earth.
Do you ever run out of anything?
Free time.
How do you get more supplies?
We have cargo ships. We have great companies like SpaceX, Orbital. We have Russian resupply vehicles and also Japanese HTV spacecraft.
What'd you miss most on Earth?
Oh, my wife and kids.
What personal items did you take with you?
Photos of my wife and kids.
Did you bring any space souvenirs home?
You always have to bring souvenirs home for your kids.
So I have to ask, what's your favorite planet?
Oh, it used to be Saturn until I saw Earth from space.
And if you were to travel anywhere in the solar system, where would you go?
I work at NASA. We all want to go to Mars.
Does the space station ever get too hot or too cold?
Oh, we keep it a balmy 72 all year round.
Nice. How about the temperature of space?
Plus 200F to minus 200F.
What about the temperature inside the spacesuit?
It's actually pretty warm, pretty nice, pretty comfortable because there's many layers of thermal protection.
How much does a spacesuit weigh?
Oh, it's really heavy. I think it's about 300 pounds.
How do you do your laundry?
We throw it out.
Do you have to clean the spacesuits?
Of course you got to clean the spacesuits, especially after a spacewalk.
How long does it take for you to put on a spacesuit?
About 45 minutes.
Can you put it on by yourself?
If you're in a pinch, you can put it on by yourself.
How long does a spacewalk normally take?
We train for about 6.5 hours.
And what's the max amount of time a spacewalk can last?
The maximum is about 9 hours. I think 8 hours and 54 minutes is our record.
How's the view?
Awesome.
What's the hardest thing about a spacewalk?
Just knowing that you're outside, and if you mess anything up, you've destroyed a $100 billion spacecraft.
And what's the most rewarding?
Coming back.
Sounds awesome. Well, I'm sure there are a lot more questions, but I know you're busy, so we'll save those for another time.
Sounds good.
Awesome. Thanks. Have a good one.
See ya.
We're on board a spaceship, but which way are we pointing? We have to control which way we're pointing because we're solar powered, and we have to point our solar arrays at the sun. We have to control which way we're pointing because we want to be able to communicate with the Earth, so our antennas need to point the right way for communications with satellites. We have to control which way the space station is pointing, even while we're asleep. So we have sort of like an autopilot that whatever we've set it in, it'll keep that attitude going, just like in an airliner. And we can control it as the crew while we're awake using this display right here. It can also be controlled by the folks in mission control on the ground, either from Moscow or from Houston. But how do you actually turn the space station? We have these huge spinning wheels, we call them control moment gyros or gyrodynes, and we put a little bit of torque on them, and instead of them turning, the whole space station turns. So we can steer our space station using spinning wheels and solar power. Nice efficient way to steer a spaceship.
If you've seen films like Gravity or 2001: A Space Odyssey, you're familiar with possibly the most terrifying death imaginable. Slowly drifting away from your space vessel, watching it recede into the blackness of space, and understanding that you have no way to save yourself would be an awful way to go. But what could cause such a tragic mishap, and how likely is it that you could be rescued in time? When astronauts step out of the ISS, they're protected by several systems. First and most importantly, their spacesuit, which protects the astronaut from the void of space and can supply up to around 8 hours of oxygen and 1 liter of water. The suit can be anchored to the ISS with a long braided steel tether with a tensile strength of nearly 500 kilograms, which keeps the astronaut secure even if he loses his grip. Finally, spacesuits are equipped with what's aptly referred to as SAFER, short for Simplified Aid for Extravehicular Activity Rescue. SAFER is basically a nitrogen-propelled jetpack with a small joystick that allows astronauts to propel themselves back to safety in the event of a tether failure or other problem. These safety measures have a perfect track record. Thankfully, no astronaut has ever been lost in space, but it's definitely possible, and the consequences of becoming disconnected from the ISS are terrifying. Let's take a look at that scenario. In the event of your tether failing during EVA, you would begin to float off according to whatever forces were acting on your body when you broke loose. So, for example, if you had attempted to catch a tool spinning off into space and became unhooked in the process, you would slowly drift towards the tool away from the ISS. At this point, with nothing to hold onto in a weightless environment, you'd be at the mercy of gravity. No amount of struggling could alter your course. That's where SAFER comes in. In an ideal situation, you'd simply power on the jetpack with the joystick, press a button to automatically negate any tumbling you might be experiencing, orient yourself using directional thrust from the jetpack, then begin the slow and nerve-wracking process of attempting to fly back to the ISS. But what happens if SAFER fails? In a situation where your jetpack refuses to function, depending on your trajectory and velocity, your odds of making it back to safety may be either very poor or basically zero. If you're lucky, you'll be drifting very slowly and not in a difficult direction, and you'll have another astronaut on EVA with you who could come get you, provided you're within the 26-meter range of his tether. If not, you're pretty much out of luck. The robotic arm on the space station is far too slow to capture a small moving target like a drifting astronaut, and there's not currently any vessel capable of rescue. The Soyuz capsules require a full day to power up and undock, and the Space Shuttle, the only vessel with a rescue-ready airlocked compartment, is in retirement. So, unless a fellow astronaut was willing and able to attach multiple tethers together into one long super tether and attempt to jetpack out to you, you're simply out of options. Depending on your trajectory, you might begin to fall towards the Earth. When this happens, you'll begin to accelerate faster and faster until you experience the unpleasant fate that is burning up on re-entry. If instead your trajectory was away from the Earth, you'd simply be captured in its orbit and have the remainder of your few hours of oxygen to contemplate your mistake. Depending on your personality, this could be the very worst death imaginable, or a fairly peaceful way to go. You'd have some water available to you so you wouldn't die thirsty. You'd get to watch the sun rise and set about 5 times, and see the continents and lights of civilization drift by far below you. Then, when your air runs out, you'll lose consciousness and fade away. Over the next 10 or 20 years, your body's orbit will slowly decay, and eventually you'll fall back towards the Earth and receive a free cremation courtesy of gravity. If you want to vicariously experience that visceral fear of drifting away into the dark void of space, go watch Gravity or this scene in 2001: A Space Odyssey.
Every day since November 1998, the International Space Station has been orbiting the Earth at a speed of 28,000 kilometers per hour. Having spent several months on board the International Space Station, the time has come for 3 of its crew members to travel back to Earth. The return journey aboard a Soyuz capsule takes 3.5 hours. Before it can start, there's a lot of preparation to do, both in space and on the ground. The normal landing site for the Soyuz is Kazakhstan. A group of ground-based experts prepare meticulously for this operation. They take into account the current orbit of the station and then select the most appropriate landing site on the ground. The landing site is checked by the search and rescue team to make sure that the terrain is flat and free from any obstructions that could complicate the landing. The search and rescue team is able to operate even in extreme weather conditions. When all the information has been analyzed, the optimal return trajectory is calculated. 1 week before the Soyuz undocks from the station, the instructors and controllers located in the Mission Control Center near Moscow conduct a remote training session with the crew and the onboard simulator. During this session, the crew are reminded about the most important actions they will have to perform during the re-entry. They carefully run through the procedures for each critical step, including the scenarios that could lead to an emergency descent. They are also briefed on the latest details of their trip back, such as landing conditions and the precise timelines for the activation of vehicle systems. The onboard crew runs a test of the Soyuz vehicle and begins packing items that will travel with them back to the ground. The Soyuz is then activated, and the crew starts preparing it for undocking. When instructed by the ground controllers, the crew say their goodbyes to the colleagues staying behind and close the hatch that separates the Soyuz orbital module from the station. The hatch is carefully checked to make sure there are no leaks that could cause an unexpected cabin depressurization. The crew members put on their spacesuits and enter the descent module that they will occupy for the ultimate roller coaster ride back to Earth. Former astronaut Frank de Winne is now head of the European Astronaut Center in Cologne. He remembers clearly the emotions he felt as he was about to leave the International Space Station.
Wow, today I'm really going home. Because of course, the days before you're preparing for the descent, you're reviewing all the procedures, you're going through all the radiograms, but it's only at the moment that you're in your spacesuit and that the hatches are closing that you know that 4 hours later you will be back on Earth.
Both crew and vehicle are now ready for the undocking sequence. The Russian segments of the station have several docking ports for hosting Soyuz vehicles. In this example, the vehicle is going to undock from the so-called service module. In this case, the undocked Soyuz reaches an orbit below the station. The orbital velocity of the Soyuz also increases. Sometimes, however, the Soyuz is docked to a port underneath the station. In these situations, approximately 40 minutes before the undocking, the station changes its orientation. The Soyuz then undocks and joins a higher orbit, and its velocity decreases. In both cases, after one revolution of the Earth, the orbits intersect, but because of their now different velocities, the station and the Soyuz arrive at the intersection point at different times. This prevents any possibility of a collision between the two vehicles. When the flight director is ready, a "go" is given to the crew to initiate the undocking. The crew commander issues the command to open the Soyuz hooks. These are the only mechanical devices holding the vehicles together. After approximately 3 to 4 minutes, the hooks are fully opened and the Soyuz is no longer firmly attached to the station. A set of pushers that were kept mechanically compressed while docked gently ease the Soyuz away from the station at a relative speed of 12 to 15 centimeters per second.
Undocking confirmed at 9:56 p.m. Central Time.
Being so close to the station, the Soyuz propulsion system is inhibited in order to avoid contamination of the station with residual chemical dust produced by the Soyuz thrusters. The crew gets visual confirmation of the separation through the image provided by the external TV camera and also from indications displayed on their monitors. ESA astronaut Paolo Nespoli returned to Earth aboard a Soyuz spacecraft at the end of Expedition 27.
I didn't actually felt the detach when we detached from the station. Physically, I did not feel it. The physical departure station is done because of a push or some spring that there is inside. You don't want to start your engines close to station because you're going to plume everything. So you're just kind of drifting away, and what you're doing there, what we were doing, we're just looking at the instruments, looking at the camera outside and checking that the Soyuz would be inside the departure corridor. This is what we were doing. Didn't really felt anything. The only thing is that we felt we started this long journey back to Earth.
3 minutes later, When the spacecraft has moved about 20 meters, the crew monitors the 15-second burn that increases the separation speed up to 2 kilometers per hour. This leads the Soyuz to a safe position relative to the space station. After the undocking, the ground controllers upload the data needed by the onboard computer to autonomously perform the descent. The crew is in constant communication with the ground. They verify the validity of the data before allowing the computer to use it. At this stage, the crew must pay special attention to prepare for the next critical operation, the deorbit burn. As can be seen, although the Soyuz is now far away from the station, it is still orbiting the Earth at an altitude close to that of the ISS. The purpose of the deorbit burn is to force the Soyuz to decrease its speed. As a result, the trajectory of the vehicle changes and it re-enters the atmosphere. The atmosphere acts as a natural brake and does most of the work in slowing the Soyuz down until a set of parachutes opens and ensures a relatively soft landing. This braking is achieved by using the main engine located in the rear side of the spacecraft to push against the direction of travel. The required orientation and duration of the braking impulse must be precisely calculated and achieved because it directly influences the steepness of the re-entry path.
If we don't burn enough, then we have still too much speed and we will still be too high in the atmosphere, and we can actually skip off the atmosphere and then go further into space. And that, of course, would not be a successful re-entry. On the other hand, if we burn too much and we come in too steep, then we will have too much speed when we are in the lower parts of the atmosphere. The heat that is normally around 2000 degrees Celsius will be much higher and we have a risk of burning up. So also therefore it's very critical that we do the correct deorbit burn and that we really fix this around 120 meters per second.
To achieve the correct burn, the main engine fires for exactly 4 minutes and 45 seconds. The Soyuz now follows a trajectory that will lead it to intercept the dense layers of the atmosphere, leading to a safe re-entry and landing about 55 minutes later. As the vehicle travels along its trajectory, about 30 minutes before landing, and at an altitude of roughly 140 kilometers, it separates into 3 parts: the orbital module, the descent module, and the instrument compartment. There is no chance of the individual modules colliding with each other. This is called impactless separation. Only the descent module hosting the crew will make it back safely to Earth. The other 2 will disintegrate and burn up in the atmosphere.
The separation of the spacecraft in the 3 parts is happening through several seconds because there are several parts that gets detached after one or the other. All of these actions are done with explosive bolts or explosive implements. Seen from inside of the spacecraft, it felt like there was somebody outside the spacecraft with a sledgehammer that was hammering here and there, up and down. And so every few milliseconds, the spacecraft was shaking with this bang, 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 bang. It felt really interesting, actually.
The descent module experiences extreme high temperatures during re-entry, so to protect it and the crew inside, it's fitted with a special protective coating and has a heat shield on its base. As the atmosphere becomes more dense, the descent module positions itself so that its heat shield points forward. The capsule is about to enter the Earth's atmosphere. This will be the most stressful part of its journey home.
By the time we were supposed to re-enter the atmosphere, I actually looked out from our window and I actually looked, we were tumbling. And I was a little bit puzzled because I thought we need to re-enter in a special angle. So I started looking at procedure, we did a few things, and when I looked out again, I saw that we were already inside there's plasma things. It was getting really red, and actually the window was getting pretty dark. What was happening that a plasma stream is actually burning the outside layer of the window, which has a protective cover. So it was kind of interesting. At that point, I really did not feel that much. I mean, the gravity starts grabbing you, but it's very gentle at the beginning, and you actually use it to feel or go into the seat and buckle up, pull your straps so that you really lay into the seat. It was an interesting feeling.
The descent module follows a path that is similar in shape to that made by a surfer riding a big wave. Like a surfer, the Soyuz is able to make small adjustments to keep itself on track. So how is the trajectory of a free-falling capsule controlled? Even though it doesn't have wings, the Soyuz capsule is able to change the way it flies through the air. The design of the Soyuz enables it to do this. The capsule's lift increases when it rotates in one direction and decreases if it rotates in the opposite direction. In this way, the capsule is able to keep to its planned trajectory. As a side effect, this rotation also induces a sideways displacement of the module. This effect is very useful because it gives more flexibility for the selection of the landing site. This sideways maneuver has already been taken into account when selecting the optimum trajectory. During the descent in the atmosphere, the crew feels the effect of the deceleration when their weight exceeds several times their own weight on the ground. The maximum G-load, 4G, is experienced when the capsule reaches an altitude of roughly 35 kilometers, when it's already been traveling for 6 to 7 minutes in the atmosphere.
Gravity is a very, very strong force. We do not understand here on Earth how gravity has such a hold on our body, on what is around us. You do feel it when you come back from space, because now you have been in a non-gravity environment for a long time, and then you see all these forces grabbing you. You look at stuff and you feel your hands are heavy, you feel your watch weighs a ton, your books, the materials around you, your head, it's extremely heavy. And it's really, really, really a very strong feeling.
In the unlikely event that the automatic control system fails, the crew is able to use a manual hand controller as a backup. They train extensively to prepare for this possibility. Another option is the ballistic descent. The spacecraft starts spinning and flies a much steeper trajectory without any additional sideways displacement. The G-load in this case will increase up to 9. When the capsule reaches an altitude of 10.5 kilometers, its speed has already decreased from 28,000 to 800 kilometers an hour. In order to further decrease the speed, the parachute cover is jettisoned and a series of parachutes are deployed.
At the end of the atmospheric re-entry, you really start hearing the noise of the wind and the sound. You're almost breaking the sound barrier. Then in the opposite direction, of course, you're coming back into the normal area of flying. And this is around 30,000 feet that the parachute has to open. This is actually a very critical moment, and it's one of the only things in the Soyuz where the crew does not have a manual override. So this is only an automated system. So far it has always worked, and we also have a backup parachute that can help us in case that the main would not open. But it's also a very violent moment. You can imagine this 2,000 kilogram capsule that is soaring at the speed of sound through the atmosphere, and then all of a sudden you have a parachute that opens on the side and that pulls on you like with a little string. It's almost like a yo-yo, and you see the capsule going all around. It's much worse than in a roller coaster because it motions in all directions, and it's a little bit scary for some of us. For some others it can also be fun to say like, oh, this is the best ride I ever had.
Then, a few minutes later, at a height of 8.5 kilometers, the drogue chute finally deploys the 1,000 square meter canopy of the main parachute. This slows the capsule down to a speed of 22 kilometers per hour. The capsule is suspended under the parachute with a specific angle relative to the ground. This angle helps the capsule to dissipate the heat accumulated on its surface and structure during the re-entry.
But then everything calms down, of course, once that the main parachute has deployed. You really can't to the calm air after this whole violent re-entry, the violent opening of the parachute. Then you're hanging safely, slowly descending to the earth underneath your parachute. And this is actually the first time that you know, yes, I'm safe, we're gonna make it.
At an altitude of roughly 5.5 kilometers, the frontal heat shield and external window glass are jettisoned. The capsule vents excess fuel and oxygen from pressurized tanks to reduce any chance of an explosion when it hits the ground. In order to position the spacecraft adequately for the landing, the main canopy switches to symmetric suspension. This setup ensures that cosmonauts' seats are now perfectly positioned to absorb the landing impact shock. The retro rockets that were hidden behind the heat shield are prepared for firing. Inside the capsule, the crew seats automatically raise in order to prepare shock absorbers. Usually, the search and rescue team equipped with aircraft and helicopters start tracking the Soyuz capsule even before the very first parachute is deployed. The helicopters land next to the capsule shortly after touchdown, and the team help the crew to exit. Finally, 70 centimeters above the ground, the 6 retro rockets fire to further reduce the capsule speed to approximately 5 kilometers per hour. The capsule hits the ground, but the crew's seats continue moving down, and shock absorbers help to make the landing softer for the crew.
The soft landing is not really soft. You prepare for it by putting your arms against your body, not touching all the metallic parts, all your books against you. You're not talking, not to put the tongue in the middle of your teeth, and you're laying there trying to be as inside your seat as well as you can. And you're waiting for this soft landing to happen, which for me felt like a head-on collision between a truck and a small car, and of course I was in the small car. So when this happened, it was like bada boom, everything shook. I was kind of checking in there, everything was saying, and then silence, everything was stopped. So I looked a little bit around, I looked at my crew members, and then I said, hey guys, welcome back to Earth.
Once landed, one of the first actions of the crew commander is to release one of the 2 ropes that connect the capsule to the parachute. This is important as in windy conditions, it prevents the capsule from being dragged away on the ground by the inflated parachute.
You know that you're on the ground, you hear the voices of the rescue troops that are next to you, and you know that 5 minutes later they will open up the hatch and you can breathe fresh air.
The crew is now safely back on Earth. They will soon be reunited with their families and begin the rehabilitation process after their extraordinary journey.
Subscribe for more space.
Hi, Chris. My name is James Allen, and my question is, in your opinion, what is the greatest contribution that the International Space Station provides to the world, and is Asteroid Watch a part of that?
We'll be watching for the asteroid a little later today. We weren't in a position to see that meteorite do all that damage in Russia. It's going to be very hard to see the asteroid. They did the math, and it's going to be less than a pixel for us to take a picture. So we may, with a time lapse, see it go by. But for the space station itself, of course, with all the experiments going on, it's very hard to predict when an experiment will have a breakthrough. But I'm hoping that over its 20 or 30-year life of the station, from way back in in 98 when it was first launched, I'm hoping that there is some science that happens on here that is truly breakthrough. We sure are setting ourselves up for it. Mounted to the top is the alpha magnetic spectrometer, which is collecting matter and antimatter and high-energy particles from the universe, trying to understand the fundament of what the universe is made of, studying the human physiology that you can't study on Earth when you take away gravity. But one of the main legacies may be that when one of you goes to Mars, you will be on a spaceship that has functioning pumps, is made of the right material, has a closed environmental system, recycling water and air, has all the systems that work. The hull is made of the right metal, all of those things because of what we learned here on the space station. When the first people sailed out of sight of land, it wasn't their first trip. They had sailed and learned how to build space sailing ships, what oakum you needed, how the sails should be built, how do you keep people healthy on a long sailing voyage before they ever started leaving sight of land. And they owed their legacy to the early sailing ships. And for those of you that leave Earth to go somewhere else, you're going to owe your legacy to both the science and the engineering that is the International Space Station.
Astronaut Scott Kelly says it was easier to adjust to life in space for nearly a year than to get used to gravity again back on Earth. He lived on the International Space Station for 340 days. NASA continues testing him to learn how extended space travel impacts the human body. Kelly posted a Twitter video Monday writing, "Gravity gets you down." He spoke with Manuel Bojorquez, who is inside the Johnson Space Center in Houston. Manuel, good morning.
Good morning. This is where Scott Kelly trained for that year in space. It is a mock-up of the International Space Station. It's also where we spoke with him about the mission and how he's feeling 1 week after his return to Earth. You seem to be walking a little funny. That's the effects of this, right?
Yeah, my legs are not feeling good.
Astronaut Scott Kelly is still getting used to walking on Earth again. The soreness is just one of the effects of spending nearly a year in zero gravity.
My legs are a little swollen still from the, all the fluid that shifts up to our heads and in space gets now pushed back down on my legs.
Your body's been through some stuff.
Yeah.
And is currently still going through it.
I'll show you my legs later when the cameras get turned off.
Okay. But just so the viewers know, it's just swollen as all that fluid goes back down there.
Yeah.
What was the toughest part about it?
Yeah, I think it's, for me, it's being away from your loved ones, your friends, your family. A year is not short, but it was very rewarding. It was enjoyable. It was something that I feel privileged to having got to do.
NASA is testing the effects of long-duration space travel for a future mission to Mars, and Kelly came with a huge bonus, an identical twin, astronaut Mark Kelly, who could be studied on Earth to highlight how the time and space impacted Scott.
I do clearly recognize that there's a difference between 159 days, which is my previous flight, and this experience at 340. So, I'm pretty sure they're going to see differences between, me in space for that long and him on Earth without question.
Ma'am, they are delicious.
But while he wasn't busy with more than 400 experiments, Kelly had fun.
I think it's part of our job, our responsibility to do that as the public face of NASA. Anything we can do to get them more excited about studying science, math, engineering, technology is something we should be doing.
Kelly posted more than 700 stunning images on social media. The view struck him too.
I'm normally like the more the like the tough fighter pilot kind of guy, but not after spending a year in space. I think I'm a little bit more compassionate now.
So it changed you?
I think it does. I think it does change you when you spend all this time removed and detached from Earth, and you follow what's going on Earth, and you know mostly what the news reports is not good stuff.
You look down below and
yeah, we should be doing better. We can do better. Got this great planet down there. Let's take care of it and let's do a better job.
And after 340 days in space, Kelly told us one thing he is thoroughly enjoying now is being able to sit down for dinner without his fork or his glass floating away. Nora?
Manuel, great interview. It really is incredible.
The little things, huh?
The little things and how much we'll learn from what he has done in space. It's terrific.
I like what he said about the planet. We need more compassion. We got a good thing going down here.
Absolutely.
Let's fix it.
The first time you look out the window once you're in space, I think the reaction of every astronaut is about the same. First, there's this huge gasp that goes, ah, wow, and you just can't believe what you're looking at. It looks quite infinite when you're down on the surface, but from above, looking back at the Earth, our atmosphere appears as a paper-thin layer, and immediately you sense how fragile planet Earth is. And I say that if anybody looked out the window just for 10, 15 seconds, that would be all it would take to change you forever. There's no other place like Earth. We haven't found another moon or planet anywhere in our solar system that is suitable for human life. And once you appreciate that this is it, this is all we have right here, and you see from space how we're destroying it, cutting the rainforest down and polluting the air, it just makes you realize, you know, we have to take better care of this place, because if it becomes unlivable, we don't have many good options. It takes all of us, all of the citizens of the world. It doesn't matter what country you're from, what your religion is. We're all more similar than we are different. We're all on this one planet together, the spaceship called Earth, you know, hurtling through space.
Here we have Mercury, for example. And you can see that Mercury basically looks a lot like the moon. It's a cratered world. It has no substantial atmosphere, maybe a real thin, but nothing substantial. And that's why you can see the surface is very cratered. It's got all these impact craters. There's nothing to stop it. Of course, objects that would impact Earth tend to burn up in our atmosphere. And so we have that nice protective atmosphere.
The atmosphere protects us.
That's right, it does. Mercury doesn't have that. And so that would be a little bit dangerous if you were there. Another issue would be the heat. Mercury is 3 times closer to the sun than we are. It's about 1/3 the size and 3 times closer to the sun. And that means if you were on the day side of Mercury, the surface temperature would be close to 800 degrees Fahrenheit.
800 degrees.
Yeah, so bring your sunscreen. Yeah.
Wow.
And then on the night side, it drops to, you know, a couple hundred degrees below zero. So it gets very, very cold on the night side. People don't realize that.
And it's part of that because the atmosphere buffers our temperature.
That's right.
It has no buffer.
That's right. There's actually two reasons for it. One of them is the atmosphere.
Okay.
There's no atmosphere to even out the temperatures. And the other reason is it's a very slow rotator.
Oh.
Yeah, Mercury rotates very, very slowly.
Like a
I think
rotisserie.
Yeah. Very
yeah.
slowly. So one side really gets baked. And it takes something like, I think it's 58 days for it to just for it to rotate.
It is slow.
Earth days, yeah. So it's very, very slow rotator. And for that reason, the day side just bakes and the night side just freezes. And of course, it is interesting that if you landed on the night side of Mercury, of course, you could have a spacesuit that would protect you from the cold temperatures potentially. But if you landed on the night side of Mercury, if you crash landed, okay, you can't get off. You're in your spacesuit. You're in your spacesuit. As long as you run west, you could actually keep ahead of the sunrise. It would be possible to run fast enough.
The rotation's so slow
right. You
that
could outrun it.
A jogger could stay out of the heat.
That's right.
Till he got tired.
You can't stop though. You can't stop because once you stop, the sunrise just catches up and then you're gone. So it's one of those little interesting factoids.
How long can you tread water? How long can you jog?
Exactly.
That's it. Yeah.
Exactly. So it's a neat little world. It's again, it's smaller than the Earth, about 1/3 the size of the Earth, and you can see it's just pockmarked with craters. And for a long time, we didn't know what one side of Mercury looked like because we sent a spacecraft there in the 70s, and it went past Mercury and mapped one side, and then it was in such an orbit that every time Mercury orbited twice, it would come back around and it mapped the same, but it got the same side because of the way Mercury rotates.
Yeah.
Mercury rotates, let's see, it's 3 times every time it orbits the sun twice, and so they got the same side every time, interestingly. Another interesting thing about Mercury is it has a slight magnetic field. And that's interesting. Of course, the Earth has a magnetic field that causes your compass to point north, and that's caused by electrical currents in Earth's core. Mercury has that too. Mercury's is weaker than Earth's, but it's there. And that's surprising from a secular perspective because magnetic fields decay with time. They naturally run down as that electricity encounters resistance. The magnetic field decays. And we actually have good evidence that Mercury's magnetic field is decaying just like we'd expect because we sent another spacecraft there more recently. The Messenger spacecraft flew past Mercury, measured the magnetic field, and there are indications that it seems to have dropped since the 70s.
Oh,
so we've actually been able to measure.
Rapidly.
Yeah, yeah. And we'd expect that based on known physics. But the interesting thing is that's only compatible with a biblical worldview.
Oh,
because you see, because of the magnetic field decays so rapidly that in 6,000 years, yeah, it would be about this amount. But if it's billions of years old, it would be gone by now. It should have decayed a long time ago. And so
that's fascinating. The rate of decay is a constant.
It's an exponential decay, but we think the exponent is constant based on our understanding of physics. And so that means if you run it back in time, the magnetic field would have been outrageous if you push it back beyond 1 million years or something like that.
So it's an argument for a young Earth.
It is, yeah, or a young solar system even.
Yes, I mean young solar system, sure, excuse me.
So it's an interesting little world. Again, we can see it rotating here as I speed up time, but you can see it rotates very slowly, and it's actually orbiting the sun significantly as it rotates. And let me change the orientation here a little bit so we can see that.
You would almost think the tremendous heat that one day it would just kind of burn up.
Yeah, although it doesn't have flammable type of elements that it's made of. It's mostly rock, and rock can withstand a lot of temperatures. But that's one reason why it doesn't have much of an atmosphere. Any atmosphere would tend to boil away. So that's Mercury. And it's an interesting little planet. It's hard to see because it's always very close to the sun. And people might have seen Mercury without knowing it. It would be just after sunset or just before sunrise. It'll appear as a little star, depending on where it's at in its orbit. And it's a little hard to see. So let's go to the next planet, Venus. Venus has been called Earth's twin because it's about the same size as the Earth. And that's about where the similarity ends. It's other than it's solid. Okay, so it's got a solid mass on its surface. But that's kind of what Venus looks like. You can see it there from space. Venus is very easy to see. Very easy to see from Earth. In fact, it's the 3rd brightest object in our sky. You got the sun, you got the moon, and Venus.
And then you got Venus.
Yeah, in terms of the naturally occurring objects that are regular objects. And you can often see it in the evening sky as a very bright star in the evening sky or in the morning sky, depending on what part of its orbit it's in. So that really object, and people look at it, man, that's a bright star. It's Venus. It's Venus. And it's one of the stars that's mentioned in Scripture as the morning star.
Oh, it's the morning star, the bright morning star.
That's right. That's right. That's Venus. So it's a lovely planet. It's beautiful to look at, but you probably wouldn't want to go there either.
Kind of looks like an egg.
Yeah, it kind of does a little bit. It's got that kind of yellowish color, and that's because that's clouds that you're seeing.
Okay.
Venus is permanently...
It has an atmosphere.
It has a very thick atmosphere, much thicker than Earth's, 1,000 times something like Earth. It's very, very thick. And those clouds that you see there, they permanently enshroud Venus, and so you would never see the sun on Venus.
Wow.
It would be permanently overcast. And growing up in Ohio, it was kind of like an Ohio winter, really.
What's the temperature?
The temperature, interestingly, is actually hotter than Mercury. The temperature is 900 degrees Fahrenheit.
And why is that?
And why is that?
Because it's further away.
You think it'd be less,
from the sun.
but it's because of a greenhouse effect. That atmosphere traps in the heat
Cooks it,
and basically cooks the surface. And we've landed, actually the Russians landed some spacecraft on the surface of Venus, and they lasted for a little while. They were able to take a couple pictures before they gave out, because it's hard to make something that can survive in 900 degrees Fahrenheit temperatures, but it's really interesting. In fact, the atmosphere is very, very thick. It's so thick it actually bends light significantly. And that would have the effect, it would make things look distorted. If you were standing on the surface of Venus, instead of the world going down, because it's a sphere, it would seem like it's going up. It would feel like you were standing in a large bowl, because the surface would seem to go up. Isn't that strange? Because of the way the light bends.
Yeah.
But that thick atmosphere is what really makes Venus kind of interesting and unique in terms of the inner planets. Now today we can penetrate that atmosphere and with radar, and we know that the surface of Venus looks like this.
Oh.
So it's a really interesting surface, and we can watch and see how Venus rotates with time. Venus actually rotates backwards and very slowly. Its day is actually longer than its year, interestingly. And let's see if we can get this, make sure we're turning the right way here. There we go. Spin it around here. Yeah, that's right. That's right. So there it is, rotating backwards. And you can see it's orbiting the sun the same direction as the other planets, but its rotation is the opposite. And so the day actually being longer than the year in terms of its rotation.
That? What would make one planet rotate one way and another way?
There's only one explanation as far as I know, and that's God is creative, and He's given these planets different spins. I don't think there's any secular explanation for that.
Explanation, just God made it that way.
In fact, in the secular view, the planets really ought to be aligned. They ought to be the same and rotating at about the same speed in the same direction. And that's the expectation of the secular model, and few of them do, really. I mean, a lot of them are different, and usually they invoke a giant impact to say, well, something hit it and changed the rotation. But Venus is almost exactly upright. It's just backwards. It's just rotating backwards, and so that's contrary to what you'd expect, really, in the secular model.
Continues to point to a designer, creator who just said, because I'm an artist also, I'll just make this one go this way.
That's right. That's right.
Isn't that awesome?
I mean, the solar system, some things need to be a certain way for the solar system to work. And so it's probably a design feature that the planets all orbit in the same direction so that there are no collisions, for example. And so that makes sense. But they can rotate different directions, and Venus does that. Now, again, we mentioned the surface temperature is not very pleasant, and also those clouds that cover Venus are sulfuric acid type compounds. So there's just lots of wonderful ways to die on Venus. It's not a place you'd want to visit, really. Yeah. It has no moons, and it has no liquid water or anything like that. Of course, it couldn't, water couldn't exist in a liquid state with that kind of temperature. So it's Earth's twin in name only and in size only. It really is about the same size as the Earth. But that's where the similarity ends. Other than that, it's a toxic world. And some people say, well, why would God create, with thick, a poisonous atmosphere like that? Well, we're not supposed to go there, right? I mean, Venus is designed to do what it does, and those clouds that would kill you if you were there make Venus very reflective, and they make it one of the most beautiful objects in our nighttime sky. So it really is stunning.
The morning star.
Yeah. Now the next planet out is Earth.
I've heard of that one.
I've heard of that one too. And all the best restaurants are on this planet right here.
Is that right?
And everyone you know or ever will know is on this little planet right here. But Earth has a number of interesting features that are unique just in terms of a planet because it is designed for life. And so of course it has liquid water on its surface, which we think is necessary for any kind of life to exist. And so Earth's covered with liquid water. That's one of those ingredients for life. Earth also has plate tectonics. As far as we know, it's the only planet that has plate tectonics.
Is that right?
Yeah. And we think that that's also a design feature because we think the mechanism that God used to flood the world and then to establish the world again after the flood of Noah. We think actually the continents were probably together before the flood year and then pushed apart. And so God flooded the only planet that really could be flooded, and in a way that He designed the planet to be able to do that. So it's kind of interesting that it's designed with just that feature in mind.
It seems to me the evolutionists are desperate to find water somewhere else.
Yeah.
Because water really is linked to life, isn't it?
It really is. And they would say, well, where you find water, hey, life probably evolved. Well, no. You can have water out in space. And the water molecule is actually pretty common in space, although Earth's the only place we know of where it's abundant in its liquid state. But it wouldn't surprise me if they found liquid water somewhere else in the universe. It's a big universe.
And it really wouldn't prove anything.
No, it wouldn't. It wouldn't. And I would not expect really to find life out there. The Earth is specially designed for life.
Right.
In fact, the moon actually stirs up tides on Earth's oceans, keeps the oceans from stagnating. Yeah, and so it has that cleansing effect. And so it really is designed for life. It has those special features. Now our next planet out is Mars. I'm not going to spend a lot of time on Earth since we live there. I figure people probably know that one pretty well. Mars is probably the most Earth-like planet in terms of if you wanted to go there on vacation, Mars would probably be the one to pick. You'd at least have a chance of surviving if you brought your spacesuit and enough food and water and so on, because Mars is similar. It's not similar in size, about half the size of the Earth. But the temperature, it's a little too cold, but it's not astronomically cold. It's just a bit chilly there.
What does a bit chilly mean? Put some numbers on it.
Well, it could get above freezing at some times.
Is that
in the
right?
Summer.
Okay.
Yeah, it could actually get above freezing. And it has polar ice caps, and you can see there the northern polar ice cap. And it's got one on the south as well. And they change like Earth's polar caps grow in the winter and then they shrink in the summer on each respective hemispheres. Mars does do that too, just like that. Mars has seasons. It's tilted about the same as the Earth.
Yeah.
So it would have seasons about the same as the Earth.
Seasons.
The year is about twice as long as the Earth's. So, but other than that, you're a little bit further away from the sun. The sun will be a little darker, a little smaller in your sky. But the rotation rate's similar to Earth, 24.5-hour rotation, which is kind of neat because you could get up a half an hour later every day and it'd never catch up with you. So it's kind of neat. It's just got that little extra half an hour that you could sleep in every day. So
well,
that's kind of a neat feature.
It has been the place that's captured the fantasies of the science fiction world.
Yeah. And that's because it is most Earth-like. Yeah. It has volcanoes on its surface, mountains. In fact, you can see, let me rotate it around here, you can see some of these volcanoes. Some of these features you can see from Earth with a large telescope, in fact, but especially these volcanoes here. You can see these large, you see those right there, those large, looks like big pimples. Well, those are actually large volcanoes. In fact, this one over here to the left is Olympus Mons. It's 3 times taller than Mount Everest.
Are these active volcanoes?
They're not. They're thought to be extinct, but it might be that they're just dormant. Some creationists think that these could erupt at some point in the future. It's possible.
And if they erupted, would it affect us in any way?
No, it would not. Okay. No, but it would be a spectacular...
It'd be something to watch.
Yeah, it would be something that would be indicative of biblical creation, because the secularists think Mars is billions of years old and therefore dead and should have no volcanic activity. But we think it might still have some. Wow. We think it's still possible. There are canyons on Mars. Here's a massive canyon. See that big, looks like a scar along the surface? Right. That's the Valles Marineris Canyon. It's much bigger than the Grand Canyon of the United States. In fact, that's about as big as the United States is across. Wow. Just to give you a feeling for that.
The whole way across the country.
So it's really amazing. Yeah. So it's a wonderful little planet. Now, again, not quite right for life because the atmosphere is carbon dioxide and very thin. You couldn't breathe on Mars. You'd have to bring a little bit of Earth with you. You'd have to bring your spacesuit, a little bit of air. No liquid water on the surface as far as we know. The conditions aren't quite right to support liquid water under most circumstances, but there's evidence that Mars once had liquid water on its surface, dried riverbeds and such. So it really is an amazing little world, and it reminds us that God is creative in the way that He creates these different planets.
He sure is. We're going to come back to that in just a minute, but we have to take a break. We have an incredible God. He's an engineer, He's an artist, and He's a creator. And we're going to talk about it when we get back. Don't you go away. We are back with Dr. Jason Lisle. And Jason, I've always wanted to say this, so I'm going to get to say this. When we left, we were on Mars.
That's right.
So take us back.
Okay. We're talking about Mars and how it is Earth-like in some ways.
Right.
The polar ice caps, they're actually made of carbon dioxide, frozen dry ice.
So it's not ice like our ice, it's more like dry ice.
There's some water ice too, but it's mostly carbon dioxide, frozen carbon dioxide, dry ice. And water would have the same effect on Mars that carbon dioxide does on Earth. Dry ice, it doesn't go to a liquid state, it goes directly to vapor. Water would do that on Mars because there's insufficient atmospheric pressure to keep it liquid.
Oh,
so yeah,
it's
kind of interesting.
Yeah.
A little bit of an atmosphere, so you'd have a blue sky, interestingly, sometimes. And sometimes the wind will kick up the dust and you'll get a pink sky. And so it depends on the time of day and the local conditions there. But otherwise, it's kind of similar to Earth in that respect.
We would have that if we had a dust bowl.
Yeah, you have something like that. Absolutely. Yeah. Mars has 2 moons, interestingly, and I wanted to show you these because they're kind of interesting to me. They're very different from Earth's moon. And we'll go to Deimos first. That's number 2. So Phobos and Deimos are the names of Mars's 2 moons. And the names mean fear and terror. And that's because Mars is associated with the god of war, and fear and terror go along with war. So when these were discovered, they were named after that. And there's Deimos, and you can see it's a weird-looking little moon, isn't it? And if we speed up time, you can watch it rotate around like that. And you can see it's one of the first things that surprises people is, wait a minute, it's not round. It's not a sphere.
Right.
And smaller moons tend to not be round. This moon is only it's less than 10 miles across.
Okay.
It's basically a big boulder in space. That's what it is. And it orbits around Mars. And it takes something like a day for it to orbit Mars, something like that, around 30 hours, I believe. And it just looks kind of like a big potato there floating in space. Really interesting. And so that's Deimos, the outermost of Mars's 2 moons, the outer of the 2. Now the inner one, Phobos, let's go to that one next. If we zoom out here a little bit. And there's Phobos on the other side. You can see these moons in a small telescope if you really know what you're doing, if you really know how to look for them. They're actually pretty bright, but Mars is 200,000 times brighter. And so it's a contrast issue. You have to in order to see these well, you have to kind of get Mars just off to the side of the telescope so the glare doesn't get in the way. And I've seen both Phobos and Deimos in a small telescope, little specks. And again, Phobos is just a little bigger than Deimos. It's only about 10 miles across. And you can see there, it's got a huge crater on one side of it. Looks like something hit it really hard. So really fascinating.
Now, our moon, we can see in God's creation plan that it has function. It creates the tides, which clean the ocean and things.
Right.
Is there any function known to these moons?
We don't know what they're for, what they do, other than it's, I think, an example of God's creativity. You know, Mars has 2 moons. Their gravity's not nearly sufficient to stir up any kind of tides. Of course, Mars doesn't have oceans anyway.
Yeah.
But their gravity would be insufficient to stir up tides. So you see, Mars doesn't have those design features that are right for life on Mars, because it's not designed for life. It really isn't. But nonetheless, they're interesting, and it gives us little examples of interesting physics. For example, if you were on the surface of Phobos, the gravity there is so weak, you could pick up a rock and throw it into orbit.
Oh,
it would
my.
go around, yeah, and you better duck because it come back
around and
and
hit you in the
or you could play catch with yourself. You could throw it that way and then catch it like that.
You keep practicing.
Yeah.
Make for an interesting baseball game.
And it orbits very close to Mars, so you can actually see. You can actually imagine looking up at the night sky and seeing Mars like that just up above you. I mean, it would be just spectacular.
Yeah.
So it's a fun little moon. It's a fun little moon to enjoy. So anyway, that's some of the characteristics of Mars. You can see it's got some things like the Earth, but some things quite different and not quite designed for life. And so all of this, you know, as we look at these different planets, it reminds us that we really do live on a very special world. A world that, according to Isaiah 45:18, God formed it not to be a waste place, He formed it to be inhabited. And these other worlds, not quite right for life. Mars is the closest, but even it doesn't have that protective magnetic field that the Earth has. It doesn't have the right kind of atmosphere. It doesn't have liquid water. It doesn't have those characteristics that are necessary for life. And that just reminds us that we really live on a special planet.
God designed all of the planets, but He fine-tuned Earth, didn't He?
He really did. In fact, if you think about it, God took one day to make all these other planets and stars in the creation week. 5 of the 6 creation days are working the Earth, making it right for life. Not that God needed time, of course, we understand that. But I think to show the Earth's special significance.
He was teaching the importance of that, yeah.
That's right.
The intricacy of everything that has to be fine-tuned to make life possible.
Exactly.
Is an amazing thing that nothing else you look at has.
That's right.
Yeah.
That's right. None of these other planets exhibit quite those features.
Very good.
Yeah.
Well, where do we go from here? How do we wrap this up?
How do we wrap it up? I think we just want to remind people that there are 4 planets that are the inner planets that are Earth-like. And we've seen Mars here. We've seen that if you land on one of Mars's moons, you get a spectacular view of Mars. We've seen that Mars is similar to the Earth in some ways, but different in some ways. And the similarities remind us that that God is a God of unity, but also a God of diversity. And so what we see in these inner planets is exactly the characteristics that we'd expect, given a God of diversity. And by way of contrast, and maybe as a little bit of a preview into another program, I just want to contrast this with one of the outer planets, Jupiter. Because you see, these inner planets are Earth-like. They're called terrestrial, meaning Earth-like, because they are similar to the Earth in the sense that they're solid, they have a surface you could land on. If you could somehow protect yourself from the heat of the inner planets or the cold of Mars, you could theoretically stand on these worlds. And that's very different from Jupiter, for example. Jupiter's a ball of gas. There is no surface on Jupiter. You could not land on Jupiter.
Surface.
Yeah.
Could you fly through it?
Theoretically, you could fly through Jupiter. Now, the gas gets very, very thick and it becomes liquid at some point, and so it'd be like going through molasses. But theoretically, you could do it.
It never gets solid.
Yeah.
That's amazing.
And so these outer planets are very different from the inner ones. And again, that reminds us of God's order, His unity, and His diversity. We have these planets that are like the Earth, unified, and these planets that are very different from the Earth, very diverse. And that's characteristic of the God that we serve. It's something that's built into the universe, and into life for that matter. The different kinds of life forms that we see on Earth, the fact that we can classify them, into kingdom, phylum, class, order, and so on. People think, well, that's because of evolution. That's why there's similarities and differences. But you can't argue that with the planets. The planets did not evolve from a common ancestor, and yet they exhibit similarities and differences. And so that's exactly what we'd expect given the God of creation, the biblical God who made each of these worlds and designed them to ultimately to reveal His glory, to glorify His name, and for our enjoyment, I think, as well.
I think you're right, for our enjoyment. I'm going to ask you this. We have a minute. Are we ever going to go to Mars? I don't mean you and I, but
I'm not.
I'm not either.
Some people it might be possible for people to go to Mars. It is a goal. There's I think it's the Mars One program, or they actually want to start a colony on Mars. I have to say, it's dangerous. It's very dangerous to put people that far away. I mean, we went to the moon, but the moon is close, very close compared to Mars. Mars is much further away. The moon was a few days away by spacecraft. Mars is 6 months away by spacecraft, minimum. And
so if there's trouble, you lose those people.
That's right. And it's a terrifying thought because human life is so precious, of course. Now, I'm not against a trip to Mars. I'm just saying there's caution. There's got to be a lot of caution because if you don't have the medical facilities there. If something goes wrong, you got to be prepared to deal with it.
And what's the takeaway if we do? Just to sort of say we did.
There's not much. Yeah. There's the coolness factor, but there's not a lot. Yeah. Most of the science we can do with unmanned spacecraft more efficiently and cheaply.
Jason, I have to say I love the lenses through which you look at our universe and our solar system. And I love the perspective you have that all of this really does declare the glory of God. It shows His diversity. It shows, like to make them all spin one way and one spin the other, just to have people sit around and say, I wonder why you did that. And the beauty of it all and the splendor of it all is remarkable. And I love how you see God in all of this. So thanks for sharing that with us. And folks, as we've been looking at the planets together, I hope too that it has enhanced your worldview to see God the Creator, God the Designer, God the Engineer at work in all of this. Always remember, my friend, that it's God's view that He created you. That should be your worldview too. Hope we'll see you again soon here on Origins. And until then, God bless you, my friend.
Hello, I'm ESA astronaut Samantha Cristoforetti. Welcome to Node 1, the place where we prepare our meals and eat up here on the International Space Station. I would like to show you one of my favorite meals up here, which is a chicken turmeric with champignon mushrooms, brown rice, and peas. And I would like to try and put the ingredients together for you, see how it works in space. Well, first of all, we don't have a plate. It wouldn't make much sense. So I'm gonna try and use a tortilla instead of a plate. We have plenty of those. They're kind of handy up here because they don't make crumbles, which are a little bit of a problem. And then I want to make sure that the ingredients stick to the tortilla. So I'm gonna start by spreading some peas cream. I have already heated the food pouches with the ingredients in the food warmer. So this is my first ingredient, peas. And this is one of the most important tools up here in space when it comes to the kitchen, a scissor to open the food pouch. So I'm gonna spread it on the tortilla. It's kind of hot. Okay, next I will add brown rice. It's whole rice, it's not refined, so a great source of good carbs. Next I will add some champignon mushrooms. And finally, my chicken with turmeric. There we go. It's not too bad considering that we are in weightlessness. It's pretty yummy to me. Now, together with this video, you will also find a video that shows how to make this recipe in a normal Earth kitchen. In fact, I was taught how to prepare this recipe by the chef who prepared these space pouches for me, Stefano Polato. And you will find the list of ingredients and all the instructions. So maybe you want to try it in your kitchen, maybe with your family next weekend. If you do so, please make sure that you send us a picture or a little video, and we'll enjoy watching that. Very good. Hello. Hello, and welcome to the toilet of the International Space Station. Let's say you're up here on ISS and you need to go to the restroom. You want to come to this cabin, and the first thing you want to do is grab this piece of equipment and turn this rotary switch 90 degrees to the open position. What that does is it turns on a fan, which creates a suction effect in this hose, so that you can use this yellow element for your number 1. For number 2, the principle is actually exactly the same, suction. We have a solid waste container here, and on top of it is this seat. And the solid waste container is connected via this hose to the same fan, so that, again, the same suction effects allows you to do your number 2 in weightlessness. I want to show you how it looks, but since we don't want any bad smells to come out, we're going to actually turn on the fan. It's going to be a little bit loud. There we go. Now you can lift the lid. There is this seat that sort of looks comfortable, but you don't really sit in weightlessness. So most of us actually prefer to lift this one as well and use directly the opening that goes into the bag. And in fact, there is a bag in there. It looks like this. And when we are done with our business, we close the bag and we push it down into the solid waste container. And then, of course, as a courtesy to the next person, we put a new fresh bag inside. The solid waste container gets changed when it's full, which is roughly every 10 days for a crew of 3 people using it. This one, for example, was installed on the 61st day of this year. So probably roughly around day 71, we will have to change it again. But urine gets recycled. So from the pretty complicated hydraulic equipment that is behind here and makes the use of the toilet in space possible, the urine actually gets directly transferred to another piece of equipment which is here in the floor, which is called UPA, Urine Processing Assembly, which is the first step into turning urine into potable water. Hello, and welcome to my hygiene corner here on the ISS. This is the place where I wash, brush my teeth, or after workouts, take a shower ISS style. The heart of the hygiene corner is the toiletry pouch, Comfort 1M. It's Russian made, and most crew members ask to have one sent up for them. It's really useful to deploy our hygiene items, and hygiene items come up in a Ziploc like this one. This contains supplies that need to last for 6 months. And they don't look much different from what your hygiene items look in your bathroom, probably. You can see a toothbrush here, toothpaste tube, deodorant. And as far as towels are concerned, we cannot wash stuff up here. So we get a supply of towels. Every week we get a towel like this one and a smaller washcloth. I usually take my new ones out on Sundays, so it's not quite time yet. I'll put those back. And for today, I will use the ones that I have already deployed for the week. Every second day, we can also take out a new, let's say, camping towel. It's one of those light towels. It comes in a foil like this. It's dry, and then we can add water, wet it, and it's really nice to clean your skin. In terms of brushing your teeth, it's actually very similar to what you would do on Earth. As I said, toothbrush and toothpaste look just the same, and you brush your teeth just the same. The only difference, of course, is that we don't have a sink to spit in when we're done all that extra toothpaste. So some astronauts just swallow it. It's quick and easy. I personally don't like to do that, so I actually spit it in a towel. It's not the most elegant thing, but you have to do what you have to do. As far as soap is concerned, it comes up in pouches like this one. You need to add water, and then you get a nice liquid soap pouch. which needs to last for about 2 weeks. And it's a no-rinse type of soap. It doesn't make a lot of foam, and it doesn't really need to be rinsed. And of course, we do not have any running water up here, so we also need to fill up water pouches. We can connect pouches like this one to the water dispenser, which is in the nearby module in the US lab. And I personally like to fill it up with warm water when it's time to wash, but you can also fill it up with ambient temperature water. So I'll go ahead and do this right now, and I'll see you in a minute. Here I am, and I got my water. So first of all, I'd like to show you how water behaves in weightlessness, which is kind of interesting. Of course, it doesn't fall down like it does on Earth, and it kind of tends to stick to your skin because of surface tension. I don't know if you can see it. See, it doesn't really want to move away from your hand, just because of that surface tension effect. Now, of course, I put a lot of water on my hand just to show you. You wouldn't use all that water to wash, just because it's a little bit difficult to control. So I'm actually gonna dry it off. But if you have some time to take your time and be careful, you can do that, I think. I do it sometimes. I really put some water on my skin like that. Just a little bit. And then I add some soap. Like that. And then you can carefully go ahead and rub it. And it actually really gives you a nice feeling of cleanliness. And then, as I said, I like to keep my actual towels here dry, so you can use them to dry off. Now, of course, you don't always have the time to take it slowly and be so careful. So if you are a little bit more in a rush, let's say it's a work day and you had your workout and then you have to rush off into something else, then you will simply, just squirt the water into your camping towel and add some soap, and that's a lot easier to control because you can just rub your skin like that. And I don't find it as pleasant, but it's certainly a lot quicker and easier to control. Now, all the water that you use eventually ends up in the towels that you use to dry. And we leave those towels close to a ventilation grid, like in this case you can see a ventilation grid right here, so that they can dry off. And all the water then is recuperated. It evaporates in the air, and then in the air conditioning system it condensates again, and it goes into our water recuperation bus, and it actually gets turned into potable water again. So we don't absolutely lose any of the water that we use to wash. Cutting your fingernails is not the easiest thing in weightlessness. Of course, you don't want to lose any pieces of nails around the cabin. So the best thing is actually to do it really close to a return grid of the ventilation system, so that all the pieces of nails that you cut off get immediately attracted, sucked towards the grid, kind of like this. There you go. And then when you're done, of course, you want to have a vacuum cleaner handy so that you can clean after yourself. And to wash your hair, we have a special no-rinse shampoo that requires theoretically no rinsing, but at least very little rinsing. So we just squirt water into our hair, we add some shampoo, we massage it just like we would on Earth, and then we kind of dry the excess water and shampoo off with a towel, and off we go.
Today we're going to look at one of the coolest parts of having experiments on the space station. It's because we can separate one of the most dominant forces, gravity, on a lot of different models. A great example is water. water is pretty much dominated by gravity on Earth, but there's other forces at work that if we understand better, we can have a better model and make greater discoveries. Things like surface tension, capillary action. I'm going to show you today by taking this wonderful bottle, repurposed from a condiment, and blowing into it. When I displace the fluid with air, it will come up the straw and cover my face.
Spiders. There's one in here and one in here. We might actually let some fruit flies in there to be their food, and I think it's going to be hard to see. Let's see. Got my flashlight. But right here in the corner, one of them, Esmeralda. Let's see. Move your focus back to that's auto. Esmeralda is already out. Can you see? Yeah?
Right there.
Yeah, I know. Yep.
Station Houston, spacecraft 2 for the
Right there.
GLA. Our safety is complete to go to perform 1.2.404 steps. I'm sorry, correction, 1.2.402 steps 2 and 3.
Just need some leverage. So, ready to understand how spiders spin webs in space. It'll be great. Welcome. Thanks so much for talking to me. And Katie, I wonder if I could start with you. I gather that you have brought music with you to the International Space Station. I wanted to ask you what you have with you. Well, I play the flute on the ground, and it's one of the things I love to do, so I brought my own flute with me, but I also brought some other flutes with me. I have a penny whistle from Paddy Maloney of the Chieftains, and also a very old Irish flute from Matt Malloy of the Chieftains, and I have a flute from Ian Anderson of Jethro Tull. So a pretty well-rounded spectrum, and I am having a great time up here with them. Oh, that's amazing. Now, how did it come to be that you have those three flutes with you? Well, so with mine, it makes 4 total, and we get to bring a certain number of things with us to represent, or we just get a certain amount of space to bring stuff. And, you know, one of the things I think that's important to do is to try to share how amazing it is up here and, you know, relate to different groups of people. And I relate to flute players, and I just wanted them to understand what a cool place it was and how many possibilities there were to play music up here on the space station. I'm not sure which flute you have there with you, but you have a flute with you. Why don't you tell us which one it is, and I wonder if you would play us out with a song. Well, I'm from Massachusetts, and I brought my own flute, which was made by a really neat company in Massachusetts. And the song I was going to play is called Blue Nose. It's by a Canadian guy named Stan Rogers, who writes a lot of the things that I love to play. And it's about, you know, an old sailing ship sailing the oceans, being away from home. And that's the kind of perspective you can't help but have when you're up here looking down at the Earth and you think about the early explorers. And here we are, more recent explorers, but we all have some things in common. And there are jobs that we have to do far from home. So this is for John McBride, who in our International Space Station branch in the astronaut office is the cornerstone of our branch, and it's his favorite song. Great. Katie Coleman, a little flute music from space. Thank you so much.
Hi, this is Scott Kelly aboard the International Space Station. I wanted to do a little demonstration of these paddles. They're called hydrophobic paddles, and they repel water, kind of like a raincoat. But up here on the space station, they allow you to play ping pong with a ball of water, and it's pretty cool. Neat stuff. This is going to be putting the space away.
Very nice.
Hello everyone, I'm going to show you how to make a peanut butter and jelly sandwich from the International Space Station. Every time we eat, it's kind of fun. Everything will float around if you don't manage it. So we have some tape to stick things on our table here, as well as a bunch of Velcro. All right, so the first thing we need for our sandwich is a piece of bread. Well, up here we don't have bread like you do on Earth, but we have tortillas. So we use tortillas a lot for sandwiches. So that's what I'm going to use for my peanut butter and jelly. I'm going to stick that down to some tape here so it doesn't go floating away while I'm getting everything else ready. So I'll get my peanut butter out, and even the lids on the peanut butter have a piece of Velcro on it so they don't go floating away. If I let it go, it'll kind of just float there for a little while, and then eventually the air conditioning system in here will take it away somewhere else. So I don't want to lose it, so I'm going to stick it on the table. I'll scoop out some peanut butter for my sandwich. I got to stick this somewhere, otherwise it just goes floating away too. But just for now, if it's just a few seconds like this, I can just leave it and let it float. I'll spread the peanut butter on my sandwich, onto the tortilla. And then I'll get my jelly ready. See, a lot of things you got to think about and manage while you're eating up here. And you just spread the jelly on the sandwich. That as well needs to get attached to the table. So there's my peanut butter and jelly tortilla or sandwich. From up here, I'll just kind of close it up and enjoy. See if you guys can enjoy it as it's coming to you.
I'm going to go out on a limb here and give the full-on Luca Parmitano look for the hatch opening ceremony. So please join me to Chris's barbershop. Okay, so here's how we cut hair in space. We have your standard hair trimmer, but the hair would go all over the place. So we need to connect it to our vacuum cleaner, which is right here. And now we're ready to cut hair. So far. Should I stop here? I don't think so. Here's your last look at the mohawk. It's coming off. I don't think I've looked like this since Plebe Summer. That's pretty going on, but it's not quite the full Parmitano look. That's completely smooth on the top, so I still have one more step to do. I wonder if he does this every day. It kind of hurts. Go. The full-on Luca Parmitano, ready for my new crewmates. So thanks for coming to Chris's Barbershop. Next up is docking of my new crewmates.
Hi, welcome to the International Space Station. As all of my family and friends know, I love to run when I'm on Earth. Luckily, we have the capability to run here on the space station too. In fact, it's one of the 3 exercises that we do on a daily basis to help keep our hearts and our bones and our muscles strong while we're here without the gravity pull of Earth affecting our body every single day. So let me show you how we do it here. This is our treadmill. It's called T2. It's located in Node 3 on the International Space Station. You'll notice that the treadmill can move. It's on a vibration isolation system like all of our exercise equipment is. And the reason is because there are a lot of loads when we run on a treadmill, and we really don't want to impart those loads onto the space station. So we have all of our exercise equipment on vibration isolation system. Obviously in space we need something to keep us on the ground when we're running. What we use is a harness, which is very much like a backpacking harness, and the straps are adjusted so that the load is evenly distributed between your shoulders and your hips, just as if you were backpacking. We attach, by these rings, the harness to a system of hooks and bungee cord. You can see there's some stretch in the bungee cord, and then we can adjust and change the number of hooks that we use. Today I'm going to use 4 hooks. If I were to use 3 hooks, it would provide a little more load. If I used 5 hooks, it would be a little less load. And then in that way we can adjust the amount of load on our body as we're running. The T2 is controlled by our laptop here in front of the treadmill. And once I'm all strapped in, I can go ahead and select a protocol. Our trainers on the ground get protocols designed for us that we can use. I'll load the protocol. This is an interval protocol that I can do. And now you can see that there's a target load. The target that my trainers wanted me to reach was a 100-pound load. There are load cells in the treadmill, and that's how it's determining. And you can see with the 4 hooks that I put on, it's pretty close to what the target load is. Click OK, and then I'm ready to run. You can see we also have heart rate on display. We wear heart rate monitors. And once I push start, the treadmill belt will start moving, and I'll just follow the protocol. That was a great run. Not quite the same as being out in the fresh air with the wind in your face, but a nice alternative. Hi there. I've had a lot of people ask me how I wash my hair in space, and I thought I'd show you how I do it. Let's see. To get started, these are the things I need. A bag of warm water, a little no-rinse shampoo, towel, and my comb. What I like to do is start by just putting some hot water, squirting it onto my scalp, and I have a mirror here so I can kind of watch what I'm doing. Sometimes the water gets away from you, and you try and catch as much as you can. Then I just work the water up through to the ends of my hair. And I take my no-rinse shampoo and squirt it also on the scalp, just a little bit, and rub it in. Again, kind of working it out to the ends. And sometimes I'll actually take my comb to help work it all the way to the ends. And I like to take my towel while I have the shampoo in there and just kind of work it. Because without standing under running water, you kind of need to use the towel a little bit to help get some of the dirt out. I like to follow that by a little more water. It's called no-rinse shampoo, but I think it's best if you use a little water with it. It actually feels kind of squeaky clean right now. Now I'll take the dry part of my towel. We use towels for quite a while here, since we have limited supplies. We use them wisely. There, I think that's pretty good. And now as my hair dries, as the water evaporates from my hair, it will become humidity in the air, and then our air conditioning system will collect that into condensate, and it won't be long, and our water processing system will turn that into drinking water. At the end, I just do one final comb through to make sure there are no snarls and snags. And while it dries, I like to let it stay free. I don't put it back in a ponytail while it's drying. And that is how I wash my hair in space on the International Space Station.
0 and liftoff of Space Shuttle Atlantis on a mission to build, resupply.
Hello, I'm Sunny Williams. I'm up here on the International Space Station. So this is Node 2. This is a really cool module. Of course, most of these modules you'll see they have 4 sides, and they're put together. That way we could sort of work on a flat plane, either a wall, a floor, another wall, or the ceiling. But you know, again, all you have to do is turn yourself and your reference changes. The reason I'm bringing that up is because this is where 4 out of 6 of us sleep. And so people always ask about sleeping in space. Do you lie down? Are you in a bed? Not really, because it doesn't matter. You don't really have the sensation of lying down. You just sit in your sleeping bag. So here's one sleep station right here. I'm going in right now. You can follow me if you want. So I'm inside. It's sort of like a little phone booth, but it's pretty comfy. I've got a sleeping bag right here that we sleep in, so we don't have sort of like a little bit of a cover. We don't fly all over the place. But you know, you can sleep in any orientation. I have it sleeping, feeling like I'm standing up right now, but like you saw, I'm on the floor. But it doesn't matter if I turn over and I sleep upside down. I don't have any sensation in my head that tells me that I'm upside down, so it really doesn't matter. The sleep station is also like a little office. We've got a computer in here. As you can see, we've got a couple little toys. I've got some books. I've got some clothes and other things that make it sort of like home. I'm coming out. And just for reference, that's one sleep station. This one's another, right here. There's one on the ceiling, if you want to call it, right here. And then there's a 4th on the other wall over here. So all of us sleep in a little bit of a circle. All right, come on back. There's more to show you. I know that there's some questions about how to use the bathroom and how do you actually live in space like normal, like at home. I mentioned real quickly about getting up in the morning and brushing your teeth and washing your face. Well, how do you do that? Well, here is the bathroom, essentially. You get up in the morning and we have a little kit, and it has all the essential things that you need, like your toothbrush and toothpaste and brush. See how much better the brush makes my hair look? I'm just joking. It still stands up straight. It doesn't matter where you are. It's always going to stand up straight while you're up in space. A lot of people ask about toothbrush and toothpaste. So, luckily enough, toothpaste, you can do it upside right this way, is sticky, and so it sticks to your toothbrush, no problem. Another cool thing is that water sticks to your toothbrush too. If you can see it, I'll have some water come out. The water is pretty neat up in space. It'll stick to your toothbrush and it will make a big bubble. And that's just by surface tension. And then you can drink it. So a lot of people ask about what do you do with the toothpaste after you brush your teeth. Two options. Swallow it, and it's sort of like mouthwash, but it tastes a little gross. Or you can just spit it out in a paper towel, and then you don't have to worry about it. Swallowing thing I wouldn't recommend at home. I'm only up here for 4 months, so it's not that bad. One of the most pressing questions about living in space, of course, is the bathroom. So let's take a look at that little piece of work. Come on in. Here we are at the throne. This is awesome. You might see the little, you might have noticed the little moon on the outside. This is our orbital outhouse right here. And of course, it serves for two functions. Number 2, right here. I'll show you. But you see it's pretty small, so you have to have pretty good aim, and you be ready to make sure things get let go the right direction. And it smells a little bit, so I'm closing it up. And that's of course for number 2. And this guy right here is for number 1. So they're sort of two slightly separate functions, but you can do a little, essentially both, by hanging on right here and doing number 1 and number 2. I might add it's color coded, so you really don't get it mixed up, which is nice. This is yellows for number 1. And also there's a selection of paper. People always ask about toilet paper. What do you do with toilet paper? What kind of toilet paper do you have? We have gloves, just because sometimes it does get messy. We have some Russian wipes, which are a little bit coarse if you like the coarse type of toilet paper. We have some nice tissues, which are nice and soft if you like soft toilet paper. We have Huggies, just for any cleanup. You know, we were all babies once, and this sort of helps. And then if things get really out of control, we have disinfectant wipes, just to make sure we clean up here. Because, you know, just like the water I showed you, the number 1 stuff can sort of go all over the place if you don't aim correctly. And did I mention both of these have a little bit of suction, so they should keep things going in the right direction. But like I said, sometimes things get a little out of control if you are out of control yourself flying around. So we have lots of protective stuff. And of course, you do have your privacy. There's a little door, so other people know that you're in there. Here's a pretty cool place. This is sort of like in your house where everybody meets in the morning. After you wash your face, brush your teeth, you want to find something for breakfast. And this is our kitchen. You might notice there's all sorts of foods here. It's like opening the refrigerator. You got all your different stuff that you want to have: drinks, meats, eggs, vegetables, cereals, bread, snacks. And that's a good place. That's where you find all the candy. Side dishes, and then some little power bars just in case. So we have all this type of food. Some of it is dehydrated, and so we have to hydrate it, fill it up with water. Some of it is all ready made, and then all we have to do is heat it up. So something like this, I'm pulling out barbecued beef brisket. Pretty yummy. Not only is this food made in the U.S., but we also have food here from Japan. We've got Russian food. As you can see, all these red containers are filled with food that's from Russia. And then we get some of our specialty stuff, some things that we like, some of our favorite stuff that your family can send up. In fact, I like fluffernutters, and so I got sent up some fluff so I could make my fluffernutter with peanut butter. So you have a lot of food up here, no problems. Now, I want to say where we are. So right now, we're in the Japanese laboratory. It's one laboratory out of many here on the International Space Station. It's actually on the left-hand side. If I was the International Space Station and I was flying through space like this, my left hand would be where the Japanese laboratory is. So now again, we're on the right-hand side, all the way on the right of the International Space Station. This is Columbus, the European module. It has science experiments all over. You could see it looks a little bit crowded. And here we do a lot of our medical experiments. Here we are in the U.S. laboratory. Again, this is a laboratory with science experiments on all of the walls here, all sorts of stuff that we do. And one of the things we also do is we exercise. We have some exercise equipment on board the space station. We need to do that because we lose bone density and muscle mass while we're up here, and that's a result of not having to fight against gravity. So how we keep ourselves in shape are with a bike, a treadmill, and a weightlifting machine. This is the bike. You notice the clip pedals. So all you need to do is actually clip your feet in, and then you can start pedaling. You don't need a seat because you don't sit down. Actually, I haven't sat down for 6 months now, so you don't need any type of seat. Just make sure you're held in with your pedals. You probably see that the bike bounces around a little bit. As I move it, it's not steady and held to the wall firmly. And the reason for that is the space station is pretty big. You saw that there's also solar arrays on the space station. If we start putting any forces into the space station, it's going to make those solar arrays bounce around a little bit. So to prevent that, the machines bounce around a little bit, move around a little bit, and that way we don't put any forces onto the structure of the spacecraft out to the solar arrays. All right, a little farther on. Come on. I'm here with my two buddies in the airlock. Actually, these are two spacesuits that are ready, primed up to go outside, as we call it, to go do a spacewalk in case we have to do anything outside. Some of the things we do outside are just like inside, repairs. We have a lot of electrical boxes and machinery and solar arrays, in fact, that I talked about earlier, that are outside, and sometimes they don't work quite right. Remember, space is really cold and really hot, and it's also the vacuum of space with no pressure, and so some of the equipment doesn't work well all the time. So we might have to go out and do a spacewalk. Right behind me is actually the hatch that you go out into space, and right now we have it filled up with a couple other spacesuits because we've got 4 of them up here and some of our tools. But right behind here is the hatch in which you actually go right outside into the vacuum of space. The spacesuit is pretty big, as you can see. It's like being a football player. Part of the reason it's so big and bulky is because of this backside, this backpack. It's like going on a hike with a backpack, but the backpack and the suit weighs about 300 pounds. Luckily in space, nothing really weighs anything, so you don't feel that it's so heavy. But we need to have such a big suit because that guy back there is essentially the heart of the spacecraft. I call this actually a spacecraft. It has all the oxygen for you. It has all the carbon dioxide removal system for you. It also has a heating and cooling system to make sure to regulate our body temperatures while we're outside. It also has a computer, so it tells you on a display here if there's anything that's going wrong with the suit, if we're running out of oxygen, if we have too much carbon dioxide, or any type of electrical problem. So it's a pretty awesome little spacecraft, and actually got to go out, use my little spacecraft a couple times, and it worked like a charm. Lucky that it works very nice. You might want to see what the helmet looks like. It's pretty cool too. We don't usually go out like this, so you usually can see when the helmet's open. So you can see what it looks like inside. Somebody's little head would be inside of here. So you can see, you can turn your head all the way around while you're inside of there, but the helmet stays still. So that's determines how far you could see. And it's usually pretty sunny out there, so we have to wear our sunglasses, and this is our sunglasses right here, which make you look pretty cool. It's like a glass-bottom boat. This is the cupola. It sticks down below the space station. It's one of those places you find yourself hanging out in all the time because all you want to do is look back at our planet. I think some questions I had were about what do you do in your free time? And you can't help but want to just come to the cupola and look outside as much as you can. And a lot of folks, I play this game with myself about where we're flying over the Earth. Try to come in here and just guess. After being here for a little while, you can sort of figure it out. You can tell different cloud types over different continents. You can tell different soil types over different continents. So let's see. And then, of course, there's a lot of ocean. So usually we're over the ocean at first glance. I will tell you in just a moment where we are. What? There we go. So right now we are right over Africa. It's a little bit cloudy, as you can tell. But we're right over the continent of Africa. Hey, what's that? I think that's a Soyuz spacecraft. That's the spacecraft that's taken us home to planet Earth today. Oh my gosh. We might have to go take a look at that. That's pretty cool. It's a little bit smaller than the rest of the spacecraft, the space station, so you'll see if we go there, it'll be a little bit more cramped. But we're going, you can look all the way back to the back of the spacecraft, which is where the Russian segment is. And then you could look all the way forward to the front of the spacecraft, where the Japanese laboratory, the European laboratory, and the American laboratory are. And then back to the solar arrays where we started in this morning when we were looking out the Japanese window. So other questions that were here are, what would you recommend as a job, and to what type of person would want to be an astronaut? I think people who would like to explore, of course people who like math and science, that's what this is all about. We have people in the office who are doctors, teachers, veterinarians, engineers, pilots, so all sorts of people become astronauts, and I think if you see it's just sort of cool, so I think people who like to do a little adventure and like to do cool stuff probably usually become astronauts. Hey, one thing I didn't show you, or I talked about but I didn't show you, was the exercise, another piece of exercise device, which is the advanced resistive exercise, and that's what this is right here. This is ARED. And you could probably see this bar. Let me just do a little bit of maneuvering here. Stand by. We have to set it up just like at any other gym. Hold on. Show you how this works. So you can see you can change your attitude just by going from one module to the next, going up from the cupola down here. This is what we call the ARED. And with this, you can lift weights based on vacuum in these cylinders, just like you do at home at a gym. For example, if I wanted to do a squat, I could do it like this. Oops. I should need some weight on this thing. I'm not lifting with anything, so it's too easy. One of the cool things you could do things that you can't do at home. For example, single leg squats with just one leg, because the other leg, you won't fall over So all sorts of stuff. You can also do bench press. We have a bench that we could add on here, so you can work on your beach muscles. Hey, Aki, what are you doing down there?
Crashing things.
This is one of the cool things about space, too. It sort of looks like there's a big old hole here, but you don't even think twice about it. You could just jump over the hole. Or, if you want, you can go jump into the hole. I'm coming down. Woo! Then you can come right back up again, like Superman. Woo! We're lucky we have a really cool big space station that you can fly around in. That's actually called the PMM. You might have saw it out the window. It's a big silver canister. What's really great about that is it's essentially our closet in our pantry, or whatever you want to call it. We have extra food down there, we have extra clothes, we actually throw the trash out down there. So it's nice and organized, and we have all of our stuff that we need while we're working in all these other modules all stowed in this location down here. And it's a lot of fun to play in. So we're going into the Russian segment. Be ready. You don't need a passport either. It goes a lot farther back than this. We'll go take a trip and say hello to the boys down there in just a minute. Well, let's do that first, actually, and then we'll go down to the Soyuz at the very end. This is Yevgeny. Hi. Doing a little tour. This is the FGB, and what's cool about this module, it is actually the very first piece of the space station that came up in 1998. The space station has been around for about now, manned for 12 years, but it's been up in space for about 14 years. And this was the very first. It is like the Russians' PMM. It has a lot of storage, as you can see. Можно? Снимаем. Чуть-чуть. So here we are in the heart of the space station, really. This is the service module. This is the central post. In case we had any problems, I know a couple of the questions were about what type of things do you have to worry about. And some of the things we have to worry about in space are fire. If we had a fire, if we had a depressurization, like we were hit by a micrometeorite and it made a hole, or if we had some type of toxic atmosphere. We use ammonia for our radiator, so there is a possibility that ammonia could come into the vehicle, and then it would be bad for all of us. If we have any of those problems, we come right here, which we call the central post. It is the main heart of the space station. It was also the first computers that came up here that ran the space station, and so behind this wall right here are these main computers. So we gather here as a group of 3 or 6 and then figure out how we're going to either fight the fire, patch the hole, or solve the toxic spill. And what's cool about this module, of course, it's the central post. It also has great windows right down toward Earth. It has controls to fly in visiting spacecraft if they need some assistance right here. It has Russian computers as well as American computers to help us control anything we need to on the space station. It's a couple of our crewmates back there, Oleg Novinsky on the right and Yuri Malenchenko on the left. And there's also a second bathroom here, which is really cool because 6 of us going to one bathroom is really tough. And so there's one bathroom here and one bathroom on the other side where I showed you. And you can probably see on the wall behind Oleg and Yuri some of the heroes of the space program. Korolev, Sergei Korolev, who was a chief designer of putting men into space, and of course on the right-hand side, Yuri Gagarin, the first man to go into space. So just reminds us of our roots. Yuri, what are you doing? Что делать?
Coffee.
Making coffee?
Yes.
Oh.
Black.
Black coffee.
Yeah.
Looks good. Okay. Spasiba. We're going to check out our Soyuz real quick. Make sure it's ready to go. All right, back to the Soyuz. I'm gonna stop here just for a quick second. You can see on the Russian spacecraft there's also other modules that stick out, down, and above. Right here is, let's see, I'm trying to be oriented. That's a place where we do spacewalks from for the Russian side. There's Russian spacesuits in here, and also a visiting vehicle which brought fruits and vegetables and becomes a trash container when we undock. Up on this side is also a future place where they're going to do spacewalks from, and connected to it is Kevin's, Oleg's, and Yevgeny's Soyuz spacecraft. And now let's go see ours. Whoa. Извините.
No problem.
Это пробка. Coming down. It's a little tricky getting in here. This is the docking probe right here, this big thing. This helps us connect to the spacecraft. This probe actually sticks into this cone, and that's how the spacecraft, our Soyuz, becomes connected to the ISS initially. That is then replaced by clamps, which are around here, that will allow the two spacecraft to be stuck together. And then you can remove the probe and the cone. You okay? All right, so here we are in the Soyuz. This is what we call the BEO, the living compartment, Bitovoy Otsek in Russian. It also has a little bathroom. It's not as good as the other bathrooms, so we try not to use it too much. It has drinking water in it if we need something to drink. And then, of course, it's filled up with a lot of cargo for us. Bringing up and also bringing back down. It has a second purpose when it comes back to Earth. It serves as a garbage container. During the descent, we'll get rid of this area right here, and everything that's in it will just burn up as it's coming into the atmosphere, so that way we can get rid of a little bit of trash. But the main area where we were on launch and where we're going to be on descent is down here, because we're not part of the trash, so we're in a safe place. So we're in the descent module, SA. It's a little small, but you can get in. Not sure how well you could see in here. Hold on for a second. I'm going to turn it up this way, just so you could see the hatch and you could see Kevin. It's a little bit small, but we'll come in and show you around. You coming in?
Probably not.
Okay. Got to move a couple things. We were just starting to get ready. We're preparing a couple days ago for our ride home. It's a little bit squishy, but everybody asks, how do you sit in the Soyuz? And you sort of sit in your seat like this. The seat is molded to your body, and so you can just sort of squish in here and be pretty relaxed. Everybody has a handmade seat for them. And then, of course, there's a control panel, and that's where we do most of our actions and work right here. There's hand controllers, which you can fly the vehicle with, and there's a stick right here, primarily used for communications when we're trying to talk to the ground. So 3 of us fit in here. Like I said, it's a little squishy, but somehow it seems like we all managed to get in here and fit pretty well, and it's a pretty safe ride home. You're probably wondering, what's all this junk behind us? Well, it's all of our parachute, first of all, and then it's all of our survival gear, just in case we end up landing in some strange place on the planet and nobody's there to rescue us right away. We have all sorts of survival gear with us, keeping us safe in here. So they've pretty much thought of everything, and we'll be home on the planet within the next 12 hours.
Anyone who's seen Gravity has had a tiny little taste of what life is like several hundred miles above the surface of the Earth. But while we were trying to experience it vicariously via Sandra Bullock's 3D eyes against a green screen, a tiny handful of people truly know what it feels like to be in space. We are joined now, incredibly, by 3 astronauts who are currently on board the International Space Station. They are Koichi Wakata, Mike Hopkins, and Rick Mastracchio. Can you just tell us physically where the space station is currently located? Where on the planet would I have to be to gaze at the sky and know that I'm looking up at you guys?
You know, that's a great question, and I have to admit I don't know. I had to look at the map right before we started here, but there's a good chance we're over the Pacific Ocean, because that's where seems like we spend a lot of time.
Yeah, it comprises a large portion of the Earth's surface, right? And where are you guys actually located on the station? It looks like you're just floating around in midair. Where are you, and what are you doing?
Yeah, we're actually in the U.S. laboratory, and so this is kind of the primary portion of the USOS segment. And so this is where we do a lot of experiments, but it's also where a lot of the systems are located that help keep us alive.
Well, we're doing quite a bit of studies related to how our bodies change in zero-G. For example, we do ultrasounds. We're all basically trained to do ultrasounds with ground guidance, ultrasounds on our eyeballs, ultrasounds on our spines, on our heart, different things like that. And we're also, of course, we're constantly doing blood draws and urine samples to see how our bodies change and are affected by the zero-G environment.
Is this to study the impact on your health of potentially much longer trips in space? Is that the point?
Exactly. You know, right now, most of our missions are about 6 months long. Pretty soon, we're going to have one-year missions. I believe I think next year, we'll start a one-year mission for an astronaut. And then eventually, we may even go longer and longer. And this is so we can see how the body is affected by the weightlessness and the environment of space, and also how we can protect the crew members, how we could keep them healthy for these long-duration missions that it's going to take to get to Mars and beyond.
How do you stay healthy in zero Gs?
Yeah, we have a pretty extensive exercise program using aerobic machine, a bicycle machine, and treadmill, as well as a resistive exercise device. We exercise almost 2 hours every day to stay healthy.
My boss, Ariana Huffington, likes to put an emphasis on defining success beyond just money and power, and thinking really bringing wonder back into our lives. Has being in space given you a fresh sense of wonder?
Oh, absolutely. There's not a day that doesn't go by when we have a chance to look out the windows down at the Earth that we don't see something just truly incredible. In fact, the other night, Rick and I he just happened to be in the cupola. It was night, and we were going down near Antarctica, and the northern lights were just absolutely incredible. It was a scene that we've never seen before. The whole sky was lit up green, and you had blues of the horizon where the sun was just over the horizon. And then we had Venus come up and the moon come up, and it was just truly amazing.
What does that do to your head?
Well, it kind of blows you away. You're just in awe at how beautiful the Earth is, and you're just every day, again, you're surprised at some of the sights that you see.
We live in an age where people have made the claim, especially secularists have made the claim, that you can't trust the Bible because science has somehow disproved it. And one of the areas where that is very prominent is in the area of astronomy. And I got to tell you, you'll even find this in the textbooks that students use at most public schools that are government funded. People like to think public schools are neutral, but for the most part, there's an anti-God agenda there. And I don't mean to offend anyone. Those of you that are maybe teachers in public schools and are Christians, praise God, you're a missionary in a system that I consider to be very pagan, is what it comes down to. But in any case, when you go to these schools and you pick up a science textbook, let's say an astronomy textbook, you're going to get a combination of things. You're going to get some good science in there, no doubt about that. You're going to learn about planets and their composition and so on. And you're also going to get a story, a secular story about how these things came about, how the worlds were created and so on. And it's a very anti-God story. A big bang exploded billions of years ago, and then accidentally planets sort of coalesced from the debris and so on and so forth. And then on one of these planets, chemicals just happened to come together and made the first life forms. It's all just an accident. Well, that's not the science, right? That's not evidence. That's a story. And the secularist strategy is very clever by mixing science, which we should respect, because science, when it's done properly, it points to God. It reflects His character. But they've taken science, which is good, and they've merged it with their belief in evolution and secularism, their belief system, to try and get you to believe in their belief system. That's pretty clever, isn't it? And a lot of people have bought the lie, hook, line, and sinker. They've been baited in on the science, which is good, and they've swallowed the story, which is not really good science at all. And that's the topic I want to address tonight, particularly in the realm of astronomy, which is my specialty field. Because you see, astronomy really reveals creation. And we're going to see how the secrets of the cosmos confirm what the Bible teaches. That's my goal this evening. And we're going to look at 5 secrets of the cosmos that confirm biblical creation. We're going to see that the universe reveals God's glory as the Bible teaches, so the Bible certainly got that right. We're going to see that the Bible is right when it speaks to the basics of astronomy. Did you know the Bible does have some astronomy in it? That's not its primary purpose, but when it touches on astronomy, God gets it exactly right, as of course He would have to, since He's God. And so when He touches on the basics of astronomy, things you would learn in any freshman level astronomy class, God got it exactly right. We're going to see that the Bible's right when it touches on the age of the universe. And of course the secularists have a very different age for the universe than what the Bible teaches, but we're going to see the science lines up with what the Bible teaches. It really does. We're going to see the Bible is right about the uniqueness of the earth. Earth is not just another planet out there. I mean, it is a planet, but it's not the sort of run-of-the-mill planet that secularists would like to believe. Earth is very special in God's eyes. And then finally, the Bible is right about starlight, and we're going to talk about how God got the light from those galaxies to Earth in the biblical timescale. So we're going to start with the glory of God being revealed in the universe. That's one of the purposes that God had in mind when He created this vast universe. It was designed to declare His glory, and the implication is to us. So we're to look, when we look out in the night sky, we see God's glory revealed. That's something we'd expect based on Psalm 19:1. The heavens declare the glory of God. The skies proclaim the work of His hands. And I think there are many different ways in which the universe declares God's glory, but I'm just going to focus on 2 this evening. We're going to see how the size of the universe declares God's glory, and the beauty of the universe declares God's glory. The size of the universe is immense and incomprehensible, but I'll at least give you some sort of feel for it so you have just at least a smidgen of the experience. And then the beauty, well, you don't have to be a PhD in astrophysics to appreciate the beauty of the universe. It really is stunning. In fact, you can go outside on a clear night if you get away from the light pollution, and it's really stunning to see what the Lord has created. And as we have, with technology, explored these issues even further with things like the Hubble Space Telescope, we've revealed a level of design that our ancestors probably couldn't have imagined. So it's really hard to get a feel for the size of the universe, but let's start with the moon. Now, the moon was one of the smallest things we're going to look at. The moon's about the size of the United States. If you were to put the United States up at the same distance as the moon, it would cover about the same area, roughly. And the moon has its own beauty to it. It's kind of a desolate beauty, but it is beautiful. It's fun to look at in a telescope. This is actually a mosaic image of the moon taken with a high-resolution spacecraft that's orbiting the moon. And of course, when we look at the moon with telescope, it's fun to see people's reaction as they look at it. You know, it's wow, it's magnificent. And sometimes people will say, well, can you see the flag, you know, that the astronauts planted? And no. When you consider that's the size of the United States, you're not going to see something that small on its surface. But thanks to spacecraft that are orbiting the moon and taking high-resolution pictures, we can actually see the places where the astronauts landed. And I want to show you one of these. This is absolutely amazing that we can do this. But in Mare Tranquillitatis, which is where the first Apollo landing was, as we zoom in and get increasing resolution, you can actually see the little bit of the lunar lander there that was left. Remember when they launched, they left the lower portion of the lander, like that spider-like looking structure, right, with the legs and so on, to save fuel. They just left the top portion. And so you can see the bottom portion, it's still there. And those little dark streaks that go off to the right and then come back, those are the footprints of the astronauts as they walked along the surface there over that crater. So 40-year-old footprints, and they're not going to go anywhere because there's no weather on the moon, so they'll be there for quite some time. And there's no maid service, so nobody's going to come and sweep up the footprints either. So that's the way it's going to remain. So isn't that amazing? We can actually see that. And of course, we can see that at the other Apollo landing sites as well. And so for those of you that think that we never landed on the moon because you read something on the internet, well, don't worry about it. Well, the scale of the cosmos is as amazing as its beauty. So again, we'll start with the moon, and it looks fantastic when it's in that first quarter phase, when it's illuminated right down the middle. You can really see the craters there very well in a small telescope. That's my favorite phase to look at the moon. It looks so three-dimensional. Your brain is able to figure out from the shadows of the craters that you're looking at a sphere. It's really neat. When the moon's full, you can't tell. It looks flat as a dime. But when it's in that first quarter phase, you can tell it's spherical. Here's the moon compared to the Earth at their true scale. And so it just kind of gives you a feel for the things that we're going to see in the universe. Now, the Earth, it may seem pretty big, but it's small compared to, for example, Saturn. Saturn is about 9 Earths across. That's just the planet. The rings extend even further out. The rings are trillions of tiny little moons that orbit Saturn's equator. And wow. And of course, astronomy is really a lesson in perspective, because when you see Saturn in a telescope, it looks tiny. I mean, you can see the rings, it's beautiful, but it looks like this tiny little gem that you just want to grab it and stick it in your pocket and take it home with you. But you can't, because it's 9 times the size of the Earth. Saturn's small potatoes compared to the sun. The sun is about 100 Earths across. And so at this scale, you can just barely see the Earth at this point. The sun is basically a stable hydrogen bomb. It's powered by nuclear fusion of hydrogen in the core, and that's a very efficient power source. God really knew what he was doing when he made the sun. And of course, he placed the Earth at the right distance to receive the proper amounts of heat and light. And Isaac Newton argued that doesn't happen by chance. That's the result of the mind of God. The sun is actually a star. And maybe you know that, because you'd say, well, that's common knowledge these days. But to the ancients, that was kind of amazing to think that those little pinpricks of light that you see out in the night sky are the same type of thing as the sun. It's just the sun is much closer than these other stars. The sun is what we call a main sequence star. And basically that main sequence star is a star that obeys a rule that if you know the mass of the star, you know everything else about it. You know its size, you know its color, you know its temperature, its luminosity, everything is determined just by the mass. And the sun obeys that rule, and most stars do, but there's a fraction that don't, and those are the giants and supergiants. But if you get red main sequence stars, they're a little smaller than the sun. Color means temperature, by the way. So the sun's kind of a medium temperature star, about 6,000 degrees at the surface. And then red dwarfs might drop down to 4,000, a chilly 4,000 degrees at the surface. And then the blue stars can get up to 20,000 degrees at the surface in Celsius or Kelvin. Now, some stars are quite bigger than the sun. Mintaka, for example, which is a blue supergiant, it's one of the stars of Orion's belt that you can see in the winter sky. And you can tell it's blue. You can see its blueness to the naked eye, and that tells you it's very bright. The brightest, hottest stars are blue stars. But there are stars that are even bigger than Mintaka. So again, the sun's 100 Earths across, and it's now basically invisible. We go even bigger stars like Canopus, which is visible in the low south in February. There's stars even bigger than Canopus, like, for example, Antares, which is over 600 suns across. And of course, the sun is 100 Earths across, so you multiply that out, and it's really, really big. Yeah. And of course, there are stars, that's about the maximum. Stars get maybe up to twice that big, and then there's a limit on how big you can make a star for physics reasons I won't go into. Some stars are kind of single, like the sun. Some come in binary pairs, and others come in these amazing clusters, like, for example, this M80, which is a globular star cluster. There are two types of clusters: open clusters, which have a few thousand stars, and then these globular clusters, which have perhaps 100,000 stars each. And there are several hundred of these globular clusters that belong to our galaxy and orbit sort of around its nucleus. And that's just one of them. Isn't that amazing? We can't even count the number of stars that we can estimate it at about 100,000. And it reminds me of that verse that says that God calls them all by their names. God has a name for each and every star, not just in that cluster, but in all clusters. Astonishing. Some of my favorite objects in the universe are not stars at all, but nebulae. A nebula is cloud, it's Latin for cloud, but it's not a cloud like in Earth's sky, which would be made of water vapor. These clouds are made of hydrogen and helium gas, which is the same stuff that stars are made of. But whereas stars are hydrogen and helium compact into a relatively small sphere, a nebula is hydrogen gas spread out over a vast region of space. And if there are stars nearby, they'll cause that gas to glow, and you get some very vivid and beautiful colors in these nebulae. It's quite stunning. They're a lot of fun to look at. And of course, my point here is that our solar system really would not show up on this image. We're at such a large scale now. And that's one of the larger nebulae. Now, not all nebulae are large. Some are small, and these small ones are called planetary nebulae. And that's an example of a planetary nebula. In that case, with a planetary nebula, you have a star in the middle, and it's ejecting gas out the poles, out the North and South Pole, and so you have a bipolar structure there. They call that a bipolar planetary nebula. And some planetary nebulae are round, but they all have a star in the middle, either one that's still active or one that's collapsed in on itself and become a white dwarf. And here's one of my favorites. This is the Ring Nebula. One of my favorites because it's the first that I got to see with my own eyes. And that was very exciting for me when I was quite young and was pointing my telescope out. And of course, it takes a little bit of practice to learn how to do that, but then you can find this little guy not too far away from the star Vega, a wonderful object in our summer night sky. So weird, because most places you point a telescope, you just see stars and stars and stars, and they're beautiful, but they're just stars. There's this one little magic spot where you will see a glowing smoke ring. And it is so strange to see this smoke ring just hanging there. You're expecting it to expand like you've seen smoke rings do on Earth. And of course it is expanding. It's just so big that we don't notice it in a human lifetime. But yeah, there's one little spot where you will find this little cosmic Cheerio suspended on nothing. Really rather remarkable. Now, all these things that we've looked at, all of these stars and nebulae and star clusters and so on, are in a much larger object called a galaxy. So we're in one of these galaxies, and for a long time, astronomers thought that our galaxy was the entire universe. But we now know that our galaxy is one of many. This is an example of a galaxy that's not too far away from ours. This is called the Whirlpool Galaxy, and you can see this in a small telescope, and it's quite spectacular. And if you get to really dark skies with a decent telescope, you can see those spiral arms there. If you have just a mediocre telescope, you'll see just the two bright cores, that one right there and that one right there. It looks like two galaxies that are in the process of collision. So really rather remarkable. But yeah, now we know that our galaxy is one of maybe 100 billion in the visible universe. And each one of these galaxies has perhaps 100 billion stars in it. So many that you can't see any of the individual stars. You have to zoom in on it to see those. There are all kinds of galaxies in the universe. There are galaxies of tremendous beauty. There are galaxies of tremendous ugliness. Yeah. There are galaxies that have large, mysterious arrows next to them. You'll see that in all the textbooks, always pointing to something interesting too. There are galaxies that have rings of stars surrounding them. Isn't that interesting? There are galaxies that look like flying saucers. That is a real galaxy. That's the Sombrero Galaxy. You can see why they call it that. And it's part of the Virgo supercluster, which is a cluster of galaxies, about 2,000 galaxies, relatively close to ours. And you can see that in a small telescope if you know right where to look. And I got a book on this that I'll tell you about later that'll show you if you want to learn how to find these things. It's a lot of fun. And you can see that dark dust lane there that blocks the light from the stars behind it. There are galaxies that are in the process of collision. Of course, the stars would all just pass by each other. It's not a problem because the distance between stars is enormous compared to the size of stars. So to suppose that any two stars would collide, it'd be like me throwing a sand grain at you and you throwing a sand grain at me and expecting them to collide. It's possible, but it's not very likely, not very likely at all. We now know that galaxies come in clusters. Here is a particular cluster of galaxies. Those are not stars that you're seeing. They're not individual stars. But each one of these little fuzzy spots is a collection of about 100 billion stars. Some less, some more. Amazing. As we go out even deeper into space, we see galaxy upon galaxy. That's not a star field. That's a galaxy field. Each one of those little specks, no matter how tiny they are, is a galaxy at distances that you can't imagine the distances that these things exist at. Truly remarkable. All made, all spoken into existence by God. He spoke, they leapt into existence. That's awesome. That's power. Think about the power that just our own sun puts out. Our sun puts out more energy in 1 second than 1 billion major cities could use in a year. That's one star. And there's 100 billion stars in our galaxy. And there's at least 100 billion galaxies. That's awesome. And I love the way the Bible describes the creation of all these hundreds of billions of galaxies with hundreds of billions of stars. Each, it's summed up in this little phrase, He made the stars also. Yeah. So it was just so easy for God to speak those into existence. And of course it was from His perspective, because He's God and His power is unlimited. Really remarkable. Certainly the universe declares God's glory. It's not what we'd expect if it was just a chance random explosion. It's got beauty in it. It's got design in it. It's got God's glory built into it. What about the basics of astronomy? Stuff that you would learn in any freshman level astronomy class. Well, the Bible got that right too. Now the interesting thing is some of these things that they will teach in a freshman level astronomy class are things that in the past secular experts would have said, no, the Bible's wrong. And yet today we would have to agree the Bible got it right. Let me show you some examples of these. The spherical nature of the earth. You know, some people have said, oh, you believe in creation, that's like believing in a flat earth. Well, they haven't read their Bible, because the Bible talks about the world being round, spherical, circular. The circle of the earth is mentioned in Isaiah 40:22. And you might think, well, that could be just a circular disc. It wouldn't have to be round. But I think the passage in Job, there's no way to interpret it any other way than that the world really is spherical. Because the passage there says that God inscribes a circle on the face of the waters at the boundary between light and darkness. And that boundary is what astronomers call the terminator. That's where light stops or terminates. And it's always a circle. And the only way that can be is if you're on a spherical world, especially with the water. It's always on the waters there, because the Earth's surface is mostly water. Now, the interesting thing I've found is that most astronomy textbooks will credit Pythagoras with being the first person to come up with the idea that the Earth might be round. Aristotle is considered the first to prove that the world is round from shadows of eclipses, and the fact that you can see the top part of the boat before you can see the bottom part of the boat when they're coming into shore, and so on. But that's Pythagoras is 500 BC, Aristotle's 300 BC. As far as I can tell, the Bible is discussing the spherical nature of the Earth long before the secular experts of the day figured it out. Isn't that interesting? It's almost as if the Hebrews had some kind of divine insight into this issue. And of course that doesn't surprise us, those of us who are Christians and take the Bible at its face value. By the way, the idea that Christopher Columbus was the first to prove that the world is round is a myth. Educated people already knew the world was round at the time of Columbus. He just thought it'd be faster to go that way, which it turns out it's not. So anyway, I'm glad he did though. I'm glad he made the trip. Anyway, Earth is suspended in space is something that the Bible teaches, that God hangs the earth upon nothing. A beautiful poetic description of the nature of gravity. What better way to say it than God hangs the earth on nothing? And of course that, we know that today. We've got pictures of the earth from space. We understand that. But it might have been hard to believe when it was written in 2000 BC. Even as late as 800 to 900 BC, the early Greeks were teaching that the earth was a flat disk that floated in water. And doesn't that make a lot more sense? I mean, we've seen things float in water, but have you ever seen something being hanged on nothing? That can't happen. I wonder if it was tempting for any of the Jews at that time to say, well, yes, I know the Bible teaches that God hangs the earth on nothing, but the best experts say it's a flat disk and floats in water. So maybe we need to reinterpret these passages. I don't know if that happened, but if they did believe that, they've got an egg on their face today, because the Bible was exactly right. God knew what he was talking about. The earth indeed is suspended in space. The expansion of the universe is something that I believe the Bible teaches. It says in a number of places, including Isaiah 40:22, that God stretches out the heavens as a curtain and spreads them out as a tent to dwell in, indicating that the universe has gotten bigger since the Lord first created it. He's stretched it out. And that, in fact, is something that we would now agree upon. It must have been hard to believe when it was written, though. And frankly, if you don't know much about astronomy, it might be hard to believe today. You go outside tonight and look at the night sky. It looks about the same size as it did last night, right? It's hard to believe it's being stretched out or expanded, but in fact it is. And what happened was in the 1920s, secular astronomers came along and confirmed that. Hubble and others were measuring redshifts of galaxies, which indicates sort of the way they're moving away from us. And they found that all galaxies sort of are moving away from all other galaxies, some exceptions that are very close. But generally, the universe is being stretched out or expanded, almost as if it were a tent being stretched out or expanded. How about that? And that's, of course, exactly what the Bible teaches. It's just the Bible got it right thousands of years earlier. It wasn't really until the 1920s that they figured it out. Up until the 1500s or so, most astronomers believed the universe was static and eternal, and therefore it couldn't be stretched out. And so this was really challenging to them. But the Bible's vindicated. The universe is apparently being stretched out like a curtain. Now, some people have said, well, does this mean that there was a Big Bang, right? Because if everything's expanding out like that, didn't the Big Bang predict that? Didn't the Big Bang predict that we should see evidence of expansion? The universe exploded into existence, and so everything ought to be moving away. Well, the answer is no. The Big Bang did not predict this. This effect of expansion was discovered in the late 1920s. The Big Bang idea, the idea that the universe came from a point that then, sort of expanded thereafter, is 1931. The guy who came up with the Big Bang already knew about the observational evidence of an expanding universe. And it wasn't until 1931 that it occurred to him that maybe we can run it all the way back to a point. But there's no reason to run it all the way back to a point, you see. But some people have said, well, does it at least count as evidence for the Big Bang, even if the Big Bang was invented after the fact to explain it? I mean, if everything's moving away from each other like that, doesn't that mean the universe exploded into existence 13.8 billion years ago? And the answer is no. Just because something's expanding doesn't mean it exploded into existence 13.8 billion years ago. Some of you are expanding a bit. That doesn't mean you exploded into existence 13.8 billion years ago. Not at all. It just means you're a little bigger now than you were some time ago. As far as I can tell, God made the universe with size, and He stretched it out a bit since creation. He doesn't tell us how much. There's no reason to think it came from a point just because it's getting bigger. That doesn't follow logically. Now, the next one I think is a little harder to, it's a little more abstract, but I do believe the Bible teaches a principle called conservation of energy and mass. That is, the amount of stuff in the universe is constant, the amount of energy or mass. Einstein tells us energy and mass are basically the same thing measured in two different ways. We'd expect this on the basis of Scripture because the Bible indicates that all things were made by Him, that is by God, by Christ in particular. And on the seventh day, God ended His work of creation. And so what that means is new stuff is not going to just pop into existence, because either it would mean that God is still creating, which cannot be because He ended His work by the seventh day, or it would mean that stuff can come into existence apart from God, which cannot be because all things were made by Him. So no new stuff's going to pop into existence. Furthermore, we would expect that stuff would not simply fade away and cease to exist, because God upholds all things by the word of His power, and in Him or by Him all things consist or hold together. So God maintains the existence of that which He created. Now He allows it to change. We can transform energy into different forms, but the amount of energy is constant. We'd expect that on the basis of Scripture. It's hard to pin down when secular scientists came to accept the idea of conservation of energy, but it's usually credited to James Joule. And from what I can tell, he was motivated by the Scriptures to believe that energy was conserved, and he found that in his experiments, indeed it is. But he's 1800s. And so again, the Bible got this right long before secular scientists came to agree with what the Bible teaches. I should add too, because some people say, well, does this mean that God can't do a miracle where He creates new stuff? Well, of course not. God can do what He wants. He's God. This is a general trend, okay? This is the general trend that we would expect to see. God can make an exception if He wants to. Uncountable stars. Abraham's descendants are described in the Bible as the stars of heaven and as the sand which is upon the seashore, a metaphor indicating a humanly uncountable number. In fact, in Hebrews it's mentioned that way. It says, which cannot be numbered for multitude, indicating by human beings. What a great analogy for an uncountable number. The stars of heaven, the sand which is upon the seashore. Of course, it might not have seemed like such a great analogy when it was first written, because the number of stars you can see with your naked eyes is a few thousand, 3,000, maybe 10,000 if you get really superb vision and you stay up all night and count all of them. But that's a big number, but it's countable. You could count to 10,000. It would be tedious, but you could do it. But then telescopes were invented in 1608, and by 1610, Galileo had made his own good one, and he started looking into the heavens, and that Milky Way that looks like a cloud in the night sky, that's actually hundreds of billions of stars, and there's no way you can count 100 billion stars. You could not do that in your lifetime. And so you see the number of stars just in our galaxy is humanly uncountable, and we now know that our galaxy is one of hundreds of billions of others. This is a great analogy. As a side note, there was I should tell you that even just a few hundred years ago, many astronomers believed that the number of stars in the universe was exactly 1,022. And you'd say, why would they believe that? Well, because the Greek astronomer Ptolemy had cataloged 1,022 stars. And although he never even claimed that his list was exhaustive, he certainly didn't intend it to be that way, there was a philosophy at the time that everything worth knowing had been discovered by the Greeks. And so if Ptolemy hadn't cataloged it, it wasn't there, despite the fact you can see more stars than that. It really is an example of how an incorrect philosophy can interfere with your understanding of the evidence, seeing something that's right before your eyes. So here's my question. Do you get the point? Have you learned the lesson of history? That's what I want to know. In the past, whenever the experts of the day have disagreed with the Bible has always turned out to be right. What about today? Have we learned that lesson of history? Have we learned that God's word is right, even if we don't understand all the evidence? God knows what he's talking about. Well, some people have learned that lesson, many haven't. And there are people today who say, but the Bible got this wrong, the age of the universe. We know that. We know the universe is billions of years old. The Bible indicates a much shorter age. But what I want to show you this evening is that the Bible got that right too. The evidence actually lines up with what the Bible says. The Bible's right about the age of the universe. Many lines of evidence confirm a universe that's thousands of years old. Does the Bible really teach a young universe? Well, it certainly does. It tells us that God created in 6 days. It's clear from context those are ordinary, approximately 24-hour days, because each one is defined in terms of an earth rotation. There was an evening and a morning, the first day, evening and morning, the second day, and so on. The universe beyond Earth is made on day 4. That would include the planets, the stars, the sun, and the moon. And that was we know that was a few thousand years ago because human beings are made on day 6, and from adding up those genealogies, we find it was something like 6,000 years ago. Can't put an exact date on it, but it would be something like that. Certainly wouldn't be millions or billions of years. And boy, that's something that secularists really hate. They don't want you to believe in 6,000 years because once you give up the billions of years, evolution doesn't have a chance. That's the primary motivation for believing in evolution. It's not because of scientific evidence. It's because of a philosophy of naturalism. You got to produce life without God because people don't want to believe in at least the biblical God. They want to make up a God they can control. And as a result, you need evolution. And to get evolution, you need billions of years because we all know it can't happen in a short period of time because we don't see it. That's really the motivation for this. But I want to show you that there's evidence that confirms the biblical time scale of thousands of years. And there's quite a lot of it. Jupiter, for example, Jupiter emits twice as much energy as it receives from the sun. Okay, so it's getting 1 unit, giving away 2, right? Takes 1 in, spends away 2. Or whatever it gets, it gives away twice as much, kind of like a federal government, right? Spending away twice as much as it takes in. And like the federal government, it can't do that forever because eventually it runs out of energy, yes? Now, Jupiter's a big planet, and it can do that for a while because it has a lot of internal energy to begin with. It's kind of like a potato that you take out of the microwave. It's nice and warm. You've just heated it up. You can feel the heat coming off of it, right? You can feel that. But it doesn't stay that way forever, does it? It radiates that heat into space, and after a while, it's cold. Now, Jupiter can do it for a lot longer because it's a much bigger potato, and so it can do that for a few thousand years. It's not a problem. But if it were billions of years old, why does it still have all that internal energy? It is a problem in the secular view. The problem is even worse for Neptune, which gives off 2.6 to 2.7 times as much energy as it receives from the sun. And it's a smaller planet, so it can't hold as much energy to begin with. So there's no way these worlds can be anywhere near billions of years old. By the way, that's true of a lot of planets. Earth even gives off more energy than it receives. But at least with Earth, they would say, well, radioactive decay might be able to produce new heat. But with Jupiter, it's made of the light stuff, so it's not going to have radioactive elements in it, at least not in any sufficient quantities to heat it up. Magnetic fields are an indication of youth. The Earth has a magnetic field that's generated by electrical current in its core, and it interacts with solar radiation. The solar radiation is actually deflected by the Earth's magnetic field. It protects us like an invisible shield. It's a design feature. But that magnetic field, which is generated by electrical current, well, electrical current encounters resistance and it runs down. And so Earth's magnetic field has been decaying since creation. And we've actually been able to measure that for the last almost 2 centuries. And by the way, we think that during the flood year, the Earth's magnetic field rapidly reversed due to the rapid movements of plate tectonics. That's a complication I don't want to go into. But the point is, the magnetic field, other than that, the magnetic field has simply been decaying. And it would have been maybe 20 times stronger at creation, which would have been nice. We'd have increased protection from cosmic rays, which would give us increased protection from things like cancer and so on. But in any case, it's decaying, and you run it backwards. It's an exponential decay as far as we can tell, and you run it backwards, and you find that the Earth's magnetic field can't be more than about 60,000 years old maximum. If it's that large, it would be stronger than a neutron star, and you don't want that. That would rip the atoms of your body apart. So it can't even be 1 million years old, let alone billions. Earth's magnetic field is very consistent with the biblical timescale. In fact, that's true of not just Earth, but a lot of the planets. Jupiter has a whopping big magnetic field. It would be larger than the sun if you could see it. And why does it have that strong magnetic field if it's billions of years old? Magnetic fields run down with time. They decay. Batteries run out. Why does Jupiter still have all this electricity in its battery? Well, I want to suggest to you it's because it's thousands of years old and not anywhere near millions or billions. Likewise, the planets Uranus and Neptune, which are almost twins, they're very similar planets. The planet Uranus actually rotates on its side like that, so it rolls around the sun, and it's got a magnetic field, a magnetic axis that's not aligned with the rotation axis. It's kind of shot through the side there, doesn't even go quite through the middle. Really interesting. So the planet Uranus is just really messed up on a number of levels, and I think God did it that way just to confuse the secularists, because there is no secular explanation for why it's this way. They want to try to, well, maybe something collided with it, but that really doesn't account for the magnetic field axis. Anyway, a friend of mine, Dr. Russ Humphreys, who is a PhD physicist, and he's a biblical creationist like myself, he was actually able to predict the magnetic field of the planet Uranus based on its biblical age of 6,000 years. And when Voyager 2 flew past Uranus, Dr. Humphreys was right on. You see how real science starts from the Bible if you want to get the right answer. The secularists' predictions were way off because they figured Uranus is billions of years old. The magnetic field should have run down by now. It should be essentially zero. But it's not. Dr. Humphreys was right. The same is true of Neptune. In fact, Dr. Humphreys' model actually accounts for the magnetic field of all of the planets. It's just interesting because he was able to, we already knew the magnetic field of the planets up to Saturn, and he was able to predict it for the 2 remaining planets, Uranus and Neptune, and he was right on. Right on. The secularists were way off. They have to try and get the magnetic field to recharge itself. If you've ever heard of a dynamo model, that the idea there is it's kind of like the alternator in your car. It takes mechanical energy and turns it into, kind of recharges the battery. But the alternator in your car is kind of a sophisticated mechanism. And as far as we can tell, planets don't have things like that. As far as we can tell, the magnetic field is simply decaying, and it's consistent with what we find on all of the planets today. The region of the moon is actually moving away from the Earth due to tidal forces. You might know the moon causes tides. It pulls on Earth's oceans, and Earth rotates faster than the moon orbits, and so the tidal bulges always get a little bit ahead of the moon, and they pull forward on it. And when you pull forward on something in orbit, it moves out. It's a little counterintuitive, I know, but that's the way it works. If the astronauts want to go into a higher orbit, they thrust forward, and that puts them into a higher orbit. It's gaining energy. You see, the moon's stealing a little bit of Earth's rotational energy, moving it away. It's about 1.5 inches a year. So you don't have to worry about the moon leaving anytime soon, okay? It's a small amount, because it's 240,000 miles away. So what's 1.5 inches a year among friends, right? But if you run the equation backwards, and you have to do it properly, because when the moon gets closer, the tidal bulges get bigger and it goes faster, so you have to compensate for that. You find that 6,000 years ago, the moon would have been about 730 feet closer to the Earth. Not a big deal at all. But if you run it back 1.4 billion years, the Earth and the moon would have been in the same place at the same time. And that can't happen, you see. And you say, well, that sounds like a lot. I mean, 1.4 billion years. But here's the point. Secularists believe the Earth-Moon system to be 4.5 billion years old, right? And last I checked, 4.5 billion is bigger than 1.4 billion, right? Even the Common Core folks understand that one, right? Yeah. Okay. So you see, that's a problem. That's a problem for the secular view. Comets. Comets are made up of icy material that orbits around the sun. They're kind of, they're just a few miles of ice. But then as they get close to the, see they kind of go far out and then they get whiplashed around like that. They come close to the sun and get whiplashed back out. Now when they come close to the sun, that icy material is vaporized and blasted away into space. And that's what forms a comet's tail. That's material that's actually being depleted by solar wind and radiation. So every time you see a comet, it's getting smaller. And we know how much material's there, and we can see the rate at which it's depleted, and so we can calculate that a typical comet can't last more than about 100,000 years maximum before it totally runs out of material. Now, if the solar system is 4.5 billion years old, then why do we still have comets? That's what I want to know. That's a problem, isn't it? I know comets don't last long. I used the SOHO spacecraft in my doctoral research, and it's designed to look right at the sun. And sometimes comets will pass behind the sun and then you don't see them anymore. They're totally obliterated in one pass. I've seen that happen. I've seen comets that no longer exist because they were destroyed by the sun. They don't last millions of years. Now, if the solar system's a few thousand years old, of course we can still have comets. But if it's billions of years old, they would be gone. And my secular colleagues have said, well, obviously there must be a comet generator that makes new ones, right? Which they call, that's what they believe. They call that the Oort cloud. And the idea is it's beyond, there's this big cloud of orbiting potential comets out beyond the farthest planets, too far away to be detected. And every now and then one of these potential comets is kicked into the inner solar system and becomes a brand new comet. So as old comets disintegrate, new ones replace them. Isn't that convenient? But as far as I can tell, there's no evidence of an Oort cloud. You'll find it in the textbooks. That's the only place you'll find it. You won't find it in the actual universe. Spiral galaxies are an indication of the youth of our universe. Spiral galaxies rotate differentially, which means the inner portions rotate faster than the outer portions in terms of their angular velocity. And so a star here will make a lap in less time than a star out here. And if you think about what that does, it's going to cause that spiral structure to twist tighter and tighter and tighter. I actually ran some computer simulations to find how long does it take for that spiral to get twisted beyond recognition. And the answer is it doesn't take more than about 100 million years, and it's gone. But you see, these galaxies in the secular view are supposed to be 10 billion years old. You see, they can't be anywhere close to that because the spiral structure would be gone. It would be twisted beyond recognition. You might notice that these spiral arms have kind of a bluish tinge to them. That's because they have a higher proportion of blue stars than the inner portions of the galaxy, the nuclear bulge. And blue stars are themselves an indication of recent creation, because blue stars are the hottest, most luminous stars in the galaxy, and they expend their fuel quickly, and therefore they cannot last billions of years. They would have exhausted their fuel a long time ago. Now, as it happens, they tend to be the most massive stars, so they have the most fuel available, but they use it up at an incredible rate. They're kind of like the SUV of the star world. They got a big gas tank, but they get very poor gas mileage, and so they can't really go very far in time. And by the way, my secular colleagues, they won't even dispute this one. They know that blue stars are young. They know that. But again, they say, well, obviously there must be some process that makes new ones. But it's really tricky to make a star. As far as I can tell, it's something that only God can do. Now, I won't be dogmatic on that. A star is not complicated in terms of its structure like an organism, right, where it requires design. A star is a ball of gas. That being said, gas doesn't want to just collapse in on itself into a little ball. Gas tends to spread out into the volume of its container. And when you walked into this room, you didn't hold your breath just in case all the air should come over here and form a little ball. You assumed it would spread out. That's what gas normally does. Normally, now, by the way, once you get the gas into a ball, something the size of a star, its own gravity will hold it together. But getting it there is a huge problem, because normally in space, the outward gas pressure is much greater than the minuscule inward force of gravity. And then there are other problems too, in terms of getting the magnetic field which tends to repel and dumping angular momentum and so on. I'm not convinced that stars can form. And you've said, oh, but, you know, Dr. Lyle, I've seen in textbooks, they say this is a star-forming region. Let me clue you in. They don't see stars forming there. What they see are blue stars. And they say, well, stars must have formed recently, right? Because we know the universe is billions of years old. And here are all these hot blue stars that can't last that long. This must be a star-forming region because you find all these young stars there. But they don't actually see stars forming. No one's seen a star form. I think it may be impossible. And again, I won't be dogmatic on that. So you see, the evidence really is very consistent with the age of the universe that the Bible indicates. What about the uniqueness of Earth? The Bible teaches that Earth is not just another planet. It's very special in God's eyes. Now, it might be not particularly spectacular in terms of size and some of its other properties, but it is the place where God put the people that he made in his own image. And that's pretty awesome. Isaiah 45:18. He's the God who formed the earth and made it. He established it and did not create it, a waste place, but formed it to be inhabited. The earth is designed for life. And to show its special significance, God actually created it 3 days before anything else. God makes the earth on day 1, if you read Genesis chapter 1. All the other objects in the universe are made on day 4. The sun, moon, the stars also. The Hebrew words for star, kokab, would include planets other than Earth. The earth really is special. The other worlds of our solar system, they have their beauty, don't get me wrong. One of the astronauts who walked on the surface of the moon called it a magnificent desolation. I think that's a great description of it. But it's not designed for life. What about the other planets? Venus, a little closer to the sun. Mars, a little further away. Beautiful, not designed for life. Venus, the surface temperature there, 900 degrees Fahrenheit. Not going to want to visit there on your next vacation. And it's always enshrouded in clouds, and you might think, well, that would help a little bit. Nope, because those clouds are sulfuric acid type compounds. Lots of ways to die on Venus. Not a place you want to visit. Mars is a little better, but even there, its current atmosphere wouldn't support you. You couldn't breathe on Mars because it has a very thin atmosphere of carbon dioxide, which you can't breathe. So that's not going to help you either. They're not designed for life, not like the Earth is. Kind of like Goldilocks and Three Bears, right? You got those ones, too hot, that one too cold. Earth's just right. That's what we'd expect, given what the Bible teaches. It really is a very special planet. What about distant starlight? I'm going to have to go through this kind of quickly. The Bible's right about this as well. Distant starlight's not a problem for a young universe. And let me give you a clue in on here a little bit if you haven't heard this. It's an argument that secularists try to use to discredit the Bible. They'll say, well, you have these light from these distant galaxies, and they're very far away. And I agree, they're very far away. And given that even though speed of light's very fast, these things are so far away, you would think it would take billions of years for the light to get from there to here. And we see these galaxies, so obviously the light has gone from there to here, right? And so the universe has got to be billions of years old, right? Well, it turns out that there's an answer to this, and I do have to point out that there are some answers that people have proposed that are not reasonable, and I don't have time to go into this in detail. I have another DVD on this if you're interested. But the distances are not real. I think they are real. There's good science for that. Or the speed of light was much faster in the past. I think that was a great thing to try, but there are good reasons to believe the speed of light has always been what it is today. Or the light was created in transit. A lot of people have said, well, you know, God made Adam as an adult. He made the earth as an adult, right? And that's true. Maybe he made the stars and he made the beam also. And I kind of like that, but there's a problem with it. I think that works on most other things, but I don't think it'll work for starlight because light in transit requires God to create fictional images in movies, right? We saw a star, for example, explode in 1987. That star that you see there blew itself to bits, and it's in one of the Magellanic Clouds. Today, you just see what's left of it, just kind of a remnant. But that thing is way beyond 6,000 light years away, which means if you think, well, the way God got the light here is he made a beam with the light already in it, then it means that star never existed. It was just a picture that God put in a beam of light about 6,000 light years out, and then he made a picture of that explosion, like a little movie along a light beam, where none of the objects actually existed. And of course, I don't deny that God has the power to do that. I just think it's inconsistent with his nature. God's not the author of deception or anything like that. So I think we have, in any case, I think we have a better answer than that. Some have pointed out that time dilation might solve the distant starlight problem. I think there's potential there, but I haven't seen a version of that mathematically actually works. I'm going to give you what I think the answer is. I don't claim to be dogmatic. The only thing I will be dogmatic about is that God's word is true, and he tells us he made in 6 days, and that settles that issue. But I think we have a good model as to how God may have done that. The solution may involve what we call the one-way speed of light. The speed of light is very fast. It travels 186,282 miles per second, but that is a round-trip average speed. Let me show you what I mean by that. Suppose we wanted to measure the speed of light. Okay, so what I'm going to do is I'm going to stand over here with a flashlight, and we're going to build a long hallway, 186,282 miles long. We'll pretend we have government funding. We can waste it that way. And we'll put a mirror. We'll put a mirror at the other end of the hallway, or maybe I've got a friend over there with a flashlight. Either way, it doesn't matter. And when my clock hits noon, I'll turn on the light pulse. It goes out, bounces off the mirror, and comes back. And as soon as I see the reflection, I'll look at the clock and see what the time is. Now, it turns out that if I did this experiment, the light has to travel 186,282 miles and then back that same distance. It would take 2 seconds for the light to do that. And so I would calculate, and I would say, well, 186,282 times 2 divided by 2, that's the speed of light. 186,000 miles per second is the speed of light. Now, most people assume that it took 1 second to go out and 1 second to come back, because I've pictured it that way. But if you think about it, I don't really know that. I'm here with my flashlight. I know when I start the experiment, and I know when I see the reflection, but I don't know when it hit the mirror. It might be the case that it zipped out, took no time at all to go out to the mirror, and then took all 2 seconds to come back. That could be the case. Or it could be the case that the light took all of its 2 seconds to go out and then zipped back. You see, I'm standing here. I'm going to see the same thing either way, aren't I? You say, well, why would it be different in different directions? I don't know, but I don't know why it would have to be the same either. Science isn't about just, well, I'd like it to be the same in all directions, so there it is. It doesn't work that way, right? You have to test things in science. So how would we test to see if the light goes out the same direction as it comes back, or the same speed it comes back? And you can see if this is the case down here at the bottom, if light, when it's moving toward an observer, takes no time at all, then there is no distant starlight problem, right? Because the light doesn't have to go out to the galaxies and then come back. It only has to go from the galaxy to the Earth. And so I'm kind of hoping this bottom case turns out to be right. But wishing for something doesn't make it so. We need to test this. So how would you test the one-way speed of light? Well, you can't use a mirror anymore because we're not going to bounce. We've got to measure a one-way trip. So you're going to need another clock. You're going to need one clock to tell you when to start the experiment, and another clock to tell you when to stop, when the light arrived, okay? And so here I am, and at noon I turn on my flashlight, and the other clock over there records the time. And you're thinking, yeah, it'll be 1 second past 12. Well, not necessarily. I did this experiment in my office. I don't have a long hallway, but I do have the distance between my watch and my phone. My phone has a clock on it, and I can convert. I'm pretty good at math. I can convert, okay? And so right at noon, I turned my flashlight on, right at noon, hit the phone, and I looked and saw when it hit the phone. I read the time, 12:05. Light takes 5 minutes to go from my watch to the phone. Do you believe that? You better not believe that, no. Now, I really did that, and that really is the result. But what went wrong? What assumption did I make? I assumed that the two clocks were synchronized. Obviously, the clock on my phone is 5 minutes fast, right? Really, it took virtually no time to get for the light to get from my watch to the phone. So you need synchronized clocks for this to work. And you say, no problem. We'll just make sure our clocks are synchronized. Turns out, it's impossible. When two clocks are separated by distance, it is impossible to synchronize them in a way that is objective, that everyone will agree upon. I'm already a little bit over time. I don't know how much I can get into this. Let me just point out, I'll just point out the two ways that people try and synchronize clocks by distance. One is by radio transmission. You'd say, well, in fact, my watch will do this. My watch receives a radio transmission from Fort Collins, Colorado, which is connected to the atomic clock in Boulder. Pretty neat. It synchronizes itself at midnight or 1 o'clock or something. But technically, my watch is a little bit behind the atomic clock in Boulder because radio takes a little bit of time. Not much, but it takes a little bit of time to go from the transmitter to my watch, right? So synchronizing the two clocks by this method, it's not going to work because that one will be just a little bit behind the other one. Now you say, but if we knew how fast the radio travels, we could subtract that off, right? We could push it ahead a little bit. Do you know how fast radio travels? Radio travels at the speed of light. You see the problem? That's the very thing I'm trying to measure. So I'd have to already know the one-way speed of light in order to use radio or anything like that to synchronize two clocks separated by a distance. I won't go into all of these, but I will. The other one that people will try to point out is they'll say, well, maybe we can synchronize both clocks together and then move them to opposite ends of the hallway. Sounds great. You'd say, well, they're still synchronized, right? Wrong. Einstein says that motion affects the passage of time. The very act of moving the clocks causes them to become slightly desynchronized. Now, it's not a huge effect, but it's there. And even a small change can make an enormous error in our measurement of the one-way speed of light. You see the problem there? Now, perhaps all is not lost. There is an equation that tells you how much time the clock loses or gains as it moves. But you know, in that equation is the one-way speed of light. God has designed the universe to where we can't measure the one-way speed of light. Apparently, it's impossible to synchronize clocks separated by a distance without knowing the one-way speed of light. And it's impossible to ever measure the one-way speed of light without synchronized clocks. We are stuck in a permanent catch-22. And I think that's very interesting. And this is something that's been explored by physicists for about a century. They've been exploring this in literature. It's a very fascinating issue, the problem of distant simultaneity, they call it. And the fact that you can't objectively synchronize clocks separated by a distance. And so my conclusion is the one-way speed of light is, in fact, not a property of nature at all, but a convention, something that we get to pick, and we all stick to it, and it works. So without going into all the details, because I'm over time, you can think of it like this. I can define the speed of light, the one-way speed of light, however I like, within certain constraints, as long as the round-trip speed remains c. And so I can define the speed of light to be instantaneous when it's moving toward me, as long as it's half c when it's moving away. And that works. You can do that. You can do it other ways too, but that's a perfectly legitimate solution. It's kind of like time zones on the Earth. And so the way you get starlight here, I can leave Kentucky at 4 o'clock and arrive in California at 4 o'clock. And I've very nearly done that on some flights because of the way the time zones work, the way we define time, which is kind of arbitrary a little bit. I mean, we prefer to have the noon when the sun is high and so on. There are other ways you could do it. That's a human convention. As long as you're going west, it works. You can arrive when you leave. You can do the same type of thing in space. The light can leave a star on day 4 when the star is first created and arrive on Earth at day 4 because of the way time is measured in space, at least one way of measuring time in space. And I think the Bible uses this particular convention because in Genesis 1, 14 and 15, then God said, "Let there be lights in the expanse of the heavens to separate the day from the night, and let them be for signs and for seasons and for days and years." We learn later that's the sun, the moon, the stars also. "And let them be for lights in the expanse of the heavens to give light on the earth." And it says, "And it was so." What was so? God made the lights and they gave light on the earth, apparently. As soon as God created them, they immediately fulfilled their God-ordained purpose of giving light on the earth. They didn't need any time at all. And that is perfectly consistent with what we understand about physics. It's called the conventionality thesis. You might look it up. There are secularists who would agree with me that that is a legitimate solution to distant starlight. They don't like the fact that it does solve distant starlight, but they will agree that if they know anything about physics, they'll agree that that is a good solution. So, is that the way that God? Do I know that's the way God did it? No, but it is certainly a reasonable way that He could have. And so there isn't a problem getting the light here in thousands of years. So, what have we seen? We've seen that the Bible's right when it speaks about the glory of God being revealed in creation, in the universe in particular. We've seen the Bible's right when it speaks to the basics of astronomy, things you'd learn in any freshman level astronomy class. The Bible's right when it speaks about the age of the universe. We've seen how the evidence lines up with the biblical timescale. We've seen that the Bible's right when it speaks to the uniqueness of the earth. And we've seen the Bible is right when it addresses distant starlight. And I've shown you one method that has yet to be refuted. I published this back in 2010 in a technical journal, and nobody's been able to refute it, so I think we got a good model there. But don't pin your faith on my model, pin your faith on the Word of God. That's really what it comes down to. And I want to show you now some resources here just at the end that I'd encourage you to get. If you want to learn more about what I talked about this evening, Taking Back Astronomy is the book you're going to want to get. That covers, I think, just about everything I covered this evening and some things that I didn't have a chance to go into. It's a great resource. It's an easy read, but it's got enough meat in there that I think you can share it with maybe an unbelieving friend as well and maybe challenge them. Stargazer's Guide to the Night Sky. If you'd say, I'd like to learn how to find some of these things that you talked about, Dr. Lyle, well, that book will show you how. And you say, I don't have a telescope. It doesn't matter. There's a lot you can see with the naked eye. And a lot you can see with binoculars, too. You know, you can see Saturn's rings in binoculars, just barely. You can see them. You just got to know which one's Saturn, and that's where the book will help you out there. We have DVDs as well. We've got Created Cosmos, which takes you on a tour through the universe. We've got Astronomy Reveals Creation, which is this presentation. You can get that on DVD. If you had a friend who you wish was here, and you can take it to them. I got one called The Secret Code of Creation. Oh, that's a neat DVD, folks. God has built an aspect of himself into an area of creation you probably haven't even thought about. And it's not something like genetics, and it's not astronomy. It's unique. So check that out. Secret Code of Creation. That's a neat DVD. Plenty of great DVDs out there. The Ultimate Proof of Creation. You say, there's all this science stuff. I can't remember all this science stuff. Get the Ultimate Proof of Creation. That's the one that's going to give you a bulletproof argument for biblical creation. Very, very powerful resource. I wish every student would get Ultimate Proof of Creation. Now, it's going to stretch some of you younger ones, but it really is. It's going to show you how to think and debate the way that Jesus did in his earthly ministry. And I see you got it back there. That's great. Thank you. Fantastic. And Discerning Truth. This is a kind of a follow-up to Ultimate Proof. This one's going to show you how to spot logical fallacies that evolutionists make in their reasoning. And I don't mean to be mean, but evolutionists do make a lot of mistakes in reasoning when it comes to evolution. They're not thinking properly. And this is going to show you how to expose that in a gracious way. And there's even a test in the back, 2 tests in the back with answer keys, so you can see how you did. And if you want kind of the best of everything, just in terms of all these different topics of creation, like was there an ice age, and what about continental drift, and could Noah get all the animals on the ark, and where did dinosaurs fit into the biblical timescale, and so on. Creation Basics and Beyond, written by Oliver Staff Scientists at ICR. Fantastic resource. I'd encourage you to get. We have a student version as well called Guide to Creation Basics. We have Acts and Facts magazine. That's our full-color monthly magazine that's just going to give you faith-building articles, and then you can, of course, share them with your unbelieving friends and so on. I think that'll challenge them. How many of you are already getting Acts and Facts magazine? Okay, a few. The rest of you need to repent of that sin and sign up. It is it is an absolutely free publication. The sign-up sheet looks like that. We just want to bless you. And then check us out on the web as well at icr.org. And thank you very much for having me out to speak. I really appreciate it.
Katrina and Megan Batur from Montreal asked, hi, Chris. Hello. How do you clean up a mess in space? Good question, because it's not going to fall on the floor. It's not going to fly up into the air. It's just going to float around until it runs into something. So let's make a little mess. Let's squirt some water as if it got away here. So those little drops are kind of departing, and then I've got a ball of water here just floating around. Got to clean it up. What am I going to do? So you look for a dry rag. You grab a rag. And we could grab a Russian rag. Here's a nice Russian rag. Here, get it out. My ball of water is still just floating there, fortunately. Get a rag out, I don't let it float away, and then bring my ball of water back on the rag. My ball of water is on this rag now. So it could have been chicken soup, it could have been some nasty fluid, but that's how you stop it. First, you get a rag out and you catch it, so now you have a wet rag. Now, something like water is fine, of course, and what we'll do with this rag is we'll just hang it on a clip somewhere and let it evaporate. And that way the water gets picked up by the humidifiers of the spaceship and goes back into our water system, gets purified back into drinking water, so we don't lose the water. But if it was something else, something a little nasty, then of course we could get a more rugged cleaner, just a great big cloth to wipe it up. Or if it was something a little sticky, we could get kind of baby wipes. We use pre-moistened wipes that then you can clean off the sticky stuff that's maybe stuck to the wall and dried, or if you got jam on something. So that takes care of things like water and stuff that isn't toxic. But what do you do if something nasty like a battery leaks or some sort of nasty liquid is floating around? Well, then we have what's called a contaminated cleanup kit. And I brought one here to show you. Here's our contaminated cleanup kit, and you of course want to protect your eyes. So you put on goggles, and you want to protect your mucous membranes and your lungs. So we put on a mask, try not to break it. Okay, so now I have my mask and my goggles on, and then we want to protect our hands. We have special gloves that protect us against chemicals. They're called silver shield gloves. So I put on my silver shield glove, and now I am ready with various types of absorbent things. And in fact, we have some great big ones, special soak-up mitts that we could put on top of a nasty spill, and then at the end of it, if you have the right type of combination, you could hold it in your hand and carefully pull off your glove. And now you've got a nasty thing on the space station, but we would wrap it inside 2 or 3 layers of containment, bags that close, zip up, until we're sure that it's not going to leak out. And then, finally, we're safe, and we can take off our gloves and our goggles and our mask and carry on with the business of being astronauts. Good question. Hi, Chris Hadfield here aboard the International Space Station. We keep busy on board the space station. Long days, lots of work, physical exercise. At the end of it, you're tired. But how do you sleep in space? In order to make it comfortable for the astronauts, originally they were going to put us all in one habitation module with sleep stations all around it. But the way a station was eventually built, we have sleep stations inside Node 2, which is in the forward part of the station, and inside the service module, which is in the aft. A total of 6 small bedrooms, sleep stations, or sleep pods. And inside each one is just a sleeping bag tied to the wall. You might think it's uncomfortable not having a mattress and a pillow, but without gravity, of course, you don't need anything to hold you up. You can just completely relax. And you don't even need a pillow. In space, you don't even have to hold your head up. So you can relax every muscle in your body, and your arms float up in front of you. Your head tips forward. But before I go to sleep, I gotta put on my pajamas, because I have space jammies. I'll be right back. Great. I'm in my super comfy Russian full-length pajamas. Nice for when you have to get up in the middle of the night, and ready to go to bed. I'll show you where I sleep. This is my sleep station, my sleep pod. This is where I spend up to 8 hours every day here on board the space station. It's actually on the floor, but once you're inside, you just can't tell.
On MPC, I'm ready as well.
CBS, The Talk. This is Mission Control Houston. Please call station for a voice check.
Station for a voice check. Station, this is The Talk. How do you hear me?
I hear you loud and clear. How me?
We hear you loud and clear. Excellent.
Welcome to the International Space Station.
Thank you.
I've been here, but I've been there before. Just kidding.
Getting by. Here we go. Welcome back to The Talk. Today we have a special treat. We're about to meet a mom whose devotion, let's just say, reaches beyond the stratosphere. Katie Coleman is a NASA astronaut and a mother of two, and she joins us now from the International Space Station. Hello, Katie.
Hello.
This is so cool, isn't it? Hey, Katie, I want to
welcome
ask you
aboard
a
the
question.
space station.
This is Leah. Look at this. Wow. Are you going to be okay, or? There's a delay, too, so we got to take that into consideration. Katie, can you hear me?
You know, we Yes, I can hear you.
Yes, I can hear you. Oh, good. Okay, well, I'm not the brightest person, so please don't try to say smart things when you're talking to me, but when you're talking to Sarah and Julie, you can say, you know, things that have to do with what you're doing. I want to know about your day-to-day. Like, take me through, like, an average day for you. You have your own room, you get up, what do you do? Do you shower? Do you have a chef? What goes on up there?
You know, we get up in the morning, brush our teeth, eat breakfast, just like everybody else, except that everything we do, we're weightless, and all the things we're doing it with are weightless as well. So you start off with that teeth brushing thing, and I have to say, you know, spitting, that's going to be a problem. So we swallow our toothpaste, and the day goes weightless from there.
And then what is your average work day? Is it like a real 8-hour day, or? And then what do you guys do? You sit around looking out the windows? What do you guys do? This is what I want to know.
You know, seriously, we live to look out the windows because it is simply amazing to look out. And, you know, every day is different looking down at the Earth. It depends on the weather. It depends on the lighting. I'm learning geography hand over foot. And so we live to look out the window. But I will say that most of our work is inside, you know, here in the space station. I'm in the Japanese part of the space station. It's the module that they built for experiments. We have a European module. We have a Russian section, a United States section. The Canadians built the arm. It's a big, big international venture. And every day, actually the day begins the night before, because I look at the schedule, see what I'm going to do, and I study up and just try to understand what experiments I'm going to do. And I can actually show you one of them. One of them's coming right at me right now.
Wow. So cool. What's that?
So before I show you this, let me just show you something else. Oops. It's going to come back to me, okay? I want to show you why we do these experiments, and that is because this is a bag of water, okay? And I'm squeezing. Let's see. Ah. So it's a brand new bag of water, and so my straw was a little crimped there. And I'm going to come a little closer, and you can see this giant blob of water. And we're getting to see in space, what do liquids really, really want to do?
Wow. That is amazing. That is amazing.
So I'm curious, because I know you have kids at home. How do you stay close to your kids?
Oh, wow.
Amazing.
Yeah.
I'm just curious how you stay close to your kids while you're in space.
Well, one of the ways that we stay close is I try to keep him really interested in what I'm doing, and I'm shaking up our fluids experiments so you can kind of see, you know, what a real experiment looks like, and not just playing with our water drops, but understanding how fluids behave in space. Well, it has to do with everything we do at home. And everything that we wear, everything that is in our house that is made with a process of something flowing through a pipe, we need to understand what liquids do. And this experiment actually shows us how to design fuel tanks for satellites. And you think, well, gee, why would I care? Everybody uses a cell phone, electronic devices, communication, military defense, you name it. And it all comes from things like this. When we talk about trying to keep my son interested, another way I do that is actually to bring one of his things with me up to space. He's a big fan, and so am I, of Calvin and Hobbes. And so I've brought a little Hobbes up in space with me, and I bring Hobbes to do experiments, and I take pictures and send him down to the ground so he understands what I'm doing every day. And I did that while I was training for this mission as well.
That's so cool. Wow. So, Katie, since you've been in space, what extra daddy duties has your husband had to take on since you're there on a 6-month mission?
Well, you know, I think a lot, and I really thank him for doing all of that. And, you know, I would have to say it's hard for me to let some of that go. You know, everything's not going to be done maybe the way that you would do it. And yet I know my son is in great hands. He's just a super, super dad. I think it's hard for any parent to be a parent alone. I know that because my husband and I both commute, we have a commuting marriage, we're both single parents in a certain way. And so I think it's really hard for him just because there's nobody else to help, really.
On a somber note, oh, okay, hang on one sec. Okay. Your commander there in space is the brother-in-law to Congresswoman Gabrielle Giffords. What has it been like at the International Space Station since the Tucson shootings?
You know, it's hard to be far away when things are happening down on Earth, and I can't speak for Scott, but I think something like the tragedy in Tucson, at least for me, it makes me think how precious all my relationships are, and it just made me want to call everybody that I love and just make sure that they knew that I cared about them. And up here, I think that we have a serious job to do, and we're intent on doing our jobs, and we try not to let things get in the way. And at the same time, there's a value in just thinking about what's going on and trying to come to terms with it.
Yeah, I'm curious. Does it get lonely in space?
Well, I was very excited about this interview just because I won't necessarily say it's lonely up here, but there are not a lot of other women. And so actually the thought of sort of having coffee with you guys was really appealing to me. In fact, I brought mine. I'm serious. There's something nice about girlfriends.
I love that.
There's something nice about sitting around with your girlfriends and saying hello.
Yeah, I love that. I'm curious how you also prepared to leave for 6 months. That's such a long trip.
Well, I did my best. I know I've left a lot of holes. I'm still writing back and forth with my husband and making sure he understands how to get my W-2 and all those kinds of, administrative things. My son had known for a couple years that I'd be going to the space station, and I tried to make it really clear when it would happen. It took several years to train. I traveled to Japan, to Europe, to Russia, and around the U.S., training for really almost 3 years to get ready for the mission, and that's actually worse in a way than being up here. They like to say that when I'm up here, at least they know where I am, and in fact they have an application where a computer program that they look at, and they know exactly where I am, and they go, "Mom, you're going over Australia." So it's pretty fun to be up here now where they know where I am.
Wow. What research are you doing in space that you're most excited about?
on a day-to-day basis, I love to do the things that I actually get to touch and move, like the experiment that you saw with the bubbles just now. But some of them aren't as tangible. We're doing some research in osteoporosis, which I think is fascinating and valuable. Basically, I'm an experiment, and because we lose bone mass up here, because we don't walk around on our legs, we lose bone at about 10 times the rate of a 70-year-old osteoporotic woman. And so, because I don't have some of the potential complications that somebody who's 70 might, I'm sort of a clean medical specimen to do some experiments. And so I'm taking some of those drugs, and we're looking at how my bone mass is changing, and we looked at it before I left, while I'm up here, and also when I get home, and it'll help us understand a lot about how osteoporosis, the mechanism of osteoporosis, which certainly affects millions of people down on the earth.
Do the health implications of that scare you?
I won't say they scare me, but I'll tell you that I take them very, very seriously, in that we exercise, about almost 2 hours a day, which I'll say I'm not disciplined enough to do down on the earth. But I do it up here because the implications of not exercising are really having a tremendous amount of bone loss. And I have a 10-year-old, and I figure I still have a lot of running around to do when I get home.
Katie, I wanted to ask you, other than your family, your son, what do you, as a woman, what do you miss the most?
I'm actually so excited about being here and just living in this environment and discovering new things every day in terms of what's delightful about just being here, about moving back and forth. It's just really such a neat place. I don't actually miss anything yet. I certainly miss my family quite a bit, and but at the same time, it's not as if I wish to be there. I'm really happy to be here.
Katie, you mentioned that you exercise 2 hours a day, but being that you have no gravity, how do you exercise in space?
It's a great question, and we have a weightlifting machine which works. It works on a principle of vacuum. Like, I'm not really lifting weights, but I'm pulling against something that's pulling on a vacuum, and so it's really hard. Like, when you're trying to get a lid off a jar that's got vacuum on it, it's harder than if there was no vacuum, or when you're pulling against something. So that we do weightlifting, and I'll do, it's like a gym. We have a bar, go up and down, and use my legs. I can do sit-ups, all these arm weights. We have a treadmill that I wear a harness, and it holds me down on the treadmill. And I have to say that it was really interesting after a few days of not exercising, floating around up here. It was fascinating to suddenly be on the treadmill, standing on your feet. And I thought, wow, standing, that's interesting.
What's the first thing you want to do when you eventually do get home back to your family?
Well, I'm assuming a shower will be like right in there. I mean, I'm actually clean up here. My hair is clean, and we take sponge baths literally, and so you're clean. But there's just nothing about like being actually in a shower. I think just being on the earth and walking around on your feet, and I think smelling and smelling just the garden and outside and the street and cars, and that kind of sense is a little missing up here. And even just listening to noises that aren't just the hum of the space station, and feeling the wind. I'm looking forward to maybe being on a beach and feeling the wind and looking at the ocean.
As we get ready to say goodbye, is there any message you'd like to send out to your 10-year-old son or your husband, your family?
Well, I miss them so much, and I appreciate, it's a lot of work for them, for me to be gone. And I'm just hoping that while I'm up here, the things that I'm doing end up being worth it. And I actually just really think that they will be. What we do here in space somehow says to kids, wow, don't you want to be an astronaut? Don't you think you could do this? Somehow they look at us and they think they could do this, and they're right. And it inspires them to study hard in school and learn the math and science that they need to be part of the future because they are the future. So it's a long time to be away from family. It's actually a magical place to spend that time in, and I think that the payoff is very big. It's nice to be with you guys today.
Katie Coleman, thank you so much for joining us. We wish you the best of luck up there in space. Keep doing the good work you're doing. Take good care. We'll be right back.
Thank you, and thanks for inviting me.
Station, this is Houston ACR. Thank you. That concludes the event.
Copy. Thank you. Nice to hear from you guys.
Thank you. The talk station, we are now resuming operational audio communications.
Station, this is Rachel Crane with CNN. How do you hear me?
I have you loud and clear on board the space station.
Great. How does a girl from Beaconsfield, Iowa, with a population of less than 20, become the commander of the International Space Station?
I don't know. I think it's kind of a miracle, actually. But I think the dedication and work ethic that I learned growing up on the farm, maybe in a healthy dose of stubbornness, kept me on a path that I got very lucky on in the end and was selected to be an astronaut. So it's pretty amazing, really quite unbelievable.
Now, you've been to space several times now. So what's the first thing that you do when you get back to Earth? Do you have a routine of some sort?
Shower is nice. Up here we have to take just wiped baths with wipes and towels and stuff, and so showers are nice, and food is nice. I like to be able to cook for myself, so food is a nice thing to have when you get back home.
So you've broken just about every record for a female astronaut, for a U.S. female astronaut out there. So was that your goal, or is that just sort of an added bonus to all of this?
It was really just an added bonus. I've been lucky enough, privileged enough to be in some very unique times and was able to do some very special things. Conducting spacewalks, being the first commander, all of that was somewhat based on timing and opportunities. So it's just a real honor for me to be able to represent NASA in these areas.
And each new record that you break, I mean, how does that make you feel?
Well, I guess I don't think about the records themselves too much, but it definitely, when I do think about them, I think about all the people that make it possible. There's an incredible number of people at NASA who make it possible.
On April 24th, you will have broken another incredible record. You will have spent more days in cumulative days in space than any other U.S. astronaut. What's the next record for you?
I'm not sure. I'm sure there's somebody out there keeping track, but I'm not sure what the next one will be.
So your stay on the International Space Station was just extended by 3 months. But how long in space is too long? I mean, do you think that our bodies and brains could actually handle a mission to Mars now, having spent so long on the International Space Station?
Actually, that's exactly why we're spending this time up here, is to find out what the limitations are, where do we need to compensate for things, whether it's from a psychological perspective or from a physiological perspective. Those are some of the questions that are really key for us that we're trying to learn here on board the space station, so that when we get ready to go to Mars, we will know that we are capable and ready, and it'll just be part of the evolution of getting there.
So the late, great John Glenn last flew to space when he was 77 years old. Do you have any indication of if you'll be still flying to space when you're 77, Peggy?
If I'm not dead.
So then this is not your last mission to space, you say?
I have no idea. There are lots of young people out there who need to have flight opportunities too, and so we don't have too many opportunities these days, and I may have to step back for a while. So that's just the way it is. But I'm loving working for NASA, and I worked for NASA for 10 years before I was lucky enough to be selected as an astronaut. I've always said I've never had a real job because I've done what I wanted.
So Peggy, your last spacewalk, you worked on a future docking port for commercial space missions. Would you go to space on a commercial mission?
Absolutely. I think our commercial providers are working very hard, striving to get up here, hopefully within the next year or so, with their first test flights. It's going to be an important time period for them, and I know they're working very hard on getting their vehicles and launchers human rated. So we're looking forward to welcoming on board the space station new vehicles, and I think that's going to be really special for us. I think it's going to be the next step in evolution of commercializing space and expanding our footprint into the solar system.
Peggy, what advice would you give to young girls out there who want to follow in your footsteps and hope to go to space one day?
Well, I think picking any field in math, science, or engineering and picking one that you love because you really need to excel at it. Also working on people skills. It's important in an environment like this to be able to work and in a collaborative way, not only with the crew that we have on board, but the crew that we have on the ground. The whole team is important. So those interpersonal skills are just as important as the technical skills. And for the crew on board, I think maybe even more important. So work on all those things, but the biggest piece of advice I would say is don't underestimate yourself, push yourself, challenge yourself to do more than you think you can.
You have stacked up one of the most impressive resumes at NASA. With all that you've done, what memory sticks out to you most, Peggy?
Well, other than actual space flight, being in space, I think probably the most challenging and interesting position I've had was being chief of the astronaut office. It was very much a work and collaborating with other organizations at NASA, and I really think it helped me develop a lot as a leader. So I think that was probably, other than spaceflight, my
and is there any advice that you would like to impart on the people who have already bought tickets to space, commercial tickets to space?
Enjoy it. It's going to be a blast. You're going to love every second of it. Just this whole environment, being able to be in zero gravity and move around at will is just amazing. It's very freeing, and it gives you a whole nother perspective on our planet below. So I just think everyone will enjoy it. Absolutely. 100%.
Thank you so much, Peggy. Really appreciate your time.
Station, this is Houston. Are you ready for the event?
We're ready for the event, Houston.
WCCO TV, this is Mission Control Houston. Please call station for a voice check.
Station, this is Mike Binkley with WCCO TV. How do you hear me?
Hi, Mike. Welcome to the International Space Station. We hear you loud and clear.
Wonderful. Great to see you both. And Chris Cassidy, I hope you understand, we're very proud of our native Minnesotan, so many of my questions today will relate to Karen Nyberg and her Minnesota ties. I got the thumbs up from you. Okay, so let's start with a question to you, Chris Cassidy. How is she doing up there? What does she bring to this team at the International Space Station?
Well, first and foremost, she brings hair. Luca and I, apparently, we don't have any, and she has an abundance of it, so we're very welcome to plenty of hair on board. And her sense of humor and feminine touch is a nice welcome thing up here as well. But we're having a great time, and it was nice for me to get companions back up here. It was a period of 2 weeks by myself for a little bit, which was fun, but I was really happy to see Karen and Luca here.
All right, Dr. Nyberg, I know that I've followed you on Twitter, and I see you do get questions about the hair. So let's just address that right now. It looks like you have it tied back just a little bit, but sometimes you just let it go.
Yeah, sometimes anybody who wears a ponytail for a long time knows that it starts to pull on your head and not feel very comfortable. But so I let it out once in a while, and when I wash it, I like to let it dry out. But when I'm working, it's usually best to have it pulled back to some extent.
All right, so let's talk about some of the pictures that you've been posting on Twitter. You've given us some amazing views. I want to talk about one photo in particular, Windows to the World. Describe your view from the International Space Station.
Well, I think that picture kind of describes it pretty well, although pictures never quite show exactly what it looks like. Anybody who's been backpacking and gone up in the mountains, the higher you get and you look out and you just think it's it's unbelievable views, and then you take a picture and when you show it to other people and try and describe it, it just never looks quite as beautiful. So we have the cupola, which we get, the 360-degree view, and we also have a couple other windows we can look at out the port side on the GEM, and then also the Russian segment. So we have a lot of opportunities and places we can grab a view.
I also want to ask about the sunset view. Apparently you get a few of these a day.
Yeah, we get 16 sunsets a day today, or recently, actually, the way our orbit is flying, we're kind of flying along the Terminator a lot, and so we see almost a perpetual sunrise or sunset. So that's mostly what we've been seeing since we've been here.
I saw a great picture of you having breakfast out of a bag, your coffee, and what was it, a scone that you had, a cinnamon scone?
Yeah, that was a cinnamon scone. That was on Sunday morning, and it was a nice, relaxing, get out of bed and have my coffee, and I felt like I was at a coffee house at home. Everything's pretty tasty, too.
I want to ask about your family, too. I know that you had at least one video conference with them so far. I know you have a young child. Is it true that you're actually reading stories from space to him? And what is that like for a child? Maybe to him that seems perfectly normal, but to us that seems a little unusual.
Yeah, I actually recorded some stories before I left for him, but I've been making a quick little video for him every day, about 20 seconds long, and sending it down. And I think it is a little normal for him and doesn't get him. In fact, I had a doll or a stuffed animal that I had showed him. I sent a video down yesterday, and evidently when he watched it, the first thing he kind of started to cry and said, "I want that one." So it wasn't as impressive that it was in space as I was hoping it would be.
All right, well, I want you to pass the mic back over to Chris Cassidy. I want to ask about the work day. How many hours a day are you actually working, and what type of experiments are you doing at this point?
Yeah, that's a good question. We generally, our work day is essentially from about 7:30 in the morning to 7:30 at night. But during that time, we have a break for lunch and to exercise. Exercise is an important part. So I would say it's probably around 8.5 hours of actual work, just like down at home. And the experiments are vast. There's some that are just kind of going on without us, and we really don't have much interaction with them. There's some that we're involved with setting them up, and once we set the experiment up, it continues and goes on. And there's several that we are the subjects for, such as eating certain foods, which Luca is doing these 4 days right now. He's eating certain foods, and then he'll have some sample blood and urine samples to see how his body's responding to the different levels of protein and potassium in his diet, as well as some ultrasounds that we'll be doing in the near future on our spines. And actually, we have eye exams this week, ocular health and that sort of thing. I personally was involved with some fire experiments. Everybody likes to burn things. Don't worry, it's really safe. There's a small little place where we do that. So those are types of the things that we're doing on Space Station, and the workday is much like a workday at home.
And so with these experiments, I mean, how will this advance science? What will we learn at the end of your period up there at the ISS with these experiments that you're doing?
Well, one of the most exciting things for me that I'm personally involved in on this time is the use of ultrasound in applications that would normally be used for MRI, and that has applications for remote regions or countries that aren't as fortunate as ours, where you can just pack in a briefcase-size ultrasound machine and give people the treatment and health care that would be available in larger cities and that sort of thing. And we're practicing and doing that and validating that up here in Zero-G. Also, the importance of keeping your bones healthy late in life, and the exercise programs and the food regimes that we're doing are helping solve that problem too. So those are things that I think are very applicable to people on Earth and rewarding for us to be a part of.
I want to try and squeeze in a couple more questions for Karen. First of all, we saw the pictures of, what do you call them, fat quarters, floating fat quarters. You're going to be doing some knitting up there?
Actually, I don't knit. My mom does. I never took up that hobby, but quilting. We have spare time on the weekends, just like you do at home. We do Saturdays, spend some time housekeeping, and then after that, some spare time. And Sunday is mostly a day just to do whatever you want, read a book, look out the window, draw, play the piano, anything like that. And I figured that's one of my favorite hobbies on Earth, so I could just as well try it here too.
And I loved the picture that you posted on Twitter of a poster that you had, pardon me, a poster that you had in your room growing up in Vining. Can you talk to me about that and how you went from Vining, Minnesota to the International Space Station?
That's right. My sisters just reminded me recently of a...
This is Houston, WCCO TV.
Hey, sup, dog? That's what we normally do, right? This is work.
This is the whole tour. Right, start and finish right here.
I'm on my computer. Look, Mom, no hands.
You have hands.
No feet.
It's roomy.
All right, welcome to the International Space Station. Here's a tour. We're starting right now in Columbus, and if you look on this little iPad right here, there's a picture of station, and right here, that's Columbus. So then we're on the starboard side, kind of front area, and that module right there, that's what we're in right now. As you can see, it's of course the European laboratory, but it's not just European. We also have NASA racks in here, NASA payloads in here too at the same time. So it's actually quite a new stuff over here. This is the EML, and Alex will have to tell you all about that because that's his little bailiwick. But it's actually pretty cool because it talks about magnetic levitation, and I just think that's a cool sounding thing. I don't know exactly what it's going to do, but it sounds great to me. And over here you can't, it's hard to see again everything, but we were growing the, in here we were growing, that's where we grew the lettuce, is right in there. That's it. Move on farther, just a workbench, storage area, and there's a storage area above me, storage area below me, over here. We come over here, this is where we take our blood. We got it all set up for doing that. All the stuff you really need for that, all around here. That's a pretty easy task. We do that, and then we have a centrifuge we can put the blood into to process it, and then after we do that for 30 minutes we freeze it, get all cold, and then we ship it to ground, and hopefully they can tell us something about it from when we get there. Again, more storage over here, and also the ultrasound we hook up right here. We do ultrasounds of all sorts of parts of our body, make sure we're still doing okay. And there's also over here the Slam D, which we don't have to set up, but that's where we do the measure our mass or our weight, see if we're losing or gaining weight. We can set that up over here too, our version of that. And again, there's a lot of science actually going on here too that we don't touch too much, but we just set up. It's a good place, and it's going pretty well. And this is Alex, as you can tell. This is the German flags in the back, ESA stuff. It's a good place for Alex. So let's move on to Node 2.
Vacuum cleaner.
Yes, it's true point. We do have one of the most important pieces of equipment on International Space Station hidden up here. This is the vacuum cleaner, and it's the AC version. And we say, NASA's talk, that this is the only piece of equipment that doesn't suck on the International Space Station. But actually, this is actually much better than the old one, so we actually like it. And it's nothing too fancy, just a vacuum cleaner. But we have to use it every week for stuff clean. Come into Node 2, and if you look on the picture here, Node 2 is this section right here. It's this front little piece that fits on the station. So it's actually where the shuttle used to front, and this black part is where the shuttle used to dock to. And so right now, there's nothing of course is docking to that, but we're in this area right after there. It's called Node 2. And so if you look out here, this is where the shuttle actually docked, is right through that hatch right that way. And there's still a device or a module called PMA-2 out there. And when we get a visiting vehicle such as a Cygnus or a SpaceX, we berth it down here on the nadir side, the lower side. So we'll open that hatch and we have that there. And again, so that's again the idea of being a node. It has multiple spots to attach to. So you have all 4 sections here around and the one out the front and actually one behind us. So it has actually 6 places to dock other modules too up here. Besides that, it's really our a workbench area and our living quarters in Node 2. So you come this way. Actually, you'll see over here another one of our workbenches. We'll usually keep both workbenches here and here. At this time, we have one in the Columbus module. At this time, just because Alex is working on a special project there. And then if you go back, you'll see now it's coming into view the 4 crew quarters around here. So we have 4 of us. This one's mine over here. We have Alec, and we have Tonto, and we have Alex. And it's kind of interesting because once you get into one, you really can't tell which one's which orientation you are. So if I happen to go into Tonto's to look at a picture or something he's got on his screen, I'll come out and I'll be kind of confused because I don't know which way I'm going. And especially if you go into Alex's or Alex to do that, you come out and you're really confused because it feels like you're in your own, but when you come out, it's totally different orientation. But if you're looking here, these aren't too big at all. You can take a quick look in here. I'll jump in here real quick. So we have a sleeping bag attached to the wall. The way I like to do it is I just have it attached here one point and one point up here, so I can put my feet right up here when I'm sleeping, and I kind of do it in a sense of this position, like this, and I'm kind of curled up a little bit in the semi on my side sleeping position, which I like to do back on Earth, and it kind of works out pretty well. It gives me that same feeling, almost, but it works well for me. And then when you wake up in the morning, the first thing you see is your laptops. I got one that connects to the internet, which works like 50% of the time, and then I got another one that does our LAN up here, which gives us our schedule, all the other information, our email, everything we need to do to work up here. That's what that one is. And we also have an iPad, as you can see, and that's also up there, and that's again for all sorts of work or for watching movies or something like that on. That's what it's good for. Again though, it's actually not a bad setup. I know it's small, but really it works out well. We don't really need much more room up here. So let's now move on to the lab. If again you look on here, so what we're doing right now is we're heading towards the back, towards the aft. We were in the very front, in the middle, and now we're going down this long path in the back. And the first one we come to is a lab. And you see on the back, on top of the lab I should say, at the very aft part is this big structure over here. It's called this truss, sorry. And on the truss we have the solar arrays. And so we can, of course, that's all on the outside, and we only get out there doing a spacewalk. But so that's kind of how this is set up, though, so you can see where we are. So here's the lab here. We're going to head into the lab. This is the U.S. lab. And again, this is pretty much just science racks and storage is what we have. And of course, in avionics. We have a lot of the computers that run the system, or run the lab, or sorry, run the station, are in here. And besides that, then we have all sorts of experiments. And also right here, the first thing we start off here with is we call this Melfi, which is actually a big freezer, a minus 80-degree freezer. And there's 4 different sections of it, and they can control each different section here with a different temperature if they want to. And that's where we put, when we say with blood and stuff like that, we're going to put it in there to store it until it goes home. So that's how all the science is stored once we do it. Here's a glove box, so we can use to do experiments on here if we need to use a glove box. So people on this increment have been doing bass, which was I think kind of interesting. We all liked it as males because it was burning stuff, and you could burn things in here in the glove box, and that also was actually kind of nice. And right, and then later on, after the next SpaceX gets here, they're actually going to do all the work on the mice in that area, which is I think going to be very interesting, difficult but interesting at the same time. You go to the other side over here, in this little hidden area is what I've been working on lately. That's a Robonaut. You can hardly see him in here. So he's been my latest project. We've been upgrading the all the electronics in there, the computers, etc. And then this next week I actually get to put legs on him. I think he's going to be actually kind of creepy looking when he gets legs. But hopefully it'll help him walk around the station, move around the station. And as you look around the other spots, then we have on the top, we call them express racks. And express racks just means really it has power and data for any kind of experiments that want to go up there. So if anything on the ground, somebody comes up with an idea for science, and all they need is a data connection and power, they can design it to fit in here, and we can easily put it on there, hook it up, and then they can control it from the ground and do all the science without much interaction from us, which actually works out pretty well because we'll set it all up and they can run a lot more science that way. As we move this way, of course, we got the bike here we set up for exercise, which you have to do about a couple hours a day, either the bike, the treadmill, or on ARED, which is our lifting device. We got that, we got storage behind it. Up here is again the material science rack, and it's kind of, again, the ground does that. We set that one up, we put in stuff to burn again almost, and they do a bunch of experiments on it. We don't really touch it while it's running, but we set it up for them. It's kind of like what's over here too. This is another combustion rack, and again we'll set this all up for them, put in the fluids, the fuels, the igniters, all that stuff, set it all up, close it up, and then they run it from the ground. Actually, again, I think they get good science out of that way, and it works pretty well. Over here is a called a FUR, or Fluids and Combustion Facility, but right now it has a really big a microscope in there, and we put samples in there for them to look at on the microscope from the ground. So you see, most of the science here is a combination of us doing work, and then on the ground they do a lot more work, and then they're the ones, of course, who are the experts. We're not the experts in the science, but we just help them out, and hopefully we get good science out of it. Bottom's another storage rack, and this has most of our medical stuff. So you can see the little cross on there for the AED, etc. The important medical stuff that is needed is right here across this rack. Another express rack for science, another express rack for science here. As we come farther in over here, this is called the robotics workstation, and the idea here, of course, is you can fly the arm from this guy right here. So this is where your camera views, so you can look outside to see what the arm's doing from this camera views. You have a controller that'll set up how you're going to fly the arm and put it into the correct mode for flying the arm. And then these are your hand controllers. And one is for translation, which means, of course, left, right, up, and down. And then this is attitude control over here, so if you want to pitch it up, pitch it down, yaw, roll, like that, you do it with this. And you do a combination to make the arm go where you want it to go. It's good. We have two of these. We have one here in the lab and one in the cupola. And they both have different advantages and disadvantages depending on where you want to go with it. Let's see, if besides that we have over here is actually a trainer for using the arm. So this is kind of a setup, the same idea, but what it is, this is just all software, and then so we can actually practice using the arm right here. And it's kind of nice because if you're going to grapple a coming vehicle, it's great to get a few practices in before you actually have to do the real thing. It helps out a lot to have this. And we usually set it up and then make it a video game because it's all set up ready to go for us to practice, and it takes only about a minute or 2 minutes to run and make a run of it. So we'll sit there and put your quarter in, run the game, and then get a little practice, and then we go ahead and move on after that. As we move here, this is more just avionics rack here. We got the like air conditioning system, computers again that run on the station, and some stowage up above. Well, that's pretty much the lab. As we move this way again farther aft, we go into Node 1, which is pretty much just like Node 2. It's a little older, with the same concept, same design, and what's where we really eat and have that our food, etc., set up a little sort of like a table where we watch a little TV. We watch movies sometimes on the weekends here, and this is kind of our area for relaxation. If you look over here, and this is our table. Now really when we eat, it's more like, I think we prepare here. We really don't eat on the table here because there's no reason to eat on a table. So what we'll do is we'll help prepare things here, keep things stuck to the Velcro or the tape as we need it to, and then when we want to eat though, you're actually just holding it here, letting it float, or eating it to do what you need to do while you eat. And as we sit around here, if we want to throw on something on a movie on, or something to watch during while we're eating, so that we don't have to talk to each other, that's always gets old. And we'll do that right here as we do it. This right here is our food warmer. So we take the packets of food, go ahead, throw them in here, heat them up, and this is actually the art of the week. So we're getting pictures from the kids of people who work on the ground force, the ground team, which we truly appreciate. We have their kids send us a picture every week of art, so it's like refrigerator art. We put it on our heater here because we really don't have a refrigerator right here. So we use that, and we have a new one each week on there. Besides that, we have more stowage here, all the way around. You can also tell the color, if you look around here, it's kind of interesting how it used to be white, but after over 10 years of people living on this thing, or over 10 years for sure, it's got a little stained. And that's one thing about eating up here, is it's a mess. Every time you open a package, as you think about it at home, when you open a package, you pull it to open, well, actually right here you're putting energy into this package, and it squeezes up and then it goes boom, and it pops. When it pops, things come flying out. And sometimes you contain it, sometimes you don't. And hence we got stains everywhere. I think that's it pretty much for, over here is where we keep our food, I should say that right here. Food stowage. So this is always interesting. So we have things categorized a little bit into, of course, people's own little food they have, and we have breakfast and sides, etc. So if you want something out of breakfast, you come over here. You look, and of course right now we're hurting for breakfast because we got scrambled eggs, there's about what's left, and maybe some sausage patties. We all like granola and oatmeal, and so that runs out in about 2 days for us. Every 7 days we get a new package of food for that. So breakfast isn't always great around here for us. But so we have those around here for that. Again, some more stuff to eat, and that's how we keep it all organized a little bit for our foods. Up here is where the meat packages are. If today we want to heat something up, again, these are the type of things you heat up. These are our meats. Throw that in the heater, and then about 10 minutes later you can eat it. So from here, if we go starboard, we go into the airlock. If you look on here, it's just starboard. That right there is the airlock, and there's two parts to the airlock. The closest part to us, which would be this part right here, is called the equipment lock, and the most starboard part is called the crew lock. And the crew lock is where you actually go out of when you do a spacewalk. It's what actually depresses down the vacuum, and that's where you open the hatch. So we come in here. This is now into the equipment lock right here. And the idea of the equipment lock, of course, is where the equipment is. And then it's also where the suits are, and this is where we actually suit up. And we have these little structures right here that the suits are on. And they're called ADAS, which is an acronym, and I don't even know what it stands for, but it's an acronym, EDDA. But that's where the suits are on, and we actually have them on here to when we get in. We can pop off basically the pants, put the pants on, and we climb up in here with the helmet off, and we get on in the suit, and we're all ready to go. The person who's helping us get the suit up will take us off and stick us in to the crew lock over here, which again right now it was full of a bunch of stuff. And then but that would be empty, of course, for an actual spacewalk. We close this hatch right here and depress this part now to vacuum, and open the hatch down that way is where the hatch is where you open. You can see there's all sorts of equipment we have. This is good in storage right now because we're not going to do a spacewalk for a little bit. So we just have it more stowed right now for everything on the spacewalk side. And that is unfortunate. If you go down from here, which would be nadir in our speak, it's hard to show on this guy because you really can't see it. So basically we're at the lab, and then we're going down towards Earth. If you look at it that way. So it doesn't really show it on here because it's blocked by the Node 2. But if you go down right here, so we would be going from Node 1 down nadir. This is actually called the PMM. And that's really us too, is a big stowage area. What we have down here is just pure stowage. That's what it's for. And we have all our supplies, food, extra equipment, other stuff like that that we need to have for months on board in case another vehicle doesn't come to resupply us. We need a bunch of equipment. So you can kind of look at that and see that that's just a bunch of stowage area. And it's also where we keep our trash. And, we just can't throw the trash out on the curb every week up here. So we have to keep it. And last time when Cygnus left, it had about we had about 25 bags worth of trash that we threw out. And the bags are pretty good sized bags. They're like big, think of big hefty bags of trash that we threw out on Cygnus. So that's where we have to keep that. Besides our new stuff, we have to also keep trash down there too. If we go to the port side, now you can see that on here. The port side is called Node 3, and again it's very similar to Node 1 and 2, and it's not even on this picture, so that makes it more difficult. But I might even have another one that shows it, but it doesn't matter. It's to the port side.
Blame the guy who downloaded the picture.
Yeah, blame the guy who downloaded the picture. Exactly, and it's not on that one either. Wow, look at all that. All right, but it's on the port side, and this has many functions. The Node 3 has many functions. First of all, it's a place for working out. Right here is our treadmill. See, it's actually on the wall, so we always are running downhill. Makes it easier that way. And the idea, of course, of the treadmill here is we have these bungees we hook up to a harness that we wear. Now here's my harness. I'll hook it up to this harness right here, and then I'll hook that harness again into here, strap myself down to the treadmill itself, and go for a run. It's somewhat similar to running on the ground, I would say. You're a little bit lighter than you actually are weight-wise. So your legs actually don't get worked just as well, maybe as much, but it feels overall as a more body workout because you have the load on your shoulders and your upper body while you're running, which you really don't have. So it's kind of a combination there, a little different, but overall it gives you a good workout. Here are some other equipment we have. This is a water analyzer. We use this, we put water samples in here from all over and test out the water to make sure we have bacteria growing, other stuff growing in the water that would be harmful to us. That's how we test that out. This is actually a container that has urine in it, and we get that from the Russians, and we put that then into our recycling system, our water recycling system. So first it goes into the urine processor, and then from there it goes into the water processor to make us drinking water. So we're drinking the urine coming from these ones. We also have here, it's called a WC, but if you notice it's actually an outhouse, and really that's what it is. It's just a bathroom. And again, so the urine that we use in here also it gets recycled, and then so we actually have quite a green little system up here. And we recycle quite a bit of all the fluids that are used up here, I guess. The condensation, our sweat, everything gets all set back into the system and used again. So for the bathroom, you know, when they call the bathroom the can, there's a reason why we call it a can. Because here it is right here. There's a can, and that definitely is a can full of crap, literally. And so that's what happens. You can sit here when you want to use it for that version of it. And basically there's a little bit of suction that comes down there to help keep pretty much the smell from coming up and everything else from coming up while you're using it. And we use little packets here that fit into the hole that fits on top here. These packets go in here. You use one of these packets, of course, and when you're done with the packet, you wrap it up and push it back in there. And about every 8-9 days, that becomes full, and we put a new one in. That also gets then thrown down in the PMM for our trash, and hopefully on a cargo vehicle that's all done, that's going to burn up on the way in. We put those on there and it's done. For urination, you got to go there. Of course, that's white, yellow. It's a standard. It's a suction. Basically, there's almost like a wet vac in the back here. That's the way I look at it. And so it separates, it has suction on it, and it separates the water and the air inside there, the urine in the air. And the urine, of course, goes to the urine processor. The air gets a little bit filtered and sent back out again. And that's the way. So it's a nice system. It actually works quite well. We had some issues early on, but now it's been working really, really well. Knock on wood. Exactly for that. We're happy about that. Yeah, but you know, it's a robust system. It's not complicated. It was probably built 40 some years ago, or designed, and it still seems to work pretty well. Yeah, we're happy with it. Besides that, we have equipment again over here is more of the Eclipse equipment again, where we have racks that circulate the air, clean the air, and this down here is a water processing system. There's an oxygen generator that takes water and makes oxygen out of it, and a Sabatier process. So this is again kind of like all recycling in this area here for the NOAA 3. And this is also where we clean up in the morning, say brush your teeth, that kind of stuff every morning. So we have right here is our, what I guess you'd call it your hygiene equipment, but basically anything like that, it's basically your toiletries. If you look at it that way. So you pull this open and it has pretty much everything you need all in one. Your toothbrush, your toothpaste, you have an electric razor, and you have a standard razor. So I usually use like the standard razor maybe twice a week, and then I'm lazy on the other mornings and I'll use electric razor. And when we take to clean the electric razor every week, we'll take the vacuum as we vacuum this place up. We'll vacuum out the electric razors, that way we don't get to make a mess out of them. Got a little no rinse shampoo. This is the shaving cream. It needs a little water to go with it. Overall though, you have everything you need, and it actually works out pretty well. It's really not, it's camping. If you're okay with camping, then it's not a big deal up here. It's pretty good. If you come over this way, you can see this is where we do our lifting right here, and it's upside down, so if I want to lift, I'm actually working on it this way. So this is, so basically this is the bar we have right here. We can set the weights by moving this, and all this really is two cylinders that are at vacuum up here. We sucked all the air out of them. So as you pull these cylinders out, it pulls against the vacuum, causing resistance. And when you change the weight, you're really just changing the mechanical arm on these cylinders to make it either make the pull harder or more easier, depending on what you want to do with it. And that can change the weight you're actually lifting. And so, and it's a good system. It gives you a good lift. We can do, you know, squats, deadlifts, hill raises and bench, shoulder press, all sorts of things on this. And I feel it's actually quite good. It's much better than I expected, honestly. It's a good workout, and I'm glad we have it. So it's one of my things I like to do up here. Back on this side again. So on NOAA 3, we again have the hatches all the way around. You can use. I'll go back the right way now. So again, the only place we have anything though right now is Nadir, and Nadir down here we have is a cupola. And right now, unfortunately, it's dark out, so maybe we'll take a look at that a little bit later. But that is our window on the world, the Gloss Bottom Boat. It's a beautiful place. That's where we like to stay and hang out and watch Earth. There's also another robotics workstation down there. I'll show you in a minute. But on the sides, again, it's just hatches, but right now we don't have anything on them. One day I believe they're going to plan on moving PMM over and also putting maybe another Bigelow module out here. It would be very interesting to see, but for right now this is all we have. And on this side again is stowage. Again, we have all sorts of things here for stowage, mostly water that we stow over here. All right. Alright, we're back in node 3. Gonna head nadir into the cupola. Got some sunlight now. And this is our best viewing spot on the world. Come on in. Straight out of the way. Very good. So we have full of cameras up here. And of course, robotic workstation, just like in the lab. And there's a beautiful Earth. So we can hang out. You see the arm? I don't know if you can see the arm there. It's set up. It's on the top, or sorry, on the bottom of node 2. It's connected to it right there. And that's the position that we use to grapple the cargo vehicles, SpaceX and Cygnus and HTV. And it goes in right on node 2. Just a little bit forward of where it's grappled to node 2 is where we berth those vehicles. And if you come right here, then you can see to the right is the Japanese, the GEM, which we'll go to shortly, along with the exposed facility out there. That's part of the Japanese Module 2 when we have experiments that are outside, and we have a Japanese arm that can move those around and do work on those. And you can see right now, if a little bit more to the right, you'll see actually a launcher that we've been launching small satellites off of right there, which is kind of cool. That's kind of nice to watch those go by. If you go back to the left over here, you're going to see the PMM, which is our storage vehicle. It's right there. Made by the Italian Space Agency, as you can see, Ozzy. As you go farther aft, you'll see first is a Progress.
No, that's my spaceship.
It is. That is Tonto's Progress right there.
Oh, it's a Soyuz.
I know that. I was giving you a hard time. He's a cargo, so you know. No, it is a Soyuz. It is a Soyuz because it says so on there, and it is a. It's the one that 39S crew came up on, and then behind that is a Progress, and not just a Russian cargo vehicle. And as you go around, that's pretty much what you can see out here. You got solar arrays, of course, on each side. If you go over this side, all the way over, you can see the solar array on the port side. Here's you kind of view what it is like from outside out here on the station. But this is the best part out here, though, is looking down at Earth. We try to do that as much as possible. Unfortunately, we don't get near as much time as we'd like. They make us do work. Let's go on back. What we're going to head to the gym because we missed that at the beginning. So we'll head there, and then that will finish up the USOS segment. And on the way, I'm going to get some water because I realized I was thirsty. And I'll show you how we put water either for our drink bags or for if you need to rehydrate some food. We have a place we get water. It's either just kind of room temperature water or it's hot water. So this is the location. It's called the PWD, Portable Water Dispenser. Potable water dispenser. I knew that. And it probably is portable too, but not that good. So you just put whatever it is into the adapter, tell it how much water you want, and hit the button. It's pretty easy. Even I can do it. Now if you do want some cool stuff, we have these, it's called Merlins, but they're kind of set for refrigerators. But we look at them. And we have stuff in there. Our main sauce right there is sriracha, and we live off of that. At least I do. That makes everything taste better. When it's done, it fills up. And the nice thing about these things, these straws, of course, it's got a little clamp on there. So if I didn't have that on there, I'll show you real quickly. If that's just off on there, the water pressure, it just starts coming on out. There we go. Let's go into the gem. I'm going back, actually right now, back to Note 2. See? We'll head starboard. Alex.
Starboard or port, either one.
Either port. It's actually port. I was backwards. I was going backwards. I was going the wrong way. Alright. So it's actually on the port side, the front port side of Note 2. Japanese module. This is their laboratory. And again, it's like the Columbus in the sense it has half Japanese and half U.S. equipment in here. Also for stowage. Many different racks. Again, we have a Melfi on this side over here, which is the big freezers go to minus 80 degrees for our science. It's very good. Over here is a glove box with a microscope in his side over here, and over here it has a place basically to incubate things. We have one, you can do it as in, so it free floats in the microgravity, another one that they compare it to, which has a centrifuge, and they make it a 1G or a partial G, however they want to do the science. And so it has a spinner in here, and that way they compare the two here. They put two samples of the same, start them up, and then we put them over into the microscope, and they can compare them right there. Been working on those this last few months too, on a couple different experiments on that. It's kind of nice. Another express rack over here, again with different pieces of equipment in it. Again, just Power Native, they can do all sorts of different types of equipment. It's pretty amazing all the things they can do. We come to our stowage area, lots of stowage of course. There's avionics down there too. Again, crystallization observatory. There's all sorts of science around here, and I haven't even got to play with this one, the Fluids Physics Experiment Facility. I haven't got to play with this one yet. So there's lots of science here that I didn't get to even play with up here that's going on. Unfortunately, I won't get to, but there's so much science going on. Well, we have over 200 experiments going on up here while we're here, and it's impossible to know them all. But I hope to get to work with at least half of them. We continue on, we go for more and more. And this is the area we also do spheres, which we like to do. So it's set up in this little area here. There's beacons that set up around here that the spheres, these little satellites, which I'll show you here real quickly, we can control these things through software, and they actually stay in this area, and they have navigation and control with them, and they can do all sorts of different kind of science with them. Just to get you an idea what it's like in the stowage areas. So here's a sphere. It's got a little CO2 cartridge in it, so it has little jets on it, and this thing can then fly around station. We're getting it set up here to actually put basically a smartphone on it, and it's going to then use its camera and map the inside of the station, and then use that as its guidance navigation, and go ahead and fly a trajectory through station. I'm looking forward to that one too. I think that's going to be really cool science. But again, this is the main area for spheres that we use, because it has right now the beacon set up to keep the navigation system right here, and it knows where it is as long as it's flying right here. I'm looking forward to the upgrade though, where we can go anywhere with these things. As we go on, again, this is the robotics workstation for the Japanese arm. You probably saw that out the cupola window. Again, it is mostly though controlled by the ground, and they do a good job. But the big thing about the Japanese arm, it can go over here to the airlock, which we put equipment on, so that launcher that was on the arm was actually inside. Alex prepped it up, got it all ready, put it on a slide table that's on this airlock that comes out here with this door open. We put the slide table into the middle, close this door, depress the airlock, and then open the outer door. The slide table moves out, and then the arm grabs whatever we put on it with it, and then in this case it was a launcher, and sticks it up in space and launches off the little satellites. Earlier this mission I did a camera before the arm. I did the same thing and put it on the table and set it out there, and the arm picked it up and moved it to the Canadian arm, which put it on itself. It's kind of all interesting, but this is a big handy little thing to have here, this airlock in the gem. And we do have a couple windows though over here. We don't keep open much, but you can see the exposed facility if you open these windows up. Of course it's nighttime right now, but right out there is the exposed facility. Unfortunately you're not going to be able to see too much, I don't think so. You can try Tondo, but I think they're going to get reflection is all they're going to see.
Yep.
But
yep, just reflection of the airlock.
Alright. That is exposed facility out there with payloads on it. And again, if we need to, we can bring those payloads in through the airlock, do some work on them. But mostly it's all done robotically. If you go to Zenith, which is up for us, that's where you get the plane. Oh, this is Tano's favorite experiment, sorry. It's called BCAT. It's colloidals again. We do a lot of colloidal research. I'm sure you're not exactly what that's all for, but I hear it's really good. And so what this is, if you look at this, there's actually 10 different little chambers in here. And what you have to do to get those chambers to work is you have to mix them up so it makes it a smooth, and then basically all the colloidals kind of mix into the solution. And then it sits over time, and they all form, the crystals are formed together, and they can do a lot of science about these things and how they form and why they form and all that. And at the same time, to measure that or to analyze it, this camera will take a picture of it once every 2 hours. And then, so they do it for almost 2 weeks it runs for.
It's running right now.
It's running right now. And that's why we have the little, the tape up here. It's not, this is an accident scene. It's actually, we're not supposed to get in there and touch it.
All right, thanks, Wayne. Now you can continue.
Now I can continue. That was BCAT. If we go up, which is a fun thing to do, this is actually called the JLP, and it is a Japanese logistics basically module, and it gets this storage area for Japanese equipment and U.S. equipment too. And it's really actually quite nice in here. It's one of the quietest places on station. But it has good storage, nice place to be. And our little, if you can't look out the cupola and you want to see Earth, you can come in here and get your little view of Earth. And these are actually kind of interesting. If you notice this right here, we call this a bungee jail. And what we do is we can put things behind these bungees and it stays up there. We don't have to really keep them contained or strapped in. They're contained in the bungee jail. We'll do that for different objects in different places. It works quite well and easy to use.
Where's your bag with all the metal in it? Is that still up here?
No, it's gone. Yeah, that would be a good thing to show, but we moved that thing. It has basically a bag big full of metal that makes some nice chime sounds. If we just had some wind to blow the chimes, it'd be really great.
Hey, you know what? Come back up and let me go to the front of the gem, and you can do your.
Oh, okay. Sounds good. I'll show you the dismount. Out of the
JLP dismount.
Yes, exactly.
Just remember, you got an SSU down here.
Thank you. You ready?
Give me 1 more minute. Swanee has perfected this over time. We'll see if he can pull it off. Okay.
Alright. The dismount. Ah, he missed it.
That was still pretty good. Well done, sir.
Didn't stick the landing. But that's the JLP dismount we like to do when we come out of the JLP. As you notice, it's kind of fun to move around up on station. So that's the Japanese portion. Again, it's a great lab. We really like it. It's one of the cleanest places on station to work, and it's always fun to work there. Try to get there. This will get part of it.
Oh, and explain what the green dots are.
Okay. Yeah.
Yeah.
Okay, this is our, it's called a PCS. It's basically information on how the station systems are doing. But most important thing for us are the comm, what is available comm-wise. And this is what we have down. So when we look anywhere around this area, we can look over here and see if we have comm or not. And we have 4 different channels. Space your ground 1, 2, 3, and 4. As you can see, it's upside down, but that's just the way it happens to be here for us. But these are the prime 2 we use, and it's the most available. And then these are, if we have KU, we have these 2, and we can use those 2. And so it's comm's very important for us. We need to talk to the ground quite a bit. They help us out tremendously. They're the ones with all the real knowledge. Again, so we're just a glorified technician, which I'm qualified for that, just being a tech. And it's good for me. But it is still fun to be up here, no doubt about it. This is the accidental trip we can do. So now we're in Node 1 again, where we have our dinner, etc., our place to eat. But we're going to move farther aft, and when we go farther aft, we're going to head into the Russian segment. And you'll see a change. Notice, of course, how I guess the size of this and the sides and the way this U.S. side is built. It's quite a bit difference when you go into the Russian segment.
I'm going to try to do this backwards.
Yes. Now I was trying to go backwards, which is going to be a little difficult for him. We'll see how this turns out. First, you notice we're going through another PMA, which gets quite a bit smaller. We use this for stowage of our main items that we need on a daily basis, kind of like towels, etc., that we get. That's all stowed right in this area. We can grab them when we need them. So this is the first kind of, I would call a node area for the Russian segment. It's the FGB GA. And so what it is, we can continue that way, which goes back into the FGB and into the service module, or we can go nadir and down into the mini research module number 1. And this is also a little interesting aspect of it. Again, it gets really narrowed down in here for a module. So this is, they call it meme in Russian, that's the Russian acronym meme. But the idea here is there has some science in there. It's more of a storage area for them. They keep a lot of their stuff here. And if we continue on, that's the Soyuz that Tano and the rest of his crew came up on. And so that's where we saw out the cupola. That's where you go to get to that one right there, through that area right there. So that's where this is docked to on the meme 1. And so this is one of the newer modules for the Russians. It came up, I know STS-132 put this on, so it's not that old. And you can see it's actually still clean on the sides. As you look at some of the older Russian modules, you'll see that basically this is the pile Velcro right here on the sides. And it's great for sticking things to. However, though, it does get dirty and it's hard to clean. And you can probably see that later. Always advantages and disadvantages to everything. So now we'll head into the main part of the FGB.
If I can find it.
As you can see, these are the hatches that they use on the Russian side. And it's set up in a way, basically, because there's usually, when a Russian module comes, it's got a docking probe on it. It goes into these things and it latches onto. And so that's what you have to have a room for the docking probe to go into these things. So they're kind of have this set up on it. This is also for airflow through the Russian modules. You can see we have the ducts going through right here. And actually this one goes all the way over from the service module all the way into node 3. It's a long running hose that goes all the way across to keep the airflow all the way throughout Station 5. Now you can see in the FGB, this is actually where the Russians have their hygiene station, where they clean themselves up. They got their mirror, they got all their stuff right here, so this is where they do it. And we move back again. This is mostly, the FGB is all about storage. It has a bunch of US and Russian storage in here. So behind all these panels there is some equipment, but mostly storage. The containers here are all food. This is how the Russian food comes up in these containers. And this is their spare food that they're going to use later on. Okay, now we're going from the FGB into part of the service module, which is like the main living quarters for the Russian side. And this is their kind of, I call it, node area. PO is the name of it in Russian. And it has two different ways to go. If you go nadir, you go into the docking compartment and into a progress down that way. And you can see their Russian spacesuits. So this is what they did to the spacesuit about a week ago. And this is what they did it out of the docking compartment. It's actually their airlock. And if you go zenith, we go into the mini research module number 2, and that's where the progress that I came on is docked to. And this is where I have to stay when the Russians do a spacewalk, so I can't be separated from my Soyuz through closed hatches. And so to make sure they want to close that hatch, they're doing their spacewalks. So I have to be in here, so I'll always have an access to my Soyuz back this way. We'll go a little farther, we can at least go a little bit into the Soyuz. As you can tell, it gets narrower and narrower. The Soyuz is actually a pretty small vehicle. This is the roomy part of a Soyuz. And it's right here, and it's called the BO, which is basically a living compartment. And so this is where you could actually, there's a little bathroom there, container, you have a little bit of room here, but this is our spacesuits, and this is all the room we really have for a living module. And on the way up here, we unfortunately had to do the 2-day version to get to station versus the 6-hour version. And so we stayed basically in this size, 3 of us, for 2 days. And that was a little cozy. But we made it. That's the best part. It's done. Overall, though, you can see there's not much in this area. These are our launch and entry suits that we use. Are pressurized suits. And we can see real quickly. I bet you we can jump into, I can turn a light on and jump into that Soyuz real quick. Actually, I don't have my flashlight. I don't have my flashlight with me to find the switch.
But I think we do. And Air Force Times, good morning. This is Mission Control Houston. Please call the International Space Station for a voice check.
Station, this is the Air Force Times. How do you hear me?
We read you loud and clear. How do you hear us?
Great. This question is for all the astronauts. I'm wondering if you could tell me how your experience as Air Force and Navy pilots prepared you for this mission.
Well, this is Terry Virts, and I'm an Air Force pilot by background, and that was probably the most important training and formation and foundation that I had to be an astronaut. There's something about my experience as being a pilot that helps the way you think. You think in an operational manner. You learn how to prioritize what's important and what's not, and do things in the appropriate order when there's something that comes up out of the ordinary. And it also helps you to communicate when you don't have a long time and you have to get your point across quickly and clearly. And so being a pilot is probably the most important training. It's for sure the most important training that I've had and that we still do as astronauts. And all the astronauts have aviation training of some kind or other, even if they weren't military pilots. It's what we do in the astronaut office. And if you want an answer from all of us, I'll let Samantha and Butch are both Air Force and Navy pilots also, so I'll let Samantha add to that.
Great, thank you.
Yeah, I would say a number of things from my pilot training and background helped me. For sure, the the habit of dealing with complex machines and complex operational environments helps you a lot to, when you're flying to space and you're doing just that. You're part of a team. Everybody counts on you doing exactly what you were trained for at the right moment, following the procedures, taking the right decisions at the right time. And that's exactly what we train for as military pilots. And then just there's a general aspect of military life that I think teaches you perseverance, teamwork, putting the goals of the team ahead of your personal goals, self-discipline, all that kind of stuff I think helps you a lot in the astronaut job as well.
Well, going third, I don't have much to add to that. I'd say I'd echo everything they said, but as a naval aviator, same thing. Certainly, I think the one thing maybe they didn't mention that I would add is you're put in stressful situations when you're in training. Flying a jet aircraft, maybe not so terribly difficult, but when you start employing all the capabilities of that airframe and leading multiple airplanes in combat scenarios, that's very challenging, can be very stressful, and dealing with all those things, multitasking, is certainly something that helps you for this job right here, without a question.
Wonderful. And when is your next spacewalk, and how do you prepare for it?
Yeah, that's a great question, because that's what Butch and I are in the middle of doing right now, is preparing for it. Most recently, I just took the spacesuits and got them resized so that they fit me. Every spacesuit has different adjustments you can make on the arms and legs and gloves to fit the individual astronaut, and so we just went through that process. Yesterday, Butch was in there getting the water loops cleaned out, making sure the fans work. So every day for the next few weeks, there's different tasks that we're doing in terms of getting prepared for it. We have to get the tools all ready. We had to build up some tools for one of the greasing lubrication events we're going to do on the robotic arm outside. So there's a lot of preparation that goes into getting ready for the spacewalk. And Butch and I are going to be doing our 3 spacewalks, while Samantha has the most important job of getting us suited up and getting us back in and out of the spacesuits, which is a pretty big task in itself. So the 3 of us will be very busy getting ready for and executing those spacewalks.
And have you done a spacewalk prior, or will this be your first?
Yeah, I had the opportunity before Terry and Samantha got here in October to go outside, and truly amazing and thrilling. But one thing that I'll have to say is it's about 2%. Oh my goodness! Wow! Look at the sights. Look at all the beautiful the Earth below, and about 98% work. It's a lot of work in preparing to go outside. It's a lot of work while you're outside, and it's 5 hours in the suit thereabouts before you even open the hatch. And then you're 6 and a half hours outside, and then once you get back in, you've got to clean up the suit. You can't just go straight to bed. There's a lot of work, so it's a long day, a lot involved. Certainly something we look forward to, though. It'll be a good day.
Right. And can you describe what it feels like?
Almost impossible to describe. Almost impossible. I think the one comment I would make is that just realizing that you and whoever you're going out with, we never go alone. We always go in 2 or more. That you're the only people in the universe doing this unique thing and having this opportunity. It's quite humbling, actually, to be able to do it and to experience it. It truly is.
And if you have a minute, if you could talk a little bit, this question is also for everyone, any experiments you are currently doing aboard the space station?
Well, right now the space station is really a very, very busy microgravity laboratory. The Dragon spacecraft came up a couple of weeks ago, and it took up a lot of experiments that now we are running. So it happens very often, actually, that Butch, Terry, and I are all working in parallel on 3 different experiments, and there's comm going on space to ground on 3 different, completely different topics. I have personally worked on a lot of human physiology experiments. There is one called Drain Brain that studies the return of blood from the head towards the heart. There is another one which is called airway monitoring. Terry and I just did a session last week that studies, for the first time really in microgravity and in the space environments, what happens to our lungs and to the gas exchange in our lungs when we breathe. and one that's happening right here, actually, next to where we are now, which is dealing with fruit flies. And it's actually very interesting, a multi-generation experiment. So we're actually breeding several generations of fruit flies, and then, some frozen samples of the different generations will go back to Earth on Dragon, and scientists on the ground can examine them. And something similar I'm actually doing with the Japanese experiments on worms. And in that case, we're also actually breeding several generations of those and see how adaptation to spaceflight actually gets transmitted from one generation to the next. So very exciting science, and a lot more, of course, but I don't want to take up all the time here.
Okay. Thank you very much.
Would you like more science? Because we can certainly go on. There's a lot of stuff going on. Actually, if I could turn that camera around, you'd see a pink Columbus module on the other end of the station, and we're growing plants there, and the light that's used for the plant growth is pink, so it looks pretty cool, especially at night when you turn all the other lights off. Today, my experiment of the day is working on Robonaut. It's a big humanoid type of robot that we have that hopefully eventually we'll be able to go outside and do some of the spacewalking tasks for us. But right now he just got legs, so today is the big day that he's going to be able to move his legs for the first time. And I've been working on an experiment called CSLM is the acronym. It's a material science experiment where they melt and mix different metal alloys and look at the process of cooling the alloys down. And so there's like Samantha said, every day it's a different experiment, and there's lots and lots of it.
Thank you.
Station, this is Houston ACR. That concludes the Air Force Times portion of the event. Please stand by for a voice check from the Houston Chronicle.
Station, this is the Houston Chronicle. How do you hear me?
We've got you loud and clear. How do you hear us?
I hear you guys just fine. Thanks so much for making the time today. There was a lot of excitement this week about the Dragon and CST-100. I know you guys have had a visit from the Dragon up there. How important is it, do you think, for the station to have redundancy and the ability to get you guys up and down to space?
Well, it's absolutely critical. Without a vehicle to get here, obviously the space station would be in pretty bad shape. Thankfully for us, we all came here on the Soyuz, which was a great ride. It was fun, and it's a very reliable and good spacecraft, but it's going to be really good to have a spaceship launching from Florida, from America again, and Boeing and SpaceX are the two contractors who won that contract. And as you know, there was a press conference just the other day with our administrator and many others. And so there's definitely a big effort and focus from NASA right now to get a capability to launch humans from Florida, from America, on the NASA spacecraft with Boeing and SpaceX. And we'll also be coming on the Soyuz also. So in the future, we'll actually have 3 different ways to get here. So that redundancy is an important part of it also.
I see. Samantha, my daughter wanted me, my 7-year-old daughter wanted me to ask you a question. She was wondering if it was scary in space.
Terry has something to say about that.
Well, if you had to live with me and Butch, yes, it's very scary in space. Every morning she has to look at us.
Jokes apart, no, I don't think it's scary. I enjoy a lot being up here. It's very interesting and challenging work. It's a great working environment. It's a great living environment. It's a privilege to be up here, and it's also a lot of fun. So I hope that your daughter, on the contrary, will maybe try and get to space herself one day.
I think she'd like to go to Mars one day, so we'll see about that. Obviously, the other big news down here this week is everyone's getting excited for the Super Bowl, and I know there's a couple of football fans up there. Do you guys have plans to watch the game? Are you going to be able to watch it live? Will you have traditional Super Bowl snacks, or how are you going to watch the game?
Yeah, regrettably, our bedtime, or at least my bedtime, is quite early, and the game actually comes on in the middle of the night. But I am an early riser, so I think that I get up usually around 4:30, so I think I might be able to watch the end of it. I don't know about these guys here. I'll let them speak for themselves. But I look forward to at least watching the end and seeing the outcome. And I might throw something on the grill just for myself as well.
Terry, a few days ago, you tweeted a picture of yourself, I guess, in a J.J. Watt shirt. Greatest football player on earth. I think we can all agree about that. In Houston, is Butch the greatest football player in space, given his experience at Tennessee Tech?
I think that's probably safe to say. Yeah, Miss Butch here. He was a college football player in space, and it's. Samantha is the greatest European football player, like in soccer, as we call it. But yes,
yeah.
But yeah, we enjoy that, and whenever we do a PR with different events, we always get a football out and use that to demonstrate the zero gravity, floating.
Have you guys
but I'm sure it's not only in Houston. I think most people can agree that J.J. Watt is the greatest football player, not only on Earth, but probably in the whole universe.
So in a few months, Scott Kelly is going to launch the space station for a 1-year mission. Butch has been up there for a couple months longer than Terry and Samantha, but y'all been up there a few months. How much do each of you think that a 1-year mission, how much of a challenge is that going to be, from a health standpoint, from a mental health standpoint, for Scott?
I don't foresee anything from a health standpoint necessarily. Scott's kind of a gym rat. He likes getting in and working out and doing those type of things, and it's an absolute necessity up here to keep yourself physically fit, to prepare yourself for the return back to Earth. And I think Scott will do that and take care of that without issue. I think one of the things that is difficult is it is concentration all day, every day. It's so much at stake up here, so many science projects, so many experiments, so many everything that people put a lot of effort into for literally for decades. And to be in charge of that, have those things in your hands, you want to make sure you get it right. So it's a lot of concentration. And over the long haul, that can wear on you. So I think that's one thing that they are aware of. They got some plans in to give a couple extra days off as the time goes on. And I think that's probably really smart.
He mentioned that, after about 4 months, he was ready to come home the last time. Have you reached that point, Butch, where you're kind of ready to come home, that 4 months is about right? Or are you still enjoying yourself and wish you could stay up there a lot longer?
I will answer that truthfully. I am not ready to come home. I would love to pipe my family up here and share some time with them, but I don't have the 4-month doldrums at all. I'm enjoying myself. They've kept us busy, interacting with the ground. The different control centers around the globe has been fun. We've tried to make it fun, have some laughs, have some good times. We kind of keep it light up here as well, and it's really an enjoyable place and such a unique environment. 4 months is not too long or long enough. I think 6 may be about right. We'll see. I'll let you know in a couple of months. But right now, I'm energetic and having a good time.
Well, I'm glad to hear that. So Terry and Samantha have both been sending back some great pictures from the planet. Obviously, you guys have been very excited about what you've seen. I'm interested, sort of from each of you, what the coolest thing you've seen in space in the time you've been up there so far.
That's a really hard question to answer because there's so many cool things. It's hard to rank one above the other. I guess for me, one thing, the sunrises and sunsets is probably my favorite, but the one picture that stands out is early in the mission, we were flying over northern Europe at night when there was some aurora, and I got some pretty amazing shots of England and France and Ireland with aurora in the distance, and one night there was a big storm there, so you could see lightning going off. So that's one out of many things that stands out to me.
From my point of view, I mean, what really always triggers a special emotion for me is when we fly over over Europe, but from a special perspective, I really enjoy those passes where we kind of fly over Gibraltar and onto the Mediterranean. There is something that has a special emotional connection. I think it's all the history that I relate to and the culture, and I don't know, it always resonates with me a lot. From a visual point of view, I guess I will just throw out the last thing that really impressed me that I saw yesterday. Actually, two of them. One was last week. For the first time, I had some night passes over, I guess, the Thailand area, and those like parts of the sea were like totally full of very, very bright green dots that I understand are fishing boats, and that was just so impressive. I mean, so many of them and so bright. It was an incredible sight. And that's something I saw just yesterday for the first time, which was like an aurora, and we've seen auroras multiple times, but this one was like the blue stripe, the really bright blue stripes that comes up on the earth limb when the sun rises. It kind of touched the aurora. So I had this incredible blue turning over into this incredible green of the aurora, and I had never seen that. So it was really amazing to see that.
Without question, I mean, like they said, look, the views out the window are magnificent. There's no way you could pick one, at least I can't, over the other. But without question, the memory I think I will take back is when Terry and Samantha arrived. I've been here 2 months, and when they came in, the looks on their faces, and watching Samantha, who's a first-time flyer, finally get to a window that she could see down towards the earth and watch her expression and the things that she's trying to describe I saw take place was just thrilling to watch. It was truly amazing. It was neat.
That's very cool. So
I'll add one more thing. Last night we had a chance to, just real quick, last night we had a chance to fly over the east coast of the U.S., which was a beautiful pass. I got some great shots of it, but it was the blizzard, so you could see Atlanta, D.C., Baltimore, New York, and then it was getting cloudier and cloudier, and you could see a hurricane there. It looks like a hurricane just off the coast of Boston. That was pretty amazing to know how many people down there in America are being affected, and then to be able to see it in the moonlight, because whenever the moon shines, you can see clouds, not like daytime, but you can definitely see them. That was pretty cool. Sorry, go ahead.
No problem. We're running out of time, so just a final quick question. Maybe one of y'all could describe the condition of the station. It's been up there now. It'll be 15 years inhabited later this year, and it's got a lifetime of 2024, maybe 2028. How would you describe it? Is it a well-worn house? Does it have the new car feel? Is it a clunker? How would you characterize it?
Well, the station, I think, overall is in great shape. It's in amazingly good shape for as long as it's been here. Module by module, it's different as far as the age and how new it is. Here in the Japanese module, it's like a new car in here. Everything looks brand new, and it's really kept up well. Node 1 is kind of our eating area. It was the very first American module that got launched, so that is definitely has a used car feel, not a new car feel. The American segment modules are different than the Russian segment modules, but overall, on both segments, I think it's in great shape. It requires a lot of effort. We have to constantly clean it and make sure we keep it in good shape, because, like with time, like anything, it would get worn out. But we spend a lot of time cleaning it, and we get a lot of spare parts that we can replace things with, and it's in great shape.
Station, this is Houston ACR. That concludes the event. Thank you.
Great to see you, Scott. It's hard to believe, but your one-year mission is drawing to a close. It's certainly been an eventful year for you and Mikhail Kornienko. And in looking back, what would you consider to be the most important accomplishments of this year in space, and perhaps the high and low points for you personally?
Our time here has demonstrated not only the capability for us to stay in space for a long time and to do well, but also the capability of the ground teams to support us and the systems that keep us alive and the resupply, and do this in a way that is forward thinking towards a potential flight to Mars.
This one-year mission was all about gathering very important biomedical data in that regard. Do you consider yourself and Mikhail pathfinders of sorts?
Sure. I guess you could use that term, but I think we all are. All the crew members over the last 15 years and even those that came before that. flying in space is a process. Exploring space is a process that you take step by step.
Scott, your career has spanned missions to service the Hubble Space Telescope. You commanded the flight of Barbara Morgan, in which she fulfilled the legacy of the Teacher in Space program, and you've conducted groundbreaking work on the International Space Station. How would you sum up your contribution to human spaceflight and ultimately the legacy you will leave after you return to Earth?
I've been really fortunate, like you mentioned, to have a spaceflight career that has had some variety to it, like you mentioned.
Looking ahead to landing, this will be your second return from the International Space Station in a Soyuz spacecraft. What are you looking forward to the most that was new to you 5 years ago during your first descent back to the planet?
The Soyuz is a pretty exciting ride back to Earth, no question about it. And, people that have flown in it previously will try to prepare you for it, but I think nothing really can until you've actually, been there yourself and experienced it. It's it's definitely an eye opener, and once you get past the initial shock of the drogue chute opening and all the pyrotechnics of various firing for various reasons, certainly the coming through the atmosphere or into the atmosphere, the plasma that's right next to your head versus feet in front of you in the space shuttle, it definitely gets your attention. It's so much fun for me that I had said, after my last flight, that if I would have, hated being in space for 6 months, I would have done it all over again just for that last 20 minutes in the Soyuz. It's that type of an experience.
Scott, the inevitable question when you touch down in Kazakhstan, what will be the first things you'll want to do, the first foods you'll want to eat, your thoughts as you emerge from a year aboard a confined environment?
It's interesting. I look forward to like fresh food, like a salad, believe it or not, stuff like that. But specific things is not as important as like the experience. I actually look forward to sitting at a table and just relaxing and having a meal with friends and family when you don't have to worry about your spoon or your fork or your food floating away and dealing with the overhead of that. So it's more the that kind of experience that I'm looking through as far as food is concerned. It's more of the more the experience and what I've actually not had to be able to eat up here or could get on Earth. The other things I'm looking forward to is seeing the sky from below and air that is fresh and a breeze and the sun on my face, running water, those kind of things, people.
And finally, Scott, without a doubt, this mission will take a prominent place in the history books when it's complete. From your perspective, what do you think will be the touchstone, the history-making moment, the legacy of this one-year mission?
It's hard for me to say right now because I think a lot of what we're doing here is because of the science. So I'm hopeful, and I think a lot of other people are, is that we're gonna learn a lot of information that will help us eventually, continue our path towards Mars. Misha and I are only, one data point really, or 2 data points, and anyone who's a scientist is going to tell you, you need a lot more numbers to draw specific conclusions. But I'm hoping what we find are areas that we need to investigate further. And we could say that, after so many months, we've seen this thing from a, physiological or psychological aspect, and we need to take a much closer look at this, before we travel further beyond low Earth orbit for longer periods of time.
Station, this is Houston ACR. That concludes the event. Thank you.
Thank you, JSC Public Affairs. Station, we are now resuming operational audio communications. Hi, I'm NASA astronaut Kjell Lindgren, and I just returned from 5 months on the International Space Station as a flight engineer on Expedition 44 and 45. I'm standing here at Johnson Space Center in Houston, Texas, and I've got some questions from kids in kindergarten coming from an iPad. So let's take a listen and see if I can answer these questions.
How do you know whether when to sleep? Because you don't know when it's night or daytime, because you're not on the Earth.
Well, that's a great question. You know, when we're in orbit, we're actually going around the Earth every 90 minutes. So we see 16 sunrises and sunsets. So our clock on the International Space Station is actually synchronized with Greenwich Mean Time. And we have a schedule that tells us at 6 o'clock in the morning it's time to get up and when it's time to go to sleep. And that way all the control centers around the world know what to expect, know when we're available for work and when not to bother us.
How does the space station not float away?
And that's because gravity is still working in space. We call it, weightlessness, or we call it zero G, but that's not entirely true. Gravity is actually what's holding the space station in orbit around the Earth. The space station is traveling so fast horizontally that it is missing the Earth as it goes around. It's just kind of curving in the Earth as it's flying around.
Have you seen an alien? Because I really want to see a picture of one.
I have not seen an alien space, but what I have seen was the aurora. On the Earth, you just kind of see it over the horizon, but in space, that green light was swirling like an active fog, and it was absolutely beautiful and one of my favorite sights during my mission.
Is there any aliens on the moon, too?
I have no idea. I don't think so. I didn't get to go to the moon, so I didn't get to investigate.
My question is, what do you eat on a space station? Thank you.
Most of our food is prepackaged and pre-prepared, so it comes in little bags that have to be heated up, or it comes dehydrated and needs to be rehydrated with hot or cold water. We do have cargo vehicles that are bringing food, water, and other supplies up to the space station to replenish the supply up there. One of my crew members was Japanese astronaut Kimiya Yui. I would often try to trade with him so that I could get some of his rice and pork curry. So having tasty food on the space station is really important. I would used to make cheeseburgers out of rehydrated beef patties, cheddar cheese spread, and then a tortilla and putting some mustard and ketchup on there. And that was kind of a faux cheeseburger that I enjoyed having on a weekend.
What is it like to walk in space?
Well, walking in space, there's two aspects to that. When we're inside the space station, we don't actually even walk, we float. And so we actually use our hands quite a bit to move ourselves around. Now to walk outside the space station, we will put on that big puffy white suit. It'll be pressurized inside, so it's giving us oxygen. It's removing the bad gases like carbon dioxide. It's controlling the temperature and provides us really a mini spaceship to be inside of while we're outside doing repairs or installing equipment. And that is an amazing experience to get to see the Earth and the space station from the outside, just separated by one panel of plastic. Thank you for your questions.
Station, this is WTOP Radio. How do you hear me?
We've got you loud and clear. Welcome on board the International Space Station.
Wow, this is really cool. This has not been done before. We are talking live here on WTOP with the International Space Station, and we say hello to Commander Terry Virts, now in command. Congratulations, Commander. We are happy to hear that you are from Maryland. You're a local guy.
Well, thanks. I appreciate it. And I am a local, born and raised in Maryland. And hello to all the folks down there in Maryland and D.C. and Virginia. I've been watching. We take a look whenever we have a pass, and it looks like it's been a pretty cold and white winter so far.
We are watching you on NASA TV, and we're streaming it on our website at WTOP.com. And it's really wonderful to talk to you, and also to flight engineer Samantha Cristoforetti, who joins us. She's an Italian astronaut. Welcome to you as well, and thank you for talking with us.
Yeah, absolutely. Thanks for having us. It's wonderful to be here.
Great to hear from you both. Terry, we know this is not your first mission on the space station. We want to know how has it changed over time? Does it get easier for you? Tell us about it.
Well, living here in space absolutely gets easier. The first few weeks that you're here, your body's still getting used to weightlessness. you're still learning how to float and how to move around, and you're learning the space station where things are located. And so the first few weeks can definitely be an adjustment period. But then it seems like somewhere between the 1 and 2 month period, you kind of hit your stride. You are adapted. You understand how to float. And there was one day I was actually trying to remember what gravity felt like. It's weird that your body adjusts so completely to being weightless, but it's a pretty cool process.
We have a lot of questions, especially from school kids who are listening in their classrooms this morning. In fact, Mrs. Balzar's 5th grade class, Andrew, asked, how do you sleep at night if every 45 minutes the sun rises and sets?
Well, Andrew, that's a great question, and luckily we don't have a window in our crew quarters where we sleep, so we shut the door, turn off the lights, and in our small crew quarters where our sleeping bag is, there's no light, so your body just thinks it's dark and thinks it's time to sleep. And I actually sleep really well. Oftentimes it's a busy day, so you don't get a large amount of sleep, but when I am asleep, I sleep very well, thankfully, because we close the windows and don't see any sunlight.
As you can imagine, we get a lot of questions about the food that you are eating. I know that there are cargo supplies that bring you fresh food every so often. What do you get to eat? Do you get to have some of your favorite foods? Tell us about what you have and how often do you get fresh food?
Terry and I are very different in terms of taste and the stuff we like to eat. But up here, we definitely both have been enjoying the few times that we have received fresh food. And that really happens whenever there is a new cargo vehicle that comes up here. So that happened early in our mission when a Progress vehicle came. And then in last January, we had a Dragon arriving and then a Progress again. Next week, we'll have a Soyuz, although I don't think there's space for food for fresh food in the Soyuz. But we'll definitely get some more fresh food coming up in the next weeks when the next Dragon will come. And the reason is that we do not have a fridge. We have a little refrigerator up here, but it's not enough to keep fresh food for a long time. So most of the food that we eat usually is thermally stabilized so that it can be shelf stable for a long time and we can keep it stored in here for months or even over a year. Or it's dehydrated, and so we plug it into our water dispenser. We plug the pouch into the water dispenser, and magically, with add in the water, it turns into food that we would recognize. And there is a great variety of food for all tastes and flavors.
Commander Wirtz, we have some questions from students at Oakland Mills Middle School, which I think is a familiar name to you. One of the questions is from one of the kids who's asking about being away from your family for so long. And I guess for both of you, how do you deal with being away, and are you able to communicate with them?
Well, that's a great question. Yes, Oakland Mills. I'm a Scorpion and graduated from there in 1985. Had a great time there. What an awesome place. But it is probably the toughest thing is being separated from your family, not only for the 6 months here that we're in space, but also for the several years beforehand that we were in training. We were gone a lot. And so it's tough. They're the real heroes. Everybody sees the astronauts in space and wants to talk to us, but it's the families that provide us support that allow us to do this. And they're the real heroes in that. That's a great question.
Commander Wirtz, we have enjoyed the many pictures of the baseball fields that you have been sending back. And so a number of folks, we know you are from Maryland, but I have been told to ask, are you a Nats fan or an Orioles fan?
Samantha says she can answer that one. She's become a baseball expert. But I'll tell you, what I'm rooting for is for the Orioles and the Nationals to be playing at the end of October this year. That's what I'd really love to see is a Game 7 between those guys right around Halloween time. And with the Nationals pitching staff this year, it definitely looks like they may be playing late in October. And with the Orioles coming off that 96-win season, they have a great shot at it too. So, of course, when I grew up, it was in the 70s and 80s, and the Orioles were going to the World Series and playoffs all the time. So I'm a homegrown, lifelong Orioles fan for sure.
We've got a few questions for you guys By the way, that was a good political answer.
That's a great
Not only
answer,
a commander, but a politician.
It's a great answer.
From the Gan Anavim kindergarten class in the Jewish Primary Day School, kids are studying the solar system there and space exploration, and they want to know, I guess, from each of you, how long does it take to train to become an astronaut? And tell us a little bit about what you're seeing up there. How beautiful are the galaxies, and what are the colors like?
In a way, you train all of your life to become an astronaut because before you can actually train to go to space, you need to be selected as an astronaut by a space agency, like NASA in the case of Terry, or the European Space Agency in my case. And to be ready to be a valid candidate at some point of your career in your life, you really have to start working at it when you are, in school already, and you're learning your basic math and writing and science, and then you go on to college. And most astronauts have some kind of technical or scientific background. Many of us are military pilots, so you kind of start on your career, and you try to be really good at it. And the key, of course, is to be passionate about what you do. And then eventually, one day, you'll hopefully be a good candidate to become an astronaut. And then, before you can actually come on the International Space Station, you have to train specifically for several more years. And in terms of what we see and what the view is up here, we are not really equipped for astronomical observation. The big windows that we have that are on the cupola actually look down towards the Earth. So that's our biggest spectacle. The greatest views that we have are mainly from the Earth. Just seeing the continents and the oceans and the glaciers and the mountains and all the different colors and textures. All of that is just magnificent, and it's ever changing and always a surprise. Of course, we also do see the stars, and sometimes really beautiful phenomena. Like right now, I was seeing one, auroras. Now we're seeing the southern lights, which are even more impressive than the northern lights that we used to see earlier. They're like three-dimensional. You almost like fly through them. So it's just beautiful. And then, of course, as you mentioned before, 16 times a day we're treated to probably the best show of nature, which is the sunrise and the sunsets on the Earth's horizon.
Amazing. Several students have asked the question about your free time. What do you do to pass the time, and do you become concerned about hitting a wall in the space station, passing the time?
That's a good question. And to be honest, I think for our first 4 months here in space, we haven't had a lot of free time. The weekends are generally, we don't have as much scheduled work, but it seems like there's always something to do. And 2 days ago, our crewmates came back to Earth on a Soyuz, and we had yesterday off as a day to sleep shift to get our schedule back normal. And that was really nice to have some time off, make some phone calls home, and go through some emails and just rest for a day. But it seems like most days, even on the weekends, there's always something to do. So we try and pace ourselves, and 6 months seems to be a pretty good time. Folks are able to work at a really good pace for 6 months, and then there comes a time when it's time to go back to Earth. But we're not there. I think we're definitely enjoying our time here, and it still feels like there's a lot we want to get done in our remaining 2 months.
Well, that is just incredible information with Commander Terry Virts in command of the space station from Columbia, Maryland, also with flight engineer Samantha Cristoforetti speaking to us aboard the International Space Station here on WTOP.
Thank you both for taking the time. We really appreciate it. This was an unprecedented opportunity for us, and we appreciate the work that you're doing. Thank you very much.
Thank you to both of you.
Thank you. Thank you. It was great talking to y'all, and hopefully I'll be back to Earth in time for that Orioles Nationals World Series.
Station, this is Houston ACR. That concludes the WTOP radio portion of the event. Please stand by for a voice check from Euro News.
Station, this is Euro News. How do you hear me?
We hear you. It's a little bit soft, but we can hear you.
Okay. Hi, Terry. Buongiorno, Samantha. Thank you very much for joining us on Euronews. I would like to start by asking how you feel about the other 3 crew members returning to Earth. As the next crew will arrive at the end of March, do you feel a bit lonely up there in space?
You know, it was sad seeing those guys leave. We were together for 4 months. They're very good friends, and we really enjoyed our time together. So it was sad seeing them leave. We're not too lonely, though. We have me, Samantha, and Anton are together now. And this is an interesting 2-week time where we'll have the space station to ourselves before our next crew arrives. But I do want to say happy birthday to Sasha. Today's his birthday. Alexander Samokutyaev, happy birthday. С днем рождения.
In the first 4 months of your mission, you have carried out some scientific experiments. Samantha, could you tell us more about this and explain the importance of these tests?
Yes, of course, scientific research is the main reason why we are up here on the International Space Station. The space station is an outstanding laboratory that allows us to do research in this very special condition, which is microgravity or weightlessness, which is very intriguing in many scientific fields because by doing scientific observations in microgravity, you can observe and measure and quantify phenomena that otherwise you would not be able, maybe not even to notice, and certainly not to study in detail in the presence of the effects of gravity on Earth. And some of those fields are human science, of course, biology, human physiology, but also material science, fluid physics, and of course the space station is also a platform for some experiments that are actually observations of the universe. I've done a lot of things in the last few months, so it's going to be difficult to name them all. But I can mention the few things that I have been working on recently and I will be working on soon, which are 2 European Space Agency experiments, airway monitoring and triple looks. And both of them actually have been a little bit troublesome. And I actually like to say this because, you don't want to give the impression that in science everything works right off the bat and immediately. Sometimes it is hard. It takes several trials. It takes a little bit of trial and error. It takes adjustments. It takes learning. And that has definitely been the case, for example, on this experiment airway monitoring, which is a very intriguing scientific protocol that for the first time is going to study how the gaseous exchange in the lungs is affected by both weightlessness, microgravity, and even reduced pressure. Actually, Terry and I were locked up in the airlock for several hours at reduced pressure to do some of those measurements. And then one which is going to come up as soon as we have fixed some issues we're having with the BioLab rack is triple looks, which is another intriguing scientific protocol which is aimed at studying the effect of weightlessness on the immune system, on the behavior of some specific immune cells that are involved whenever our body fights disease.
Terry, another goal of this mission was to prepare the station for the arrival of future private spaceships. For NASA, it will mean once again having direct access to space. How important will it be having a partnership with private companies for space exploration?
Well, it's been a big part of our mission so far, both doing spacewalks and doing work inside to get ready for the future vehicles that will be coming to the space station. And it's very important for NASA, our way forward, the way that we're going to launch astronauts from Florida once again to the space station is going to be on both a Boeing capsule and a SpaceX capsule, starting sometime in the next probably 2 years, and we're really looking forward to that. It's a important part of the space station program. It's an important logistical thing that needs to be solved in order to get people to the station and back, so it's very important.
And what comes after the International Space Station once its mission is over? How do we ensure the presence of humans in space?
Well, that's a great question. The plan that NASA has is to build a rocket called SLS, which is a heavy lift rocket. It's something that is much bigger than what we have today, and it will be able to launch the Orion capsule with humans on board, as well as landers or other components to destinations beyond Earth orbit. Right now, we only can fly in Earth orbit. That's the farthest that we can go. And this new system that we're building is going to allow us to go beyond and hopefully take humans into the solar system to explore. So the moon, Mars, asteroids, there's a lot of destinations that we could go to, and we're building these building block components in order to allow us to do that eventually.
Samantha, according to a recent survey based on research on internet, you are the most popular Italian woman in the world, ahead of Monica Bellucci and Laura Pausini. Does it mean that science may be more attractive than showbiz?
Your haircut.
Well, I'm not sure that was a survey conducted according to the most scientific and statistical criteria, but just to take it for the fun that I'm sure it was meant to be. I'm certainly happy that a person like me, who is really nobody as a person, but has the privilege of being the representative of something really special, which is the space station program, having this incredible technological, scientific achievement, which is really a testament of what humanity can achieve when we decide to work together and put together our best minds all over the world to do something which is really amazing. And of course, it's a testament to the scientific research that is conducted here and all the technological development, which is really just ensuring that we do all the steps that are necessary for further exploration in the future. So in that sense, of course, I am happy that about the outcome of this survey, which again I'm sure it was meant in good fun.
Okay, just a quick question sent in by our social media followers. In around 2 months, you will come back to Earth. What did you guys miss the most during your stay in space?
Well, that's a great question. Living here is very pleasant. We have everything that we need. The food is good. We're here with good friends, and so life here in space is pretty good. The thing I think we miss the most is people. Missing our families on Earth, missing our friends, getting back to see folks. That's the thing that you really miss more than anything. Another thing that I'll throw out there, we were just talking about this, is weather. We don't have weather here, and we were just talking about rain and snow and what it's like to have on Earth. So that is something that I miss, and I'm looking forward to experiencing a little bit of weather. Hopefully a lot of sun and warmth, but other rain and snow and that kind of stuff is something that we don't get here.
Okay, to finish, I would like to ask how you remember on the station actor Leonard Nimoy, and was your interest in space inspired by Star Trek and Mr. Spock, just like so many people?
We're going to have to ask you to say that question again one more time, please.
I would like to ask how you remembered on the station actor Leonard Nimoy, and was your interest in space inspired by Star Trek and Mr. Spock?
Okay, now I understand. Yeah, thanks for the question. Definitely, I was as a big trekker growing up. I was really a big fan, and I do think that it has played a part in helping me to show me this path, to help me become aware that this is what I wanted to do. Become an astronaut, travel to space, and play a little bit my part in this human adventure of space exploration, which is just one long journey, and one day maybe, or I believe so, a Star Trek reality will become true. So I really felt like I had an obligation to honor Leonard Nimoy when he passed away recently.
Thank you very much for having been with us. Enjoy the rest of your mission, and just as Mr. Spock would have said, live long and prosper.
Thank you very much. I appreciate that. And hello to all the folks down there in Europe. We just had a beautiful pass over Europe this morning. It looked like a sunny day in a lot of places, and we'll see you back on Earth in a few months.
Station, this is Houston ACR. That concludes the event. Thank you.
As long as it goes in an arc, the string will stay taut. That has to do with the physics. Okay, here we go. I've got my yo-yo bag, and in my yo-yo bag I have a free-spinning, non-returning yo-yo. Okay, hear that? Okay, that's the sound of precision ball bearings. So here, spin a yo-yo. I'm going to do orbit the Earth. There we go, and it's orbiting slowly, but it's spinning fast. And then I'm going to do around the moon. Look at that. And then I'm going to do the tether assist. Now normally we'd call that man on the trapeze, but it won't catch. And so it just bounces off the string. And it's kind of like the tether technology we use for satellites and things. So I call that the tether assist. And let's see if I can get it to come back now. Ah, there we go. And because I'm in space, and I get to name these yo-yo tricks as I invent them. So I call this Shoot the Planets. And I'm spending more time training to fly the robotic arm so I can snag this little spacecraft coming up here in a week or so called Dragon. And I haven't been spending as much time as I should working on my yo-yo training. So I've been ignoring my yo-yo training. So it may take a couple of times to get this trick correct. And it just shows that I've got misplaced priorities. There we go. Oh, so far so good. Orbit the Earth. And so I'm keeping it moving in an arc. There's 2, there's 3. Oh, how about that? Let's see if I can get it to come back. Oh, okay. So now it's spinning really fast. We're going around. Oh, I like this. I'm going to do shoot the planets again. So there's that, and there's that. There. That was a good one. That's a keeper. Okay, now I call this the asteroid because it's basically uncontrolled. The string is limp and it's just bouncing back and forth. So this trick is the asteroid. You have to be careful because if it comes back in an uncontrolled way, it can end up hitting you in the head. And I call that the G-bonk. Another thing about yo-yos. There's a lot of physics involved in this, a lot of physics. Exchange of angular momentum with the yo-yo spinning, angular momentum of the yo-yo moving in an arc as a system, and then the linear momentum of it going in and out of the string. And then of course there's energy expenditure in this because you've got bearings and friction and drag with the air around it, and drag with the air is kind of small. So you have all of these neat pieces of physics working on this. And it's good to understand the physics of your recreational activities. So if you like doing yo-yos, you should read up about how they work, how the physics works. And it will benefit you in several ways. One way it'll benefit you is you'll be able to have some delightful conversations. You can impress people by talking about the physics of your yo-yo. And if you're a guy, just think you can impress the gals by talking about the physics of how your yo-yo works. And of course, there's going to be a class of gals that won't be interested in that, and you won't impress them, but then those are the kind you don't want to be around. And then if you're a gal and you're yo-yo, again, learn the physics, and when you talk about the physics of how the yo-yo works, in addition to doing your yo-yo tricks, you can impress the guys. And of course, there's going to be some guys that won't be impressed because they don't like physics. And you don't want to hang around those kind of guys anyway. But there's even a more important aspect of this. If you learn the physics of how the yo-yo works, and you can talk about that, that means you've learned a certain amount of physics. And when you learn a technical subject like physics, guess what? It helps you get a good job. And then, of course, when you have a good job, you can afford to buy these fancy yo-yos, and you can use your spare time then to do even more work with your yo-yos. So here we go. Let's see if we can do it again. So orbit the Earth, orbit the Moon, orbit the Moon again. There's the tether assist. Okay, tether assist. Shoot the planets and come back. Hot dog, look at that. Again, I'm going to try shoot the planets again. That's a string jam. Oh man, and it hurts your finger. I hate it when that happens. Let's see if I can get this. One of the neat things about video is that you can edit out all these fades when you goon it up, you know, and then you can make it look like you're a real yo-yo champion.
While our sense of touch isn't really affected in orbit, after about 2 months up, the bottoms of our feet start to get really soft, while the tops of our feet start to get raw and super sensitive. Why? It's because we don't walk on the soles of our feet, and instead the tops of our feet are used to hook around doorways and handrails and hold me up right now to keep me from bumping into things. Because without gravity, fluid shifts and collects in our head and upper body, causes facial swelling, nasal congestion, your sinuses never drain, so it makes it difficult to detect, the more subtle smells in microgravity. The burnt steak and gunpowder smell that many astronauts report in the airlock, that's one of the few smells you can smell strongly, but it's not exactly a spring garden. Eating in space is like eating with a head cold. You just can't taste very much. So because of this, a lot of our food tastes kind of bland. That's why we like especially spicy food here. Stuff that you might not normally eat on Earth, like shrimp cocktail with horseradish sauce. It's probably my all-time favorite, because it has a real bite and actually decongests your sinuses a little bit. Some astronauts on long-duration space flights have reported having blurred vision. And scientists think it may be caused by the extra fluids in our head, resulting in sort of a flattening of the eyeballs and maybe even swelling around the optic nerve, which creates a shift in our prescription, in our vision. And the swelling of the optic nerve seems to resolve over time, but the flattening of the back of the eye, we're not sure, but it doesn't appear to return to normal even after we return to Earth. Another strange effect is the sensation of seeing flashes of light when our eyes are closed. It's caused by cosmic rays that can be seen as bursts or stripes or even stars. And some astronauts are more sensitive than others, and they can detect them even in the daylight. Now everybody knows in space that no one can hear you scream, because sound can't travel through the vacuum of space. But inside the space station, we constantly hear the hum and the whir of the fans and the pumps and the machinery. And the ongoing noise of the space station can really take its toll, which gives us all the more reason maybe to play a little music and cut the monotony. So on that note, I'll see you out with a tune. Till next time.
Station, this is Houston. Are you ready for the event? Houston, are you ready for the event?
Houston, the International Space Station's ready for the event.
CTV Studios, this is Mission Control Houston. Please call station for a voice check.
Station, this is Canada AM host Beverly Thompson. How do you hear me?
Beverly and Canada AM, I hear you loud and clear. How do you hear me?
I can hear you very well, Commander Hadfield. Thank you so much for doing this.
It's a real pleasure. I've been lucky enough to visit with you folks several times, and to be able to talk to you today from this place doing these things is a real privilege.
Well, and it's so great for us to be able to catch up with you. You know, we do a lot of interviews all over the world. This is my first certainly doing one out of this world. I have to ask you to tell us kind of, you know, not where in the world you are, but literally, where are you in the International Space Station?
The International Space Station is enormous. I mean, it's a lot bigger than most people think. It's a bunch of laboratories bolted together. I'm currently in one of those laboratories. That's the universe just out the window. We're inside the Japanese laboratory. Just behind the camera is the European laboratory. The American laboratory is over there. The Russian segment is down there. And then all across it here, bigger than 5 hockey rinks, is the whole space station. It's a big place, and we're just in one little corner of it here right now with experiments all around me.
You know, and it's just, even though we know you're in weightlessness, it's still pretty funny to see a microphone just kind of sitting, floating around. I have to ask you, tell us how you spend your day, your average day there.
Average day in space, you wake up at 6 a.m. We live on Greenwich time. They had to kind of split the pain between Mission Control in Moscow and Mission Control in Houston. So they chose London, England, about halfway between. So we wake up at 6 a.m. London time. You have an hour and a half or so in the morning to get yourself ready, just like everybody does. Clean up. Go to the bathroom, which is a little intricate in space, make yourself some breakfast, read the day's plan. And then we have a meeting with all of the mission controls all around the world, where we talk to each of them. There's one in Europe, there's one in Montreal, there's one in Houston, Moscow, and Japan. And then once everyone's told us the important stuff for the day, then we work our way through experiments, fixing equipment, maintaining the vehicle, all the various things you might do. A couple breaks for meals. It's evening time. Oh, during the day we exercise 2 hours as well, because without fighting gravity, you could be really lazy. So even my microphone floats, as you say. So we exercise 2 hours a day, have dinner, and then you have about an hour and a half in the evening to try and catch up on personal things. Maybe look out the window, take some pictures, play a little guitar, talk to family, and then go to bed, get 6 or 7 hours sleep, and repeat. And we pretty much do that every day for the whole 6 months we're here.
And Commander, how are you feeling now that you've been up there as long as you have already, and you've got, you know, the rest of your time there for your 6 month tour? How do you physically feel now?
I completely feel adapted. I feel like a spaceling. It sounds weird. It's not a very common word, but I don't feel like an earthling. I mean, I can fly and float and turn upside down. I don't need to touch the floor. It's a whole new way to be, and at first it feels very strange, but now you don't even think about it. You're just, if you want to put something somewhere, you just let go of it, and you become graceful and elegant in weightlessness, maybe like a porpoise in the water, or a swallow in the air. And at first you're clumsy, you bump into things, but after a while it really feels natural. In fact, it's a big improvement on gravity. Nothing sags on your body, so it's gratifying when you're in your 50s, and it's a wonderful way to be able to fly and float and take advantage of this really rare experience. And that's just the physical side of things.
There's so many interesting things that you've been sharing with us, not the least of which we saw you making a peanut butter sandwich. Tell me about some of the, not the dangers, but some of the troubles or some of the things you have to be careful about with regard to eating.
You know, try eating a lunch sometime where you lie on your back and you make your whole lunch holding the food up in front of you, above you. You know, opening up a can, opening up anything, trying to use utensils where you can't set anything down, and everything that you open, there's nothing to keep it in the container. That's sort of what it's like. I just brought a can of typical food that we eat here. This is a white bean puree, and it's it's got a pull top, but of course, if it's a liquid inside, as soon as you open this, you're going to have a big ball of white bean puree floating around. So hopefully the manufacturer has thought to make everything sticky in there. And your fork, if you turn around, your spoon is gone. We can't really heat our food very well. Everything just comes like this, pre-made and pre-packaged. So we just have sort of a little, easy bake oven that we warm things up in. There's no real chiller for the water. So the food isn't really cold, and you can't make anything fresh, of course, because it's like being on a long voyage anywhere, a long sailing voyage where everything has to have a long shelf life. But we have dietitians and health specialists on Earth in Montreal with the Canadian Space Agency and at NASA and in Russia, and they really take good care of us. There's a big variety of food. It tastes good, and it's keeping us healthy. So even though it's a little tricky eating up here, as you saw in the peanut butter video, it's quite pleasant. It's something we look forward to, both just for the food, but also as a social get-together.
There's so much that is so fascinating about this mission, and you've been able to share all of it with us through social media, through taking pictures. Just yesterday, we saw a picture that you took of Mount Etna. Some of these images are just stunning. I don't know how you have time to do it, but you do it. You've got so many followers. Tell me, when you first saw this picture of Etna and you took it, what you thought.
Well, I get tremendous support from the ground. The Canadian Space Agency has a team of people that have been working on this flight for a couple of years, and they're doing a great job. My children as well, especially my son Evan, has been helping me, an old guy like me, understand social media. And with that whole team, we've really had a chance to include a lot of people in this. And so they send me information. I got a note saying that Mount Etna was erupting, and then the people at NASA also said, hey, here's a particular pass where the lighting might be good. And so I set the alarm on my watch here and went over to the window at the right time and grabbed the camera and tried to take some pictures. And it's, Beverly, it's sort of like almost a miracle when you're working away in what looks sort of like a building, and you float over to the window, like that one there, and you look outside, and you're transported. You're suddenly, there's the whole world in all of its curvature in front of you, and there's a volcano out of the world that is spewing ash and smoke and steam, and you float the big lens up in front of you and zoom in on it, and you can see how the energy from that volcano, from this great big Earth that we live on, is spewing the energy of the Earth up into the high atmosphere where it's being picked up by the jet stream and carried out over the Mediterranean. And we're going 8 kilometers a second. So we come up, you start getting your camera ready over Africa, and you come across the horizon, and there's Mount Etna, and you take pictures as it rolls by in front of you, and then the next thing you know, you're over the Black Sea and up and over Kazakhstan and gone. So it's phenomenal. And as you say, I'm working all day on all the science we're doing here, but at the same time, the distraction of what's out these windows and the lure of the magnificence of our own planet is a magnet that constantly pulls you away.
And it's such a lure for everybody here on Earth, and we've been watching with interest. You've been speaking to so many students and classes. They ask you great questions. It must be wonderful for you to be able to share and see the excitement that these kids share in your mission.
Yeah, when I was a kid growing up, it was the very start of space exploration back in the 60s and early 70s. And I was fascinated by it. I thought of all the things that are going on with our species and our history right now. This is something really new in the human experience, to be leaving our planet. And so I was really excited about it as a kid. And whenever somebody's taught me, I've always sort of felt that, well, now I have an obligation to try and share the privilege of things that I've learned with other young people, same as people did with me when I was little. And so I really, over the last 20 years as an astronaut, have spoken right across Canada and up in the Arctic, and trying to let people know the opportunities that are there. This is something that Canadians do. There's Canadian hardware on here. The Canadarm built this place. It's just on the outside. There's a Canadian science experiment looking at how tiny nanoparticles react, doing fundamental research right over here behind me. And all of this is going on. It's an opportunity for Canadians, Canadian universities, Canadian businesses. And so I'm the lucky guy who gets to be here. but I really consider it a vital part of my job not to keep this experience to myself, but to use every means that I can think of to try and share it, to try and let people see what we're doing up here and the fact that we are starting to leave our planet permanently for the first time in history. It's a pretty interesting stage, and now with the technology that's available to be able to immediately share a picture of Mount Etna or some random thought or some emotion that's going through, it really even makes it more accessible, and for me, more rewarding to be able to not just keep it to myself, but to be able to let people right across Canada share it.
And I guess we can add Canadian music to that because of your song and the Bare Naked Ladies, and the fact that students are going to be singing this song, your song, on Music Monday. What do you think of that?
I think it's tremendous. I went through of course, the Canadian school system. I had music teachers in elementary school and high school. Miss Soren, who taught me in high school, taught me how to read music and how to play musical instruments. And when we looked at this Coalition for Music Education right across Canada, they have a great program with Canadian schools, and we thought, why not participate in that? Invited Ed Robertson, who I'd known for years. The two of us wrote a song together, joined with a choir, the Gleeks from Wexford, and sang this song. And it really came off nicely. It's a song about exploration, about starting to leave the earth, about putting all that into personal perspective and what it means to us. And Ed and I really liked the song that we wrote, and it's going to be sung by schools. I mean, I invite all Canadians to listen to this song. You can see it through the Canadian Space Agency website and through Music Mondays and Coalition for Music Education. And it's going to be in schools across Canada on the first Monday in May, Music Mondays. I think it's the 6th of May. A song called Somebody Singing, ISS, International Space Station. And for me, music is fundamental to humanity. They've found musical instruments when we lived in caves 40,000 years ago. Of the few artifacts, the things that people made, they made musical instruments back then, before written history. It's an ancient necessity for humanity. And to be able to have a guitar up here, to be able to write and play music up here, to be able to then share it and have Canadians join in voice and song is just another wonderful way to try and help communicate not just the science, which is important, but also the art and the humanity of this experience. And I really hope lots of Canadians will have a chance to join in the music. Why not?
It's really great to see you holding that guitar. And with the weightlessness, when you play that guitar, does that feel different?
Oh, it sure does. It's the guitar, just kind of like this microphone. The guitar just floats in front of you, so you don't need a strap. But it is a little weird to fret up the neck because your arm doesn't weigh anything. So you kind of have to pay a little more attention when you're playing up and down the neck. You need to really think about where your hand's going. But fortunately, there's a Canadian guitar on board made out in Vancouver, and that was just a lucky coincidence to have a Canadian on board with a Canadian guitar. And in my spare time, I've been playing lots of Canadian folk songs, Stan Rogers and Gordon Lightfoot and M. Greiner and a bunch of music, and having a chance to play some songs that I've been writing and record music. It's just, it's not the main purpose of what we're here for, but having that as something to do in my spare time is something I do on Earth, and it's a wonderful facet of of actually living in space.
Yeah, I just love it. And, given the amount of space that you have for personal life, what other kinds of personal things did you bring with you? I mean, obviously you've got a guitar. What other kinds of things were important to you to have with you?
Well, I looked at this, of course, as sort of a very significant event within my life, within my family, my extended family's life. And so I invited, of course, each of my family members, brothers, sisters, children, my wife and parents, of course, and asked them if they would like me to bring something up for them. And we're very, very space limited. I came up and I helped. In fact, I was like the pilot of the Soyuz, the Russian rocket ship, spaceship that we flew up here. So in fact, everything I could bring had to fit in a package about as big as one of those little loaves of bread, and couldn't weigh more than 1.5 kilos. So just small things. But almost everybody has some small little maybe something that's historic to them or personal to them or important. And so I collected those from all my family, little, jewelry or maybe something from a grandparent, something that's been passed down through the generations, little things like that. My brother wrote a song, that I brought up the sheet music for, that type of stuff. And now I have that up here. And it's really nice actually to go through them one by one. Of course, I want to photograph with them, but to take them out and think about this is the embodiment of a friend or a history or a whole story, each one of them, and to float it weightless next to myself, snap the camera with the world in the background, not just knowing that this is an interesting photograph, but this is an encapsulation of humanity and time, looking at it, putting it back in the package and taking on another one. It's a personal but a really touching moment for me and a real joining moment with everybody that's important to me.
Wow, and you're so busy up there with the experiments that you've mentioned, and such a full day. You are about to take over command of the International Space Station. Are you still going to have time to do your tweets and your photographs and all of that we love?
You just can't deny it. And I mean, I could sleep longer, I guess, but that would be a waste. We have a very regimented life. We, in fact, have a schedule on a computer that moves in 1 minute increment. Our life is scheduled to 5 minute increments for the whole 5 months. But there's a little bit of gray space at the start of the day and the end of the day. And there's also a block where you're supposed to be asleep. And yes, I do. I take over to command what is, in effect, the world spaceship here in a couple weeks, which is just amazing for me to even contemplate that. I can accept the reality of it, but in my heart, it just still is kind of daunting and surreal. But I definitely need to address that role. Of course, my regular working day here, but at the same time, I'm not going to spend my evenings and spare time, watching movies or not being productive. That's not what people put me here for. It's definitely not what I want to do, and I'm in such a rare position on behalf of so many Canadians, so many of my coworkers, so many people, that I want to live this experience just as fully as I can, share it with Earth real time, but also absorb it as completely as I can so that I can reflect it back and reflect on it and let people know what it means to all of us, for the rest of my life. So yeah, I'll be busy, but this is a good place to be busy.
I know there's going to be a lot of things you're going to want to do, not the least of which is hug your family when you get back, but what would you look forward to being able to do once you're back on Earth?
It's a very quiet, austere environment here. Great people, super competent, undemanding, self-starting group of 6 humans that I'm up here with from all around the world. It's interesting. We grew up speaking different languages, very different cultures, people from Belarus and Russia and different places in the United States, and me from Canada. And yet, this little microcosm, we have a wonderful time working here, but it's also, somewhat monastic, and I'm very much looking forward just to the contact of being back on Earth, the noise and the tumult and the wind in your face, and being able to give someone a hug and just the regular messiness of life. I'm looking forward to that. I'm looking forward to, of course, we have all the compulsory things, but to relaxing, to getting back to our cottage in Canada and spending the time with my feet up, trying to put all this together and figure out, what it really means, and somehow fit it into the rest of my life, and try and really put it into context of everything else that's going on. So I think the debriefs, the rush of humanity, and then a chance to really reflect on it. There's all the trivial stuff of food that I want to eat or something, but in truth, it's the opportunity to really make the most of it that I'm looking forward to when the pace slows again.
Commander Hadfield, this has been such an incredible opportunity to speak with you. You've been such an inspiration. Continue to be. Best of luck and safe travels for the rest of your mission. Thank you.
Thank you very much. It's been a real pleasure to talk with you. Thanks for having me on. Bye.
The station, this is Houston ACR. That concludes the event. Thank you.
Thank Thank you, CTV Studios. Station, we are now resuming operational audio communications.
So here's a common question. Can you cry in space? Do tears work? Well, let's try it out. I can't cry on command, but I'm going to take some water, drinking water, put it in my eye just as if I was crying. Let's see what happens. Get myself nice and stable for you here. Here we go. So, just as if I started crying, my eye is full of tears. But you can see it just forms a ball on my eye. In fact, I can put more water in. And so if you keep crying, you just end up with a bigger and bigger ball of water in your eye. Until eventually it crosses across your nose and gets into your other eye, or evaporates, or maybe spreads over your cheek, or you grab a towel and dry it up. So yes, I've gotten things in my eye. Your eyes will definitely cry in space, but the big difference is tears don't fall. So grab a hanky.
So you guys went up there very fit. How does it feel as your body changes during weightlessness? And when do you think fat people will be able to go to space?
It's all of us have been lucky enough to fly before this long duration flight. I think everyone would agree that the process by which our bodies adapt to weightlessness, you can feel it. And you can see how your body is changing. It's really rapid for the first week or two, almost day to day, as the fluid shifts, as your balance system changes and relates to how you see things, how coordinated you are in weightlessness. You're pretty clumsy when you get up here, but after a while, maybe sort of like a young ape swinging through the jungle, reaching out for vines, we get used to it, and you get pretty graceful in weightlessness as you adapt. But it definitely takes time. We also lose a little weight, but mostly it's just water, because there's no fluids pooling in the lower part of our body that our body's constantly pumping up to our head. Our legs get really skinny up here because gravity's not pushing the fluids down to our legs. And to live on a space station, you have to pass a really hard physical, just because we can't afford to get sick up here. We really want to have healthy people. But we're trying to open the doors to space to everybody. That's the whole purpose of this, is figuring out how to safely get to space and back again. And just like early in aviation, at first it wasn't for everybody, and it was only a very select few could fly. And now, of course, pretty much anybody can fly anywhere around the world. And we're just in the early stages of that. We haven't invented everything we need to invent yet. But hopefully soon, everyone will be able to get this incredible experience that we're lucky enough to be part of. The question is, if you get a cloth dripping wet without gravity and you wring it out, what's going to happen? What will happen to a wrung out cloth? So, and had to use equipment that was here on board the space station. We may have the coolest washcloths ever here on the space station. I'm going to show you. Here's one of our washcloths. And it's compacted. It's put down into this little tiny hockey puck so that it saves space. But when you open up a hockey puck and you pull out your washcloth, this is the one I'm going to use for the experiment today. And so when you open up your hockey puck and turn it into a washcloth, it was compressed in a great big vise somewhere. Okay, so here's my washcloth, like a magic trick. And now I'm going to get this soaking wet, and then we're going to see what will happen when we wring it out. Meredith and Kendra suggested that I dip this in a bag, but bags don't hold water in space, so instead I filled a water bag. This has drinking water in it. And I'm going to squirt a bunch of water into this washcloth. Okay, so here's a soaking wet washcloth. Get the microphone so you can hear me while I'm talking. And now let's start wringing it out. It's really wet. It's becoming a tube of water. The water's all over my hands. In fact, it wrings out of the cloth into my hands. And if I let go of the cloth carefully, the water sort of has it stick to my hand. Okay, so the experiment worked beautifully. And the answer to the question is the water squeezes out of the cloth, and then because of the surface tension of the water, it actually runs along the surface of the cloth and then up into my hand, almost like you had Jell-O on your hands or gel on your hand, and it'll just stay there. Wonderful moisturizer on my hands. And the cloth doesn't really unravel itself. It just stays there floating like a dog's chew toy, soaking wet. Great experiment, worked perfectly. Meredith and Kendra, congratulations. Great idea.
All right. They may look like expensive abstract works of art, but these images are actually some of the breathtaking photos of our planet taken from space by Colonel Chris Hadfield. He's one of the most accomplished astronauts in history, and his new book reveals a visually stunning tour of Earth from his adventures aboard the International Space Station. It's called You Are Here, Around the World in 92 Minutes. Chris Hadfield, welcome back to Studio 57.
Thank you for the
First
invitation.
of all, thank you, because this is everybody's dream is to be able to see, I think, the world from outer space, these images. How many pictures did you take?
NASA doesn't give us any time to take pictures. They just assume the view out the window is going to be so compelling, you're just going to not be able to avoid it. And I took, when I should have been sleeping, I took about 45,000 pictures over half a year up there.
They have, a dozen cameras on board?
We have a big variety. Cameras don't last very long because of the radiation up there. It tends to destroy the little sensor in the back. So we keep cycling through. But yeah, we keep about 8 cameras by the big window in the belly of the space station.
How does this change you?
I think it gives you a real understanding of the world, not your own part of the world and then sort of a percolated view of the rest, but you see the whole thing sort of unanimously, uniformly, in 92 minutes, as it says on the book, around and around, and that really starts to seep into you the fact that we're all in this together.
You don't see the same shot over and over again because your orbit changes.
Yeah, our orbit stays fixed. It's sort of like a ball on a string, but the world turns underneath you like a gift. So every time you come around, you see something new. And we were there as we went halfway around the sun, so the seasons changed on the world. So it's like the world just revealed itself every time you came around with a new view.
I was interested that the most common request a person would make, take a shot of
my hometown. That delighted me. My son Evan sent me a note saying, Dad, ask everybody what they want you to take a picture of. So I asked, hey, everybody, and they said, my hometown. Well, but what was delightful about that was not just the narcissism, but the fact that people are proud of where they're from, but they also want to see how does that fit in, how do they look in perspective to the rest of the world, and that was really revealing to me.
Can you see, when you're in outer space, can you see the lights of Manhattan? Can you see at night a city that's lit up?
Oh yeah, the eastern seaboard of the U.S. is so distinctive. It's maybe even clearer than it is during the daytime because the big cities, as you come across D.C. and Philly, and there's a difference between day and night of the two. Yeah, you can see Central Park so clearly, and the naked eye does a much better job at low light than any camera does. So you can pick out the Statue of Liberty if it's lit up
and
out
how
there.
Many thousands of feet, tens of thousands of feet are you?
We're about 1.3 million feet up.
Yeah, 1.3 million, thank you.
About, 270 miles up or something like that, depends.
Yes. Asking, your favorites, but I think you saved the best for last. South America, the South America section is just page after page of mind-boggling.
And I think part of it is you don't fly across South America in airliners on the way to anywhere. You know, you're going somewhere and coming back. So for a lot of people that look in a book, they're not familiar with what that part of the world looks like from the air. And we crossed it thousands of times. The variety from the glaciers to the huge expanses of farmland, and then the dryness of Chile and the high salt pans up there. It's gorgeous.
And
it's
your
just beautiful.
Amazon.
Oh, and yeah, the Amazon also.
Would it be possible to, I mean, do we have a camera? It's 92 minutes that could give us just 92 minutes of what it looks like and what you could see from your eye?
We have that from the space station now, Charlie, but the difference is a person with a camera can be going, wow, look at that, or you catch a glimpse, a glint of the sun off something for just a second as it flashes by, or shadow is so important, a dawn picture. Like if you're looking at Manhattan, if you catch it at dawn, the tall buildings are actually shadowed on the river, or you can pick out the dunes of Australia with the colors, very much depending on the time of day. So the trained eye makes a big difference in not just recording the world, but actually seeing the world.
You're not a professional photographer, a trained photographer, but you produce almost fine art.
The people that trained me for years at NASA would despair for you to say I'm not a trained photographer. I'm definitely not a professional photographer. The world is so generous in its beauty, and you do your best to take pictures of it. It's just flat gorgeous to see.
So what did you think of the movie Gravity?
I enjoyed it.
Yeah. But I mean, what we saw, is that anything like?
The visuals.
Yeah, that's what I mean.
Yeah, they're the most compelling visuals of any space movie ever made. I've been out on 2 spacewalks, sort of like on the cover of the book, and that sense of not being on the world looking at the universe, but being in the universe with the world. That parallel, bottomless, huge, vast expanse. The movie, if you want to get some feel of what it's like, that movie shows it the best.
Oh, wow.
Well, Colonel Hadfield,
so lucky. Thank
you. You are here, goes on sale today.
Good evening from Mission Control Houston, and welcome back to tonight's continuing coverage of the landing of the Soyuz TMA-07M spacecraft and its crew of 3 Expedition 35 astronauts. As of right now, the crew is moved into their Soyuz craft, having shut the hatches between the craft and the International Space Station successfully back at about 2:50 p.m. Central Time. The 3 are suited up in their Sokol launch and entry suits and inside of the descent module. As of right now, they are moving towards the next major milestone for tonight's activities, the scheduled undocking from the International Space Station. They accomplished a series of leak checks on either side. Before entering the craft, they were able to say a final farewell to the 3 astronauts and cosmonauts that will remain on board the International Space Station. Here you can see them beginning to egress into their docked Soyuz vehicle. All of the crew currently inside of the Rassvet module right here. You can see NASA astronaut Dr. Tom Marshburn now moving in. The man he's moving past in the striped shirt there is Pavel Vinogradov, a Russian cosmonaut who is remaining on board and will continue his stint as commander of Expedition 36, having taken over command of the International Space Station yesterday from departing commander, Canadian Space Agency astronaut Chris Hadfield. Now giving a final goodbye there and climbing in, you can see Russian cosmonaut Roman Romanenko. He will be in the center seat of the descent module throughout the flight this evening, in charge of all the Soyuz systems throughout the flight. He is the TMA-07M commander. There you can see the hatch being closed between the two, the hatch on the Soyuz craft. The crew arriving in that craft after launching from the Baikonur Cosmodrome back in December.
Approximate. In a minute, I will select depot. Okay, separation confirmed. Timer is on.
And separation confirmed at 6:08 p.m. Central Time, while the station and Soyuz craft fly about 257 statute miles over eastern Mongolia.
Well, do that.
Backing away at a rate of just a little over 1/10 of a meter per second.
R7. Okay. Depot B1 confirmed. Send in S7.
R7. Команда ПСС, как нас слышно?
I'll copy.
Ну как, интересно? Очень.
There we are getting live views now from the search and recovery forces of that Soyuz craft as it makes its final descent.
Everything is nominal.
You can see it there under the main parachute, heading down towards its touchdown just about 10 minutes from now.
So
while we're getting communications from the crew, you also hear the intermittent beeping sound. It's a beacon that is emanating from the Soyuz craft that search and recovery forces can use to pinpoint the exact touchdown location of the Soyuz vehicle. These helicopters carried many of the essential personnel to the landing zone, including flight surgeons, as well as landing site personnel in charge of safing the vehicle and extracting the crew, and also erecting the medical tent. At this point, the Soyuz spacecraft was descending at a rate of just about 7.2 meters per second. And once there, you can see the soft landing rockets fire just about 2 seconds before landing, slowing it to a final descent rate of just 0.8 meters while right above the ground. Now we're standing by as the Russian recovery forces, in concert with personnel from NASA and the Canadian Space Agency, move in to begin extracting the crew from the Soyuz craft, landing almost on the dot there, just to the southeast of Zhezkazgan.
okay, let's get ready for the hatch opening. Okay, I'm standing. I'm ready. Attention. Careful. Hello. Welcome back.
Our first look at the returned crew. Roman Romanenko there in the center seat, Chris Hadfield to his left, and Tom Marshburn to the right. The astronauts will be carried over to these seats where they can relax for a moment as they're all extracted before eventually being moved over to the medical tent erected about 100 meters away from the landing zone. Once inside that medical tent, the crew will get their initial medical exam. Meanwhile, Canadian Space Agency astronaut Chris Hadfield being lowered into his seat now after being extracted from the Soyuz craft. All three crew members now safely out.
We'll see it once again. Oxygen 90.
Thumbs up from Canadian astronaut Chris Hadfield, returning from his command of the International Space Station. Chris was the first Canadian commander of a spacecraft, wrapping up a historic 144 days on board the station.
How are you doing? Yes, yeah. Boy, that was quite a ride home. Quite a sun.
Roman Romanenko heading to Star City, Russia. Hadfield and Marshburn heading back to Houston. But for now, the crew members out of the Soyuz craft, which landed successfully at 9:31 p.m. Central Time.
Now, something that happens when astronauts first come into space is that they usually feel pretty rough for about the first 24 hours, a mixture of dizziness and becoming disorientated and sometimes nauseous as well. And I think a lot of this has to do with the fact that the vestibular system is a little bit messed up. All the fluid in the inner ear is in microgravity, so it's just floating, and so the brain is getting these mixed signals from the ear versus the eyes. And I'm pretty sure that, you know, the brain sorts this out after about 24-48 hours and shuts down the vestibular system and relies more on information that's coming from the eyes. And that helps you because it stops the dizziness, it stops the disorientation, there's no more nausea, and you can turn yourself in all sorts of orientations, around, upside down, and spin about, and it doesn't really matter. Your brain is able to cope with that situation. So I wanted to do a quick check today and just to see if I can make myself dizzy, and if I can make myself dizzy, how quickly can I recover, and does it make me feel unwell? So I'm going to get Tim to spin me around doing something that would probably make me feel quite sick down on Earth. So let's see how that goes. This could be the worst idea I've ever had.
Oh, come on, you can do better than that.
Okay, so yeah, I'll just go into a ball and start spinning, and then if you want to just keep me go round, and
Try to keep you on axis too.
yeah, on axis, that's cool. Well, actually, it's more provocative when you go off axis.
Yeah, I'm not sure I could even control it.
Yeah, no, don't worry. Provocative's fine. Just keep it going.
You want faster?
Yeah. Let's go for it. That's good.
It's really simple.
Okay. So at the moment, I'm just starting to feel the G's of the acceleration there. Yeah. So I was gonna, that's really fast. Does that look fast on the outside? That's really fast from my point of view. But I mean, I'm seeing the world whiz past me really quickly, and I'm starting to feel the increased pressure at the top of my head now, I guess, with the acceleration. But it's not making me feel ill at all, not in the slightest. Not dizzy, and I'm finding it hard to focus on things because it's going past so quickly. But I'm feeling absolutely fine. That's quite remarkable. I think if I was on Earth by now, I'd be feeling very, very unwell.
Without a doubt.
And I've got my eyes open, I'm moving my head. When I move my head, that is definitely provocative, and that gives me some off-axis. But again, it's not making me feel sick. That's quite weird. Okay, if you want to stop me.
Yep.
Okay, I'll see if I can. I'm feeling dizzy. I'll see how quickly it stops. So it definitely felt dizzy initially, and now it's gone.
No, is that quick?
Yeah, completely normal.
Amazing.
Yeah, and again, I wouldn't be able to kind of just get off a fairground ride spinning that quickly for so long. I feel normal. Yeah.
Crazy.
It is amazing.
It's a good demo.
Yeah. Okay.
Hi, I'm Ashley, and I'm in grade 9, and my question is, how does being in space for so long affect your body?
It affects us a lot of different ways. It affects your bones, your muscles, but one of the ways that we're learning recently is it affects your vision. We don't understand why, but it makes some people's vision worse, and we're studying it and trying to figure it out. So we have a lot of new equipment on board just to test and understand our vision. One of the things we have is a tonometer. This is actually like a pressure gauge that you touch to your eyeball. We put drops, it's weird to put drops in your eyes with no gravity. You sort of touch the little drop thing to your eyeball. It spreads over your eye. And then one of the other astronauts will just tap the center of my eyeball really carefully about 10 times. And this lovely little tonometer will figure out the pressure inside my eyeball. That's one way to measure our eyes. Another is to look into the back of them. And so we put those drops in your eyes that dilate your eye, and then I actually put this up against my eye and plug this into a computer, and then I can look into the back of my eyeball, and there are expert doctors on the ground who are looking at my eyeball while I'm doing it, and we could take photographs and videos of the optic nerve, or at least where it comes into my eyeball, and the veins and the stuff that's inside my eye. So we can do it that way. And then also, we actually do ultrasounds of our eyeballs, and that's in order to see how our eyeballs are changing, what's going on with the optic nerves. And so we have a full ultrasound machine on board, but we don't need gel. You just put a ball of water in your eye, and then you touch the ultrasound to your eyeball, or just to the water above your eyeball, and move it back and forth. And with that, we can see our whole optic nerve. We can see the lens and the cornea and everything in beautiful resolution. It's something we've just started doing, and we have experts on the ground who are helping us do it. But with all of these things, we're trying to figure out how the human body works and what controls vision and how it changes when you take away something as simple as gravity. We're learning more about eyeballs, but we're also learning more about how to stay in space permanently. So if you go to Mars, you won't show up there with bad vision.
astronauts all love their food. So, NASA tried to ensure space food is as much like home cooking as possible.
Oh, yeah.
The process begins here.
We're making spaghetti with meat sauce.
It's only when it gets back to the NASA lab, things change.
Thank you.
Spaghetti and meat sauce is just one of 250 options that the astronauts can choose from. And all of them are forensically prepared.
We have a database where we maintain the nutritional content of all our products, calories, fat, protein, carbohydrate, things like that.
The biggest challenge with cooking for space is weight. It costs $10,000 to blast each 1-pound serving to the astronauts. NASA has a clever way of dealing with the cost by removing 97% of the water.
Freeze drying removes a high percentage of the moisture, so typically when we freeze dry our products, we take them down to about 3%.
Each portion now weighs just 1 ounce. Cost to transport, $660. 1,300 miles away, an orbital Cygnus resupply module is being packed.
These are the tortillas. They're very popular on orbit.
Each apple is worth its weight in gold to transport.
As you can see, we're only sending 3 apples, so you may think that's unfair because we have 6 people on orbit. They may have to share.
For this launch, the precious cargo is hand-carried to the site at the very last minute.
It's on its way.
3, 2, 1.
Less than a kilometer away from us now.
2 days later, and the groceries are arriving.
We're getting ready to berth the Cygnus 1 vehicle. All right. Looks really good. Perfect. Perfect. All right. Bonus food.
Including some surprise treats from their families.
Wow. Oh, look at that.
Tortillas.
The real tortillas. Look at that. Real tortillas.
Wow.
Oh my goodness gracious. The greatest hot dog relish in the history of man. Oh my gosh, my wife didn't tell me about this.
Very frequently get asked. I would say every single week I go speak, which is 52 weeks a year now for 16 years. Every single week somebody will say, now Hovind, how do we see stars billions of light years away? You say the Earth is only 6,000 years old. How do we see the stars? Yesterday on the radio program, on the website, Dr. Dino, some guy called in and said, now, Hovind, I did some studies, and in a 6,000 light year radius, we'd only have so many cubic miles, and all the stars wouldn't fit. I said, wait. Who said anything about a 6,000 mile radius? He said, well, you're the one that said the universe is only 6,000 years old. Yes, I did. But I did not say all the stars are within a 6,000 light year radius. I've never said that. That would be ludicrous. But how do we see the stars billions of light years away if the universe is only 6,000 years old? And I believe the Bible clearly teaches it's only 6,000 years old. And God made everything. Actually, He made the earth first in Genesis 1. And then verse 14, He made the stars also. Evolution says He made the stars evolve first and then the earth. Well, there's certainly a lot of stars out there. Nehemiah chapter 9 says, Thou, even Thou art Lord alone. Thou hast made the heaven of heavens. God is claiming that He made them. So, either He did or He didn't. But what about the stars? How do they fit in? Astronomers can see a star blow up about every 30 years. It's not like it's on a timetable. It might be every 5 years, might be every 50 years, but on an average, every 30 years, a star explodes. And they're looking out there with their telescope and say, oh, wow, there's a new one. A star exploded. It's called a nova. Or if it's a big one, they call it a supernova. Nova in Spanish means no-go. By the way, the Chevy Nova did not sell very well in Mexico for that reason. Hey, do you want to buy a Nova? No. Why would I do that? It won't go. But stars blow up every 30 years. Well, they've searched the heavens with these telescopes looking for how many supernova rings are there. They call it a dead star. Or they can find less than 300. Now, wait a minute. If there are less than 300 supernova rings, and one happens every 30 years, You can do the math. I mean, that's about 9,000 years. If the universe is billions of years old, there ought to be a whole lot more supernova rings out there. Why are there less than 300 supernova rings? Because it's less than 10,000 years old? Boy, they don't like that answer at all. But that's the logical conclusion. Anyway, if stars are blowing up every 30 years, we would have to have at least one star born every 30 years just to keep the balance. I mean, countries that have a population problem because they're getting less births and deaths, like Germany, more people are dying than being born. Oh, well, eventually that's going to create a problem, okay? Stars should have to be born. Nobody's ever seen one star form, not one. We see them blow up all the time. They've never seen a star form, and I'll cover that in a second. Its last estimate by Hubble telescope was that there are 70 sextillion stars. 70 sextillion. They say the universe is 20 billion years old. Well, you can do the math. That means 6.5 million stars would have to form every minute. We'd have to have 6.5 million stars forming every minute for 20 billion years to make the stars that we know about. It doesn't count the ones we don't know about because we can't see them yet. Who knows how many stars are out there? Sometimes the textbooks will say, well, there are new stars being constantly born in clouds of gas and dust. This is so stupid. How a physics textbook can teach this, I don't know. Anybody that knows freshman physics knows when you try to squeeze gases together, pressure builds up, temperature builds up, and it drives them back apart. It's called Boyle's gas law. Nobody has ever seen dust collapsing into a solid. It would take such incredible pressure to do that. I was in a debate one time, and this professor, I asked him, I said, how can you get dust to collapse into a solid? Explain that to me. He said, well, we calculated that if 20 stars explode near each other, it'll produce enough pressure to make a brand new star. I said, now that's brilliant. You got to lose 20 to gain 1. I said, you ought to run for Congress. You could help those guys borrow their way out of debt, you know. It's not going to get a universe full of stars if you got to lose 20 to gain 1. And even that is only theoretical. It's never been observed, okay? I was in Alamogordo, New Mexico, and they've got a science center down there, and they showed these pictures of star babies. He said, oh, this is a new star forming. No, sir, it's a bright spot, okay? One guy in Science magazine admitted, the silent embarrassment of modern astrophysics is we do not know how even a single one of these stars managed to form. Nobody knows how stars can form from dust clouds. No one has unambiguously observed material falling into an embryonic star, which should be happening if the star is truly still forming. And no one has caught a molecular cloud in the act of collapsing. Precisely how a section of interstellar cloud collapses gravitationally into a star, a double or multiple star, or a solar system is still a challenging theoretical problem. Astronomers have yet to find an interstellar cloud in the actual process of collapse. The origin of stars represents one of the most fundamental unsolved problems of contemporary physics. This guy said, no one really understands how star formation proceeds. It's really remarkable. Nobody knows how this happens. So if they tell you new stars are forming, you tell them Kent Hovind said they're confused or they're lying. Because nobody knows how it happens. There's not even a good theory how you could squeeze dust into a star, and there's certainly no evidence. But here's what happens. They see bright spots appear in the clouds. Right, not in the clouds, in the dust clouds in space. They look at this Crab Nebula or Eagle Nebula, and they're staring at it, and all of a sudden one day a spot gets a little brighter. Oh, wow, a star's being born. That's immediately their conclusion that a star is being born. I said, wait. Maybe the dust in front of it is clearing and the star was already there. Maybe it's a star blowing up. Maybe it's another supernova. Because that's what happens when stars supernova, they get really bright. They don't know that a star is forming. So don't let them tell you that we've seen stars form. Nobody has seen such a thing. All we do is we see them blow up, which is the opposite of what evolutionists need. Now, the Bible says in Genesis chapter 1, let them be for signs and seasons and for days and years, and he made the stars also. Here God is claiming he made the stars, and it says in Psalm, he counts the number of the stars. Not only how many there are total, but each one has its own number. So God will say, oh, this is star number 42 trillion, 718 billion. He knows the number of each one. And it says, praise him, ye waters that be above the heavens in Psalm 148. This is the only verse that says anything like this. Waters that be above the heavens. Now in Genesis 1, it talks about verse 6 and 7, water that be above the heavens. I believe when God first made the world, it was very, very different than what we see. Mostly land, instead of the huge oceans that we now have. Most of that water was in the crust of the earth. We covered that in video 2. But there was earth and there was heaven, singular. King James is the only Bible I'm aware of that gets it right in Genesis 1:1, where it says, in the beginning God created the heaven and the earth. All the rest of them say heavens. Okay, that's a mistake. There was heaven, which means expanded place. There was earth, and then from here on out. Then he divides it up into 3 slices. First heaven, second heaven, third heaven. The first heaven is where the birds fly. Genesis 1 talks about that, verse 20 and 21. Then there was water above the firmament. Now, some creationists do not believe in the canopy theory. I understand. I've read their stuff. I think they're wrong. I still believe, and some accuse me, well, you don't agree with us, therefore, you're not a good creation scientist. To keep up on your research. I keep very much up on the research, and I disagree. It's not that I haven't read it, it's that I have read it and disagree. Okay? But I believe there was a layer of air for Adam to breathe, layer of water above to protect him, and then a layer of stars, and then more water. The only verse I have to back it up is right here, Psalm 148. Praise him, ye waters that be above the heavens. That's present tense. Is there still water above the heavens? Psalm 104 says, who layeth the beams of his chambers in the waters, who maketh the clouds his chariot, who walketh upon the wings of the wind. Could it be that there is another layer of water beyond all of outer space? Maybe everything that we see as this universe, which looks like huge, maybe everything we see is inside water, a crystal, and God is outside of that, the third heaven, 2 Corinthians chapter 12. Could there be a third layer where God lives? Of course, God doesn't need a place to live. He just is, Psalm 29 says, the voice of the Lord is upon the waters. The Lord is upon many waters. Maybe everything that we see when we step out at night and say, wow, look at all these stars. Maybe the whole thing's a little snow globe on God's dresser. That he picks up and shakes once in a while. How you doing in there? I don't know. I like to think that way. But the Psalm 148, the waters that be above the heavens, people have often asked, hey, where's the last star? And once we find it, what's on the other side? I don't know the answers to those, but just a possibility is that there, according to the Bible, may still be water above the heavens. But there's a lot of stars out there. Hubble estimate was 11 trillion stars per person. That is 76 trillion divided by 6 billion people. Every one of you gets 11 trillion stars. What happened, they told the Hubble telescope to focus in on a dot. They found a dot above the Big Dipper. You can see the picture of it there. It is about the size of a grain of sand, held at arm's length. And it was black. They said, we don't think there's any stars there. Let's focus in on that spot and see what we can find. They took pictures for 10 days straight, focusing in on that dot. After 10 days, there were more stars in that dot than they could count. These were brand new stars, never been seen before. Called it Deep Field, Hubble Deep Field. Looking up there saying, man, that's stuff we didn't know about. Assumption would be that it's that way all through space. Truly, the stars cannot be numbered, which is what the Bible says. They cannot be numbered. But how do you tell the distance to the stars, and how can the Earth be 6,000 years old and the stars be so far away? Fair question. Stephen Hawking said, stars are so far away, they appear to be just pinpoints of light. We cannot see their size or shape. How do we tell different types of stars apart? For the vast majority, there's only one thing we can see, and that is the color of their light. If you get the biggest telescope on Earth, this is not it, by the way, spotting scope, but if you get the largest telescope on Earth and look at the closest star, which is Alpha Centauri, 4.5 light years away, all you're going to see is a dot. If I focus this in on the sun, it'll start to get bigger and bigger, and you can actually see flames leaping off and see the spicules, and you can see color changes, and you can actually see features of the sun. When you look at a star, you never get to see that. Nobody has ever seen a star as far as any of the features of it. You get the biggest telescope on Earth, it's going to be nothing but a dot in your scope. All you can tell is, I say, that's a red one, that's a yellow one, that's a blue one. That's all you can see. So anything we do, we have to do based on assumptions just from the color. But how do you tell the distance to the star? Well, I taught high school trig for years, and if you guys had trig, you know how it works. If you have 2 observation points, you can calculate the third distance. You have to know it's solving a triangle. Trigonometry deals with triangles, so you sine, cosine, tangent. If you know one distance and two angles, or two distances and one angle, you can calculate the rest of the triangle using sine, cosine, tangent. Here's the problem. Earth is only 8,000 miles in diameter, which compared to star distance is zero. It's nothing. So if I'm looking at a star and somebody over in China is looking at a star, we are 8,000 miles away from each other, straight line through the Earth. That would be nothing. What they've done to enlarge the distance to look at a star, instead of just being opposite sides of the Earth is also going around the Sun in this great big huge circle. We're going 66,000 miles an hour, and it takes us a year to go around. Great big racetrack. Well, the distance from the Earth to the Sun is about 93 million miles, average. And that's a lot, but at the speed of light, it's not much. At the speed of light, it's 8 minutes away. It takes the sunlight 8 minutes to get to the Earth. So if we're 8 light minutes from the Sun, the diameter of our orbit going around is 16 light minutes. So what we're going to do is we're going to look at a star in January, and then we're going to look at the star in June, and we have now gone halfway around this monster circle. And we're going to get 2 observation points to try to enlarge the base of our triangle. And it sounds huge. Man, that's 186 million miles. Well, it's still not much. A year has 525,000 minutes in a year. If this picture here showing the little yellow dot was the scale, if that yellow dot represented Earth's orbit, not the Earth's diameter, the orbit of the Earth, it's way too big for the picture. What we're going to do is try to show you the math involved here. If I had 2 surveyors setting up with their transits or telescopes, and they are 16 inches away from each other, and they're both looking at a dot 525,000 inches away, which is 8 1/3 miles. Would you agree that would make a rather skinny triangle? Let's go out in the parking lot and draw a triangle with point A and point B 16 inches apart, and point C 8 1/3 miles away. It's going to make a real skinny triangle. That is exactly the triangle you get when 2 people on opposite sides of Earth's orbit try to measure 1 light year. 1. Now, and I'm not sure you can tell exactly where you were 6 months ago. I think that would be a little stretch of the imagination to say, oh yeah, 6 months ago in January we were, I'll give them that. I won't even argue that. I just would bring that up, for appeal, Your Honor, in case we need to. You can't know exactly where you were 6 months ago. But the angle you get with that is 0.017 degrees. Now let's imagine this. I want you to get 2 guys to set up their surveying transits. They're 16 inches apart, and I'm going to go put a dot 8 1/3 miles away, but they don't know how far away it is. They're both focusing in on the dot, and they see this dot out there. Here's the only information they have. The measurement between themselves, 16 inches, and the angle out of parallel. I say, guys, I want you to calculate how far away that dot is based on that little angle change you get. I think that would be difficult to measure. 1 light year. There'd be some guesswork involved, okay? Now, if you want to measure 100 light years, you got a much worse problem. Now you got to move your dot 830 miles away. If we had 2 guys on the roof of this building here in Pensacola, Florida, 16 inches apart, and they're both focusing on a dot in Chicago, which is 830 miles away, but they don't know how far away it is, they're going to tell me how far away it is, based only on their angle of their telescope out of parallel. I would say that's impossible. Impossible. To measure 15 billion, no question that's impossible. I don't think you can measure 100 light years. Not with real numbers, not with real measurements, but this textbook says they can measure, parallax trigonometry can measure up to 100 light years. Okay, I doubt it, but I'll give them 100. I'll give them 1,000 if they quit crying, okay? The fact is you can't measure 1 billion. Simple fact. So here's some things to consider about starlight. It said in 2004 that the new SIM technology, Space Interferometry Mission, they hope to get where they can improve the distance of measuring to stars. And they say this accuracy will enable SIM to determine stellar distances to 10% accuracy out to a distance of 482,000 million miles. That's 82,000 light years. And then it says, this is an improvement of several hundred times over what is possible today. Well, now wait a minute. If they're going to improve it several hundred times, and it ends up being 82,000, what's 82,000 divided by several hundred comes out to be several hundred. Apparently they're admitting they can only measure several hundred light years, which I would agree. I mean, I would say that's even a stretch, but I'll give them several hundred. They can't measure billions, is the point. So when you students in school get taught, oh, that star's, 14.629, billion light years away, I don't believe you. I don't believe you at all. It might be, but you can't prove that. They're making up a story. With SIM technology, they hope to finally be able to get out to where they can measure most of the way across our galaxy, and we're in it. We can't even measure across our own galaxy, let alone these distances to other galaxies. So I think we should look at the stars and say, wow, what a mighty God we serve. Instead of going out there and say, well, we know how far that way it is, we know it evolved. I mean, it's just that egotistical attitude some of these atheists get, makes you want to slap them in the face, like, man, why don't you serve God? Look what he made, Here's the things to consider concerning starlight. Then we'll take a break. Number one, we cannot measure these great distances. It just cannot be done. Number two, nobody knows what light is. They call it a wave or a photon or a particle. We know what it does. We use it all the time. But actually, give me a jar of it and paint it red. Nobody knows the substance of it. What is light? And we sure don't know that it always travels the same speed all through time or space. The entire theory behind a black hole is that light can be attracted by gravity. Well, if light can be attracted by gravity, then you cannot say the speed of light is a constant. Okay? At Harvard University back in '99, they slowed light down to 38 miles an hour. The next year, they slowed it down to 1 mile an hour. And the next year brought it to a dead stop. Light goes, pretty quick, 186,000 miles a second. They slowed it down. It was done at Harvard. It was done at Smithsonian. It was done at Cambridge University. A repeatable, demonstrable experiment. Now that is science. If you do an experiment, get a result, somebody else follows your data, does the same experiment, gets the same result, that's science. They slowed light down. This article came out on Fox News Channel. They said, we've succeeded in holding a light pulse still. They brought the speed of light to zero, brought it to a dead stop. Meanwhile, back in 2000 at Princeton University, they speeded light up to 300 times the speed of light. So when somebody says that star's 10 billion light years away, which I doubt they can measure, therefore that we can prove the universe is 10 billion years old, they got several problems in their logic right away that they probably don't see, which is why we do these seminars, so we can help people understand. It's 300 times the speed of light. Astronomer Barry Setterfield, Australian government astronomer, said, during the last 300 years, 164 measurements of the speed of light have been published using 16 different measurement techniques. The speed of light has apparently decreased so rapidly, experimental error cannot explain it. This is a chart showing the decline in the speed of light from the published numbers in the last 150 years. You notice the decline in the chart. The speed of light's getting slower until about 1960. For the last 40 years, anybody that's measured the speed of light gets the same number, 186,282.4, I think, miles per second. Who cares? Well, it could be that it leveled off in 1960 for two possible reasons. Three possible reasons. Our way of measuring is getting better. Instruments are getting better. We're smarter. Everybody in the past was dumb. We're smart. We got it right. Could be. That's what they'll tell you. Second option, though, is we're at the tail end of a logarithmic curve, and you're much less likely to see any decline. As you get further out on the logarithmic curve, it pretty much levels out. But a third reason is 1956 is when they invented the atomic clock. And they started using that as their clock to measure the speed of light. Well, now, wait. The atomic clock is based on the wavelength of a cesium-133 atom. So the clock is based on the speed of light. Now, if you have a clock based on the speed of light and you're measuring the speed of light with it, if the speed of light changes, you're never going to catch it with that clock. It's like watching two twins grow next to each other. Well, neither one's growing. Well, duh. You got a rubber ruler problem here. Clear back in '87, they said the speed of light was 10 billion times faster at time zero. There must have been a faster speed of light. There have been articles from the 80s, 90s, 2000s saying, look, the speed of light is not a constant. They said no physical law prevents anything from exceeding the speed of light. In 2 published experiments, the speed of light was apparently exceeded by as much as a factor of 100. The Big Bang Theory requires a much faster speed of light. Dr. Magliucci, or however you pronounce his name here, I got his book on the table. He says, a shocking possibility is the speed of light might change in time during the life of the universe. Could it be the speed of light was faster? Here's an article in the newspaper said, speed of light may have changed over history, study says. Winnipeg Free Press, nothing's reliable, not even the speed of light. We have shown that a time-varying speed of light could provide a resolution to well-known cosmological puzzles. One of the mysteries of a decaying speed of light seems to be able to explain why opposite extremes of the cosmos that are too far apart to have been in contact with each other appear to obey the same rules of physics, and even about the same temperatures. It would only be possible for light to cross from one side to the other if it traveled much faster than today, moments after the universe was created. Is the speed of light really a constant? There are articles here in Reuters News Service, the speed of light may not be a constant. I have dozens of articles like this in the last 15 years, and this will be much more detail in our college class about the speed of light. So don't let somebody tell you the speed of light is a constant. We don't know that. Big article came out in Discover magazine, says, was Einstein wrong about the speed of light back in 2000? He said, yeah, Einstein was wrong. The speed of light is not a constant. There's the book by the Italian scientist, I'm assuming he's Italian. It says, look, the speed of light is not a constant. And there have been many articles published about this. You can read them for yourself. I'll flash through them quickly here and you can get the details. So the third thing to consider, the creation was finished when God made it. Not only can we not measure those distances, not only is the speed of light not necessarily a constant, the creation was done. See, Jesus made wine out of grapes that never existed. He's missed all that time. Instead of going from the water in the ground, through the plant, into the grape, squeeze it, make the wine, now drink it. No, Jesus turned the water straight to wine. What happened to all the intermediate steps? God can bypass all that. He doesn't need any of that. Okay? I ask people the question, how old was Adam on day 6? Anybody know? How old was Adam on day 6? 0. Did he look 0? No. He looked 52. 53 next month. But he looked perfect top, physical condition. God didn't make 2 babies and put them in the Garden of Eden and hand them a package of seeds and say, here, plant these quick. You're going to need supper. It has to be a full-grown man, full-grown woman, full-grown garden. They got to have supper like tonight, Better be something hanging on the tree ready to eat. Even if you plant a tree, you're going to take 4 or 5 years to get fruit off it. So the creation had to be mature. A fourth thing to consider about the speed of light question. A light year is a distance, it's not a time. It's a distance. And since the speed of light is not proven to be consistent, why would star distance have anything to do with the age of the universe? Now, I am not saying, and have never said, all of the stars are inside of a 6,000-mile radius of the Earth. That is not what I say. I don't know any creationist that teaches that. So when they say that, they're setting up a straw man, knocking it down. They're lying, basically. The stars probably are billions of light years away. They probably are. We just can't measure them, that's all. I like this article in the Discover. It said, how do scientists measure the age of stars? They said, well, we can find the absolute ages by comparing a star's color and brightness with those in stellar evolution models. What? We can tell how old it is by how old we think it is. That's exactly what they're saying right there. That's dumb, okay? Now, I think everybody's asking the totally wrong question. Everybody's saying, how did the light get from the star to the Earth? They're asking the wrong question. 17 times in the Bible, it says God stretched out the heavens. Well, if He stretched out the heavens, they're asking the wrong question. It's not how did the light get from the star to here, but how did the star get from here to there? That's the question we need to be asking. The Bible says pretty clearly God made the earth first, and then He made the stars also. And He stretched, suppose He made the earth, and then He stretched out the stars from here. Adam would see the stars on day 6, and day 7, and day 8. As the star is being stretched out into place, it's going to leave behind a trail of light. So the stars could be billions of light years away today, and still have been created in the 6 days, 6,000 years ago. Russell Humphreys has a book which I read, and I just have to say, I didn't understand it, all of it. He's really, really smart, but it's a good one on starlight and time if you want to get more on that. I don't know that I agree with his premise. I think he starts with the assumption the speed of light is a constant. Now, how do we explain that? and they get into this warped space and bent space stuff. I think it's much simpler. The speed of light's not a constant, and God made things and stretched them out into place.
The real universe is the biblical universe. That's just the way it is. What about distant starlight? I want to spend some time on this one because this seems to be a big problem for a lot of people in terms of embracing what the Bible teaches. It really shouldn't be, but because of the weakness of our faith, sometimes we need a little more. Distant starlight really is not a problem for young universe. What I'm talking about here is the fact that we can see these galaxies that are billions of light years away. And when I use the term light year, that is a unit of distance, not time. A light year is about 6 trillion miles, okay? And so when I say the universe is billions of light years in size, that just means it's really big. It doesn't mean it's old. People hear the word year in there and they think that, well, doesn't it have something to do with time? Well, a light year is the distance that light under normal circumstances would travel in 1 year. And so you'd think if these galaxies are billions of light years away, that it would take light, billions of years to get from there to here. And obviously the light has got from there to here because we see them. And so doesn't that prove the universe is billions of years old? And this has come to be called the distant starlight problem. But I want to give you what I think is a solution to this. There's actually a number of different ways to resolve it, which is interesting. And of course, God has access to solutions that we might not have even thought of or even considered. He's not bound by laws of nature as we are. But I do want to point out that some of the proposed solutions really don't work. And I mention this because sometimes people will come up and say, well, have you thought of this? And yeah, we've thought of that. And there's a reason it doesn't work. Some of the simpler solutions that people think of really have been investigated and they don't pan out. The idea that the distances aren't real, maybe the galaxies are all within 6,000 light years, it's not realistic. Even our own galaxy isn't within that distance. These distances, I won't go into all the details, but there's good science to support the fact that these are incredible distances. The idea the speed of light was much faster in the past, I think that was very worthy of consideration. I'm glad that they looked into that, but I think there's compelling evidence that it was not faster in the past. The speed of light is linked into other properties in nature. It sets the relationship between, for example, between electric fields and magnetic fields. It sets the relationship between energy and mass. And so if you tinker with the speed of light very much in vacuum, it might not even make atoms possible. So we like the speed of light the way it is. Light was created in transit is one that I want to spend a little more time showing you why I don't believe that's a good idea for starlight. People have pointed out, well, the universe was made mature in the sense it was functional. Adam was made as an adult. He didn't have to grow up from a baby. And if you assume he grew up from a baby, you'd conclude the wrong age by looking at him. And that's true. That's certainly true. And so people have said, couldn't starlight be that way? Couldn't it be that God made the beams of light, the star, connecting the star to the earth? I think not. And the reason is because it would require God to create fictional images and movies. And I want to show you what I mean by this. Here we have supernova 1987A. There was a star in one of the Magellanic Clouds, and that little star right there in 1987 decided to blow itself to bits. Very sad, but it's a supernova. And so that star blew up. Now this star is in one of the Magellanic Clouds. It's over 100,000 light years away, let's say 170,000 light years away, something like that. And today, it looks like that. We see expanding star guts, what's left of the star expanding off into space. Now, if you say, well, when did that happen? Now, the secularists would say, well, 170,000 years ago, and the light just got here in 1987. And if you say, well, no, the reason we're able to see that is because God made the beam of light already on its way. When did this happen? Well, if you believe in light in transit, this didn't happen. It was just a picture that God made in a beam of light about 6,000 light years out that finally reached the Earth in 1987. If you believe in light in transit, this star never existed. That explosion never happened. And by the way, this doesn't exist either. These are just pictures that God put in a beam of light. And that really bothers me. It's not that I don't think that God has the power to do that. Of course he has the power to do that. The question is it consistent with his nature to do something like that? And I don't think it is. And if I don't think God would create light with fictional information in it, as it were. And if you say, well, I don't know, I think he might. Be careful, because how do you know I'm here right now? Right? I mean, how do you know God isn't making the light 1 inch away from your eye? An image of me. Well, we hear you too, no problem. God made the sound 1 inch away from your ear. No, I don't think that God makes fictional pictures for us. So if light in transit is true, then none of these things have ever actually existed. But we do see these things. And I think there's a better answer anyway. One of the ones that I thought was a little more plausible, I think it's not the right answer, but I want to mention it because at least it deserves consideration. Dr. Russ Humphreys has pointed out that time can flow at different rates under different circumstances. Einstein discovered that. And Humphreys says, well, maybe that's the solution to starlight. Maybe that clocks on Earth tick slower than clocks in the universe. And I've chatted with him about this. It's an interesting model. I haven't seen the math work out in a way that actually solves distant starlight, though. But he continues to work on it, and it's interesting. I'm going to suggest that the solution may involve, I'm going to give you what I think the answer is. I think it involves the one-way speed of light. And that is the speed of light on a one-way trip as opposed to bouncing out off a mirror, a two-way trip. The speed of light in vacuum is 186,282 miles per second, very fast. But that is a round-trip average speed. And what I mean by that is if we wanted to measure the speed of light, here's how we could do it in principle. We could build a very long hallway, okay, 186,000 miles long. We'll pretend we have government funding so we can waste it that way, okay? And we'll put it out there. And so I'm going to stand over here on this end with my flashlight. I'll have a mirror at the other end. Or another flashlight, either would work. And what I'm going to do is when the clock strikes noon, I'm going to send out I'm going to turn on the flashlight for just an instant, send that pulse out, and it'll reflect back. And as soon as I see the reflection, I'm going to look at the clock and see how much time has elapsed. And if we were to do this, we would find it takes 2 seconds for light to go out and come back. And so it's traveled a distance of 186,282 miles twice, and it's taken 2 seconds to do that. So the average speed is 186,282 miles per second. That's how you get the speed of light, and that's what we would find. Most people assume that it took 1 second to go out and 1 second to come back. But we don't actually know that, do we? All we know is the total time is 2 seconds. It could be, hypothetically, the case that the light zips out and takes all of 2 seconds. Maybe it takes no time at all for it to get out there, and then it takes all of 2 seconds to get back. That's a possibility. Or maybe it's the reverse. Maybe it takes all of 2 seconds to travel out there, and then it zips back instantaneously. And people have said, well, why? Is the mirror affecting it? No, it doesn't have to be the mirror. You could even use another flashlight out there. And when your buddy sees the beam, he turns on the return trip. It could just be that the nature of space is such that light propagates at a different speed this way than it does that way. You'd say, why would it be that way? Well, there are certain crystals that do that, where the speed of light's very different in one direction than another. And it could be that the vacuum of space is like that. The point is, we don't know. And you see where I'm going with this, because if this is the case, if light, when it's moving away from me, is slower, and when it moves toward me, it's much quicker than the average speed, that would solve the distant starlight problem, wouldn't it? Because I don't have to send light out to the galaxies and reflect it back. It only has to make a one-way trip. It only has to go from there to here. But so I'm hoping that this will be the case, but hoping for something doesn't make it so. We want to see if we can do an experiment to measure the one-way speed of light. So how are you going to do that? How are you going to measure the speed of light just on a one-way trip and not a round trip? Well, you can't use a mirror anymore. Instead, you got to use 2 clocks. You got to use one clock to tell you when to start the light pulse, and then another one to record when it impacts. Yes? So I'm going to stand over here. When this clock strikes noon, I send out the pulse, and my buddy's over there with his clock. And when he sees the pulse, he looks at his clock, and you're thinking that'll say, 1 second past noon. Yes? Well, I tried this in my office. I don't have a long hallway, but I have the distance between my watch and the clock on my phone. And I turned on the light right when it hit noon, and the light beam went over to the phone. As soon as the phone, lit up, I said, 12:05. It takes 5 minutes for light to get from my watch to the phone, right? No, you're not buying that? You see what I'm saying? When my clock hits noon, I turn on the light, it goes over, hits the phone says 12:05, 5 minutes. I made an assumption, didn't I? A faulty assumption. And that is, I assumed that the clocks were synchronized. Obviously, the clock on my phone is 5 minutes fast. I do that so I don't miss staff meetings. Okay, so only if the clocks are synchronized could you measure the speed of light this way. And by the way, they have to be exactly synchronized because the speed of light is very quick, whatever it is. We know it's quick. So if that other clock is just a little bit off, you'll get the wrong answer for the speed of light. It could be very wrong. You say, no problem, we'll make sure the clocks are synchronized. That turns out to be very difficult to do with clocks that are separated by a distance. Normally, the way we synchronize clocks is with a radio transmission. In fact, my watch does that. It receives a signal from the radio transmitter in Fort Collins, which is tied into the atomic clock in Boulder. And every night it receives that signal. I never have to set it. It's pretty neat. But it's not maybe exactly synchronized, right? Because that radio pulse actually takes a little bit of time to travel from the source clock to the receiver clock. Radio's fast, but it's not instantaneous. So, well, maybe what we could do, of course, if we knew the amount of time it took the radio pulse to travel from here to here, we could subtract that off. We could push that clock forward a little bit. Well, how fast does radio travel? You know the answer to that? It travels at the speed of light. Yeah. And so that's the very thing I'm trying to measure. That's the very thing I don't know is the one-way speed of light. We know radio travels at the speed of light because if I have a radio transmitter and a flashlight, they'll hit the wall at the same time. We know that. We just don't know what that speed is. My point is you'd have to already know the one-way speed of light in order to synchronize clocks by radio transmission. Now, I don't worry that my clock is maybe slightly behind the one in Boulder because I'm not trying to measure the speed of light. But if you're trying to measure the speed of light, they have to be exactly synchronized. Some people, for some reason, have thought if you put the radio transmitter in the middle, that'll solve it, right? Because then you send the radio pulse in both directions and both clocks are synchronized to noon at the same time. It doesn't matter what the speed of light is, but in fact it does because that presumes that the speed of light and therefore the speed of radio is the same in both directions. If it's different, then this clock gets set to noon first and that clock gets set to noon second. See, noon there and then noon there. And they're not synchronized. See, so you can't synchronize clocks that way. It doesn't work. One last resort. We'll synchronize two clocks in the same place. That's easy to do because you can see they're both reading the same time at the same time. Then we'll move one of them or both of them to opposite ends of the hallway. Yes? That should work, right? It doesn't, because according to Einstein, motion affects the passage of time. The very act of moving the clock has caused it to become desynchronized from its buddy. Now, it turns out there's an equation that can tell you how much the clock has become desynchronized, and you could compensate for it. And in that equation is the speed of light. Yeah. Isn't that interesting? It's almost as if God doesn't want us to know the one-way speed of light. Here's what the implication of this is. Apparently, it's impossible to synchronize clocks without knowing the one-way speed of light in advance. And it's impossible to measure the one-way speed of light without synchronized clocks. So you see, we're stuck in a permanent catch-22. It is fundamentally impossible to measure the one-way speed of light. It cannot be done because you need to have synchronized clocks, and the only way you can have synchronized clocks is if you already knew the one-way speed of light. It cannot be done. Now, when you have a catch-22 like this, it suggests that the question may be a bad question, a faulty question. And so I'm going to conclude that the one-way speed of light is not actually a property of nature at all, but is something that is a convention. A convention is something that we choose and we all agree to it and we stick with it and it works. Like driving on the right side of the road. That's a convention. We all agree to that and it works. But in other nations, they pick the left side of the road. And as long as they all agree to it, it works too. You see, that's a convention. It's not, it's, you know, if we asked, well, what, you know, in the universe, what is the correct side of the road to drive on? That question is meaningless because it depends on what country you're in. It depends on where you're at. Or how many, if I had a table that's, let's say it's 1 yard long or maybe it's 3 feet long. Which is it? Is it 1 or 3? What's the right answer? Is it 1 yard or is it 3 feet? What's the answer, right? Well, yeah, it's both, isn't it? Well, should the number be 1 or should it be 3? Well, you tell me what you want. You would tell me if you're using yards or feet, and I'll tell you what the answer is. The one-way speed of light is like that. We get to choose what it is, and that tells us how to synchronize our clocks. And then when you measure the one-way speed of light with your synchronized clocks, you'll find it was whatever you chose. Yeah. Okay? So the lightning bolt strikes exactly in between these two clocks, and we're going to decide that the speed of light's the same in both directions. We can do that. We're going to choose that, and then the two clocks are synchronized. But if you want to make a different choice, you can do that too, and you can synchronize them differently. That light requires the same time to traverse the path A to M as for the path B to M is in reality neither a supposition nor a hypothesis about the physical nature of light, but a stipulation which I can make of my own free will in order to arrive at a definition of simultaneity. We choose the one-way speed of light, and that tells us how to synchronize clocks. And that quote is by Albert Einstein. Einstein recognized that the one-way speed of light is not something you measure, it's something you choose. Which means I can choose it to be something very different than what most people do. In fact, I can choose the speed of light to be infinite when it's directly toward me, and half c when it's moving away. And the reason I pick those two values, it has to average to c. It has to average to the speed of light. That's the round trip speed. Okay, but you get to pick the one-way speed, and then the average will tell you what the return trip has to be. And it turns out it's 1/2 c if you make it infinite in one direction, because it's a time averaged. And one of the reasons I choose this is because it solves the distant starlight problem. But another reason is because all ancient cultures implicitly used this definition. They didn't subtract off light travel time because they didn't know what the speed of light was. When you saw something, that's when it happened. And so I'm going to suggest that the distant starlight is solved if we use this. I'm going to call it an anisotropic, which means different directions, anisotropic synchrony convention, or ASC. Using the anisotropic synchrony convention, light takes no time at all to get from distant galaxies to here. And according to Einstein, I'm free to synchronize clocks that way. And the distant starlight problem, therefore, is solved if the Bible's using that convention too. And so that's really the only issue. Is the Bible using this anisotropic synchrony convention, or is it using Einstein convention, or is it using something else? It's using some convention because it's talking about time. So there's some convention there. I think the Bible is using this anisotropic synchrony convention. I'm going to show you why. Well, I already mentioned one reason. All ancient cultures used that. And the Bible is meant to be understood by everybody, not just by modern physicists. But if you take a look at Genesis 1, 14 and 15, then God said, "Let there be lights in the expanse of the heavens to separate the day from the night, and let them be for signs and for seasons and for days and years." And later we find this is the sun, the moon, and the stars also, the greater light, the lesser light, the stars also. He says, "And let them be for lights in the expanse of the heavens to give light on the earth." And it was so. It's that last little phrase, "and it was so." What was so? Well, they gave light on the earth. You see, God created them to give light on the earth, and apparently they immediately did, and it was so. That suggests to me that the Bible's using this anisotropic synchrony convention whereby light reaches the observer in no time at all. And according to Einstein, that is a legitimate convention. And by the way, I'm not suggesting that the alternative, that the speed of light is the same in all directions, is wrong, because that's like saying a table, it's wrong to say it's 1 yard long. It's actually 3 feet. They're just two different ways of measuring things. And so I'm going to suggest that the convention the Bible uses allows light to get here instantaneously. It's not a problem. There could be other answers to that, but this is one that works and nobody's been able to refute it, so I think it's a pretty good model.
Dark sky is true. They got a message from the action man. I'm happy, hope you're happy too. I've loved all I've needed love, so would you just follow me? Speaking of nothing is good, there's pictures of jackets and synthesis. Ain't got no money, ain't got no hair, but I'm hoping to get blinded, is glowing, glowing, glowing. Ashes to ashes, fire to forget. Ring down major tones, a junket, strung out in heaven's high, giving an old time loud. no, not again. I'm stuck with a valuable friend. I'm happy, hope you're happy too. One flash of light, no smoking bits down. I never did good things, I've never done bad things. I never did anything out of the blue. No. Wanna relax to break the ice, wanna come down right now. Ashes to ashes, funk to funkin'. We know Major Tom's the junkie, strung out on heaven's high, living an old-time love. Mama said to get things done, you better not mess with Major Tom. Mama said to get things done, you better not mess with Major Tom. Mama said to get things done, you better not mess with Major Tom. Mama said to get things done, you better not mess with Major Tom. Thank you.
Because they received not the love of the truth, that they might be saved. And for this cause God shall send them strong delusion, that they should believe a lie, that they all might be damned who believed not the truth, but had pleasure in unrighteousness.